So the basic approach we're going to be taking here is to get straight into code, start building models, not to look at theory. We're going to get to all the theory, okay, but at the point where you deeply understand what it's for, and at the point that you're able to be an effective practitioner. So my hope is that you're going to spend your time focusing on experimenting. So if you take these notebooks and try different variations of what I show you, try it with your own data sets, the more coding you can do, the better, the more you'll learn. Okay, my suggestion, or at least all of my students have told me, the ones who have gone away and spent time studying books of theory rather than coding found that they learnt less machine learning, and that they often tell me they wish they'd spent more time coding. The stuff that we're showing in this course, a lot of it's never been shown before. This is not a summary of other people's research. This is more a summary of 25 years of work that I've been doing in machine learning. So a lot of this is going to be shown for the first time. And so that's kind of cool, because if you want to write a blog post about something that you learn here, you might be building something that a lot of people find super useful, right? So there's a great opportunity to practice your technical writing, and here's some examples of good technical writing, okay, by showing people stuff which it's not like, hey, I just learnt this thing, I bet you all know it. Often it'll be, I just learnt this thing and I'm going to tell you about it, and other people haven't seen it. In fact, this is the first course ever that's been built on top of the FastAI library, so even just stuff in the library is going to be new to like everybody. Okay, so when we use a Jupyter Notebook or anything else in Python, we have to import the libraries that we're going to use. Something that's quite convenient is if you use these two auto reload commands at the top of your notebook, you can go in and edit the source code of the modules, and your notebook will automatically update with those new modules. You won't have to like restart anything, so that's super handy. Then to show your plots inside the notebook, you'll want matplot inline. So these three lines appear at the top of all of my notebooks. You'll notice when I import the libraries that for anybody here who is an experienced Python programmer, I am doing something that would be widely considered very inappropriate. I'm importing star. Okay. Generally speaking, in software engineering, we're taught to like specifically figure out what we need and import those things. The more experienced you are as a Python programmer, the more extremely offensive practices you're going to see me use. For example, I don't follow what's called PEP8, which is the normal style method, style of code used in Python. So I'm going to mention a couple of things. First is go along with it for a while. Don't judge me just yet, right? There's reasons that I do these things. And if it really bothers you, then feel free to change it, right? But the basic idea is data science is not software engineering, right? There's a lot of overlap. You know, we're using the same languages, and in the end, these things may become software engineering projects. But what we're doing right now is we're prototyping models. And prototyping models has a very different set of best practices that are taught basically nowhere, right? They're not really even really written down. But the key is to be able to do things very interactively and very iteratively, right? So for example, from library import star means you don't have to figure out ahead of time what you're going to need from that library. It's all there, okay? Also, because we're in this wonderful interactive Jupyter environment, it lets us understand what's in the libraries really well. So for example, later on, I'm using a function called display, right? So an obvious question is like, well, what is display? So you can just type the name of a function and press Shift-Enter. Remember, Shift-Enter is to run a cell, and it will tell you where it's from, right? So anytime you see a function you're not familiar with, you can find out where it's from. And then if you want to find out what it does, put a question mark at the start. Okay, and here you have the documentation. And then, particularly helpful for the FastAI library, so the FastAI library, I try to make as many functions as possible be like no more than about 5 lines of code. It's designed to be really easy to read, right? If you put a second question mark at the start, it shows you the source code of the function. Right, so all the documentation plus the source code. So you can see, like, nothing has to be mysterious. And we're going to be using, the other library we'll use a lot is scikit-learn, which is kind of implements a lot of machine learning stuff in Python. The scikit-learn source code is often pretty readable. And so very often, if I want to really understand something, I'll just go question mark, and the name of the scikit-learn function I'm typing, and I'll just go ahead and read the source code. As I say, the FastAI library in particular is designed to have source code that's very easy to read, and we're going to be reading it a lot. Okay. All right, so today we're going to be working on a Kaggle competition called Blue Book for Bulldozers. So the first thing we need is to get that data. So if you go Kaggle bulldozers, then you can find it. So Kaggle competitions allow you to download a real-world data set that a real problem that somebody's trying to solve, and solve it according to a specification that that actual person with that actual problem decided would be actually helpful to them. Right? So these are pretty authentic experiences for applied machine learning. Now, of course, you're missing all the bit that went before, which was why did this company, this startup, decide that predicting the auction sale price of bulldozers was important? Where did they get the data from? How did they clean the data? And so forth. Okay, and that's all important stuff as well. But the focus of this course is really on what happens next, which is like, how do you actually build the model? One of the great things about you working on Kaggle competitions, whether they be running now or whether they be old ones, is that you can submit yours to the leaderboard. Even old closed competitions, you can submit to the leaderboard and find out how would you have gone, right? And there's really no other way in the world of knowing whether you're competent at this kind of data in this kind of model than doing that, right? Because otherwise, if your accuracy is really bad, is it because this is just very hard, like it's just not possible, then the data is so noisy you can't do better? Or is it actually that it's an easy data set and you've made a mistake? And like, when you finish this course and apply this to your own projects, this is going to be something you're going to find very hard, and there isn't a simple solution to it, which is you're now using something that hasn't been on Kaggle, it's your own data set. Do you have a good enough answer or not? Okay, so we'll talk about that more during the course. And in the end, we just have to know that we have good, effective techniques for reliably building baseline models. Otherwise, yeah, there's really no way to know. There's no way other than creating a Kaggle competition or getting 100 top data scientists to work at your problem to really know what's possible. So Kaggle competitions are fantastic for learning. And as I've said many times, I've learned more from competing in Kaggle competitions than everything else I've done in my life. So to compete in a Kaggle competition, you need the data. Right? This one's an old competition, so it's not running now, but we can still access everything. So we first of all want to understand what the goal is. And I suggest that you read this later, but basically we're going to try and predict the sale price of heavy equipment. And one of the nice things about this competition is that if you're like me, you probably don't know very much about heavy industrial equipment auctions, right? I actually know more than I used to because my toddler loves building equipment. So we actually watch YouTube videos about front-end loaders and forklifts. But 2 months ago, I was a real layman. So one of the nice things is that machine learning should help us understand a data set, not just make predictions about it. So by picking an area which we're not familiar with, it's a good test of whether we can build an understanding, right? Because otherwise what can happen is that your intuition about the data can make it very difficult for you to be open-minded enough to see what does the data really say. It's easy enough to download the data to your computer. You just have to click on the data set. So here is train.zip and click download, right? And so you can go ahead and do that if you're running on your own computer right now. If you're running on AWS, it's a little bit harder, right? Because unless you're familiar with text mode browsers like eLinks or Lynx, it's quite tricky to get the data set to Kaggle. So a couple of options. One is you could download it to your computer and then SCP it to AWS. So SCP works just like SSH, but it copies data rather than logging in. I'll show you a trick though that I really like, and it relies on using Firefox. For some reason, Chrome doesn't work correctly with Kaggle for this. So if I go on Firefox to the website, eventually, and what we're going to do is we're going to use something called the JavaScript console. So every web browser comes with a set of tools for web developers to help them see what's going on. And you can hit, so we'll do it through here, developer, Control-Shift-I. Okay, so you can hit Control-Shift-I to bring up this web developer tools. And one of the tabs is network, okay? And so then if I click on train.zip and I click on download, okay, and I'm not even going to download it, I'm just going to say cancel. But you'll see down here, it's shown me all of the network connections that were just initiated, right? And so here's one which is downloading a zip file from storage.googleapis.com, blah, blah, blah. That's probably what I want. Right, that looks good. So what you can do is you can right click on that and say copy as curl. So curl is a Unix command like wget that downloads stuff. Right? So if I go copy as curl, that's going to create a command that has all of my cookies, headers, everything in it necessary to download this authenticated data set. So if I now go into my server, right? And if I paste that, you can see a really, really long curl command. One thing I notice is that at least recent versions have started adding this --2.0 thing to the command. That doesn't seem to work with all versions of curl. So something you might want to do is to, oopsie daisy, copy curl, is to pop that into an editor, find that to get rid of it, and then use that instead. Right. Now, one thing to be very careful about, by default, curl downloads the file and displays it in your terminal. So if I try to display this, it's going to display gigabytes of binary data in my terminal and crash it. Okay. So to say that I want to output it using some different file name, I always type -o for output file name, and then the name of the file, bulldozers dot, and make sure you give it a suitable extension. So in this case, the file was train.zip. Okay, so bulldozers.zip. And there it is. Okay, and so there it all is. So I could make directory bulldozers. And then I could move my zip file into there. Oops, wrong way around. Yes. Thank you. Okay, and then if you don't have unzip installed, you may need to sudo apt install unzip, or if you're on a Mac, that would be brew install unzip. If brew doesn't work, you haven't got homebrew installed, so make sure you install it, and then unzip. Okay, and so they're the basic steps. One nice thing is that if you're using Cressel, most of the data sets should already be pre-installed for you. So what I can do here is I can say open a new tab. Here's a cool trick. In Jupyter, you can actually say new terminal, and you can actually get a web-based terminal, right? And so you'll find on Cressel there's a /datasets folder, /datasets/Kaggle, /datasets/FastAI. Often the things you need are going to be in one of those places. Okay, so assuming that we don't have it already downloaded in Paper, actually Paperspace should have most of them as well, then we'd need to go to FastAI. Let's go into the courses, machine learning folder. And what I tend to do is I tend to put all of my data for a course into a folder called data. You'll find that if you try and, if you're using, well, we're using Git, right? You'll find that that doesn't get added to Git because it's in the Git ignore, right? So, so don't worry about creating the data folder. It's not going to screw anything up. So I generally make a folder called data, and then I tend to create folders for everything I need there. So in this case, I'll make the bulldozers, CD, and remember the last word of the last command is $! I'll go ahead and grab that curl command again. Okay, unzip bulldozers. There we go. Okay. So you can now see I generally have like anything that would change, that might change from person to person, I kind of put in a constant. So here I just define something called path, but if you've used the same path I just did, you should just be able to go ahead and run that. And let's go ahead and keep moving along. So we've now got all of our libraries imported, and we've set the path to the data. You can run shell commands from within Jupyter Notebook by using an exclamation mark. So if I want to check what's inside that path, I can go ls data/bulldozers. Okay, and you can see that works. Or you can even use Python variables. If you use a Python variable inside a Jupyter shell command, you have to put it in curlies. Okay? So that makes me feel good that my path is pointing at the right place. If you say ls curly capitals path and you get nothing at all, then you're pointing at the wrong spot. Yes? Let me do this query box. Yeah. And turn this up here.
Can you explain again what the curly brackets were for?
Yeah, so the curly brackets refer to the fact that I put an exclamation mark at the front, which means the rest of this is not a Python command, it's a bash command. And bash doesn't know about capital path because capital path is part of Python. So this is a special Jupyter thing which says expand this Python thing, please, before you pass it to the shell. Good question, thank you. So the goal here is to use the training set, which contains data through the end of 2011, to predict the sale price of bulldozers. And so the main thing to start with then is, of course, to look at the data. Now, the data is in CSV format, right? So one easy way to look at the data would be to use shell command head to look at the first few lines, head, bulldozers, and even tab completion works here. Jupyter does everything. Right, so here's the first 5 lines, okay? So there's like a bunch of column headers, and then there's a bunch of data. So that's pretty hard to look at. So what we want to do is take this and read it into a nice tabular format, okay? So does Terence put his glasses on mean I should make this bigger, or is it okay? Is this big enough font size for everybody? Okay. So this kind of data where you've got columns representing a wide range of different types of things, such as an identifier, a value, a currency, a date, a size. I refer to this as structured data. Now, I say I refer to this as structured data because, like, there have been many arguments in the machine learning community on Twitter about what is structured data. Weirdly enough, this is like the most important type of distinction is between data that looks like this and data like images where every column is of the same type. Like, that's the most important distinction in machine learning, yet we don't have standard accepted terms. So I'm going to use the terms structured and unstructured. But note that other people you talk to, particularly in NLP, people use structured to mean something totally different, right? So when I refer to structured data, I mean columns of data that can have varying different types of data in them. By far, the most important tool in Python for working with structured data is pandas. Pandas is so important that it's one of the few libraries that everybody uses the same abbreviation for it, which is PD. So you'll find that one of the things I've got here is from FastAI imports import star, right? The FastAI imports module has nothing but imports of a bunch of hopefully useful tools. So all of the code for FastAI is inside the FastAI directory inside the FastAI repo. And so you can have a look at imports. And you'll see it's just literally a list of imports. And you'll find there pandas as PD. And so everybody does this, right? So you'll see lots of people using pd dot something. They're always talking about pandas. So pandas lets us read a CSV file. And so when we read the CSV file, we just tell it the path to the CSV file, a list of any columns that contain dates, and I always add this low memory equals false that's going to actually make it read more of the file to decide what the types are. This here is something called a Python 3.6 format string. It's one of the coolest parts of Python 3.6. You've probably used lots of different ways in the past in Python of interpolating variables into your strings. Python 3.6 has a very simple way that you'll probably always want to use from now on. And it's you create a normal string, you type an F at the start, and then if I define a variable, then I can say hello, curly's, Python function. Okay. This is kind of confusing. These are not the same curlies that we saw earlier on in that ls command, right? That ls command is specific to Jupyter, and it interpolates Python code into shell code. These curlies are Python 3.6 format string curlies. They require an F at the start, so if I get rid of the F, it doesn't interpolate. Okay, so the F tells it to interpolate. And the cool thing is, inside that curlies, you can write any Python code you like, just about. So for example, name.upper, hello Jeremy. Okay, so I use this all the time. And it doesn't matter, because it's a format string, it doesn't matter if the thing was, I always forget my age, I think I'm 43. It doesn't matter if it's an integer, right? Normally if you like do string concatenation with integers, Python complains. No such problem here. Okay, so this is going to read path/train.csv into a thing called a data frame. Pandas data frames and R's data frames are kind of pretty similar. So if you've used R before, then you'll find that this is reasonably comfortable. So this file is 9.3 meg, and its size is 112 meg, and it has 400,000 rows in it. Okay, so it takes a moment to import it. but when it's done, we can type the name of the data frame, dfraw, and then use various methods on it. So for example, dfraw.tail will show us the last few rows of the data frame. By default, it's going to show the columns along the top and the rows down the side, but in this case there's a lot of columns, so I've just said .transpose to show it the other way around. I've created one extra function here, display all. Normally if you just type dfraw, if it's too big to show conveniently, it truncates it and puts like little ellipses in the middle. So the details don't matter, but this is just changing a couple of settings to say, even if it's got 1,000 rows and 1,000 columns, please still show the whole thing. Okay, so this is finished. I can actually show you that. So if I just type, this is really cool. In Jupyter Notebook, you can type a variable of almost any kind, a video, HTML, an image, whatever, and it'll generally figure out a way of displaying it for you. Okay, so in this case, it's a pandas data frame. It figures it out a way of displaying it for me. And so you can see here that by default, it's actually doesn't show me the whole thing. So, so here's the data set. We've got a few different rows. This is the last bit, the tail of it, right? Last few rows. This is the thing we want to predict, price, okay? And then all of the other, so we call this the dependent variable. The dependent variable is the price. And then we've got a whole bunch of things we could predict it with. And when I start with a data set, I tend, yes, Terence, can I give you this? Green box.
Hello, Jeremy.
Hi, Terence.
I've read in books that you should never look at the data because of the risk of overfit. Why do you start by looking at the data?
Yeah, so I was actually going to mention, I actually kind of don't. Like, I want to find out at least enough to know that I've like managed to import it okay, but I tend not to really study it at all at this point because I don't want to make too many assumptions about it. I would actually say most books say the opposite. Most books do a whole lot of EDA, exploratory data analysis, first.
Academic books.
Yeah, academic books.
Well, I mean, the academic books I've read say that's one of the biggest risks of overfitting. But the practical books say, let's do some EDA first.
Yeah, so the truth is kind of somewhere in between. And I generally try to do machine learning driven EDA, and that's what we're going to learn today. Okay. So the thing I do care about, though, is what's the purpose of the project? And for Kaggle projects, the purpose is very easy. We can just look and find out. There's always an evaluation section. How is it evaluated? And this is evaluated on root, mean, squared, log, error. So this means they're going to look at the difference between the log of our prediction of price and the log of the actual price, and then they're going to square it and add them up. Okay, so because they're going to be focusing on the difference of the logs, that means that we should focus on the logs as well. And this is pretty common, like for a price, generally you care not so much about did I miss by $10, but did I miss by 10%, right? So if it was $1 million thing and you're $100,000 off, or if it's a $10,000 thing and you're $1,000 off, often we would consider those equivalent scale issues. And so for this auction problem, the organizers are telling us they care about ratios more than differences, and so the log is the thing we care about. So the first thing I do is to take the log. Okay. Now NP is NumPy. I'm assuming that you have some familiarity with NumPy. If you don't, we've got a video called Deep Learning Workshop, which actually isn't just for deep learning, it's basically for this as well. And one of the parts there, which we've got a time-coded link to, is a quick introduction to NumPy. Okay, but basically NumPy lets us treat arrays, matrices, vectors, high-dimensional tensors as if they're Python variables, and we can do stuff like log to them, and it'll apply it to everything. NumPy and pandas work together very nicely. So in this case, dfraw.salePrice is pulling a column out of a pandas data frame, which gives us a pandas series. right? It shows us the sale prices and their indexes, right? And a series can be passed to a NumPy function, okay, which is pretty handy. And so you can see here, this is how I can replace a column with a new column. Pretty easy. So, okay, now that we've replaced sale price with its log, we can go ahead and try to create a random forest. What's a random forest? We'll find out in detail, but in brief, a random forest is a kind of universal machine learning technique. It's a way of predicting something that can be of any kind. It could be a category, like is it a dog or a cat, or it could be a continuous variable like price. It can predict it with columns of pretty much any kind, pixel data, zip codes, revenues, whatever. In general, it doesn't overfit. It can, and we'll learn to check whether it is, but it doesn't generally overfit too badly, and it's very, very easy to stop it from overfitting. You don't need, and we'll talk more about this, you don't need a separate validation set in general. It can tell you how well it generalizes, even if you only have one data set. It has few, if any, statistical assumptions. It doesn't assume that your data is normally distributed. It doesn't assume that the relationships are linear. It doesn't assume that you've specified the interactions. It requires very few pieces of feature engineering for many different types of situation. You don't have to take the log of the data. You don't have to multiply interactions together. So in other words, it's a great place to start. Right? If your first random forest does very little useful, then that's a sign that there might be problems with your data. Like it's designed to work pretty much first off. Can you please throw it at or towards this gentleman? Thank you.
What about curse of dimensionality when using random forests?
Yeah, great question. So there's this concept of curse of dimensionality. In fact, there's two concepts I'll touch on. Curse of dimensionality and the no free lunch theorem. These are two concepts you'll often hear a lot about. They're both largely meaningless and basically stupid. And yet, I would say maybe the majority of people in the field not only don't know that, but think the opposite. So it's well worth explaining. The curse of dimensionality is this idea that the more columns you have, it basically creates a space that's more and more empty. And there's this kind of fascinating mathematical idea, which is the more dimensions you have, the more all of the points sit on the edge of that space. Right? So if you've just got a single dimension where things are like random, then they're spread out all over. Right? Whereas if it's a square, then the probability that they're in the middle means that they can't have been on the edge of either dimension. So it's a little bit less likely that they're not on the edge. Each dimension you add, it becomes multiplicatively less likely that the point isn't on the edge of at least one dimension. Right? And so basically in high dimensions, everything sits on the edge. And what that means in theory is that the distance between points is much less meaningful. And so if we assume that somehow that matters, then it would suggest that when you've got lots and lots of columns and you just use them without being very careful to remove the ones you don't care about, that somehow things won't work. That turns out just not to be the case. It's not the case for a number of reasons. One is that the points still do have different distances away from each other. Just because they're on the edge, they still do vary in how far away they are from each other. And so this point is more similar to this point than it is to that point. So even things we'll learn about k-nearest neighbors actually work really well, really, really well in high dimensions, despite what the theoreticians claimed. And what really happened here was that in the 90s, theory totally took over machine learning. And so particularly there was this concept of these things called support vector machines that were theoretically very well justified, extremely easy to analyze mathematically, and you could like kind of prove things about them. And we kind of lost a decade of real practical development, in my opinion, and all these theories became very popular, like the curse of dimensionality. Nowadays, and a lot of theoreticians hate this, the world of machine learning has become very empirical, which is like which techniques actually work. And it turns out that in practice, building models on lots and lots of columns works really, really well. So yeah, the other thing to quickly mention is the no free lunch theorem. There's a mathematical theorem by that name that you will often hear about that claims that there is no type of model that works well for any kind of data set. Which is true, and is obviously true if you think about it. In the mathematical sense, any random data set, by definition, it's random, right? So there isn't going to be some way of looking at every possible random data set that's in some way more useful than any other approach. In the real world, we look at data which is not random. Mathematically, we'd say it sits on some lower dimensional manifold. It was created by some kind of causal structure, right? There are some relationships in there. So the truth is that we're not using random data sets. And so the truth is, in the real world, there are actually techniques that work much better than other techniques for nearly all of the data sets you look at. And nowadays there are empirical researchers who spend a lot of time studying this, which is which techniques work a lot of the time. And ensembles of decision trees, of which random forests are one, is perhaps the technique which most often comes up the top. And that is despite the fact that until the library that we're showing you today, FastAI, came along, there wasn't really any standard way to pre-process them properly and to properly set their parameters. So I think it's even more strong than that. So yeah, I think this is where the difference between theory and practice is huge. So when I try to create a random forest regressor, what is that? Random forest regressor. Okay, it's part of something called sklearn. sklearn is scikit-learn. It is by far the most popular and important package for machine learning in Python. It does nearly everything. It's not the best at nearly everything, but it's perfectly good at nearly everything. So like you might find in the next part of this course with your net, you're going to look at a different kind of decision tree ensemble called gradient boosting trees, where actually there's something called XGBoost, which is better than gradient boosting trees in scikit-learn. But it's pretty good at everything. So I'm really going to focus on scikit-learn. Random forest, you can do two kinds of things with a random forest. If I hit tab, oh, I haven't imported it. So let's go back to where we import. So you can hit tab in Jupyter Notebook to get tab completion for anything that's in your environment. And you'll see that there's also a random forest classifier. So in general, there's an important distinction between things which can predict continuous variables, and that's called regression, and therefore a method for doing that would be a regressor, and things that predict categorical variables, and that is called classification, and the things that do that are called classifiers. Okay? So in our case, we're trying to predict a continuous variable, price. So therefore we are doing regression, and therefore we need a regressor. A lot of people incorrectly use the word regression to refer to linear regression, okay, which is just not at all true or appropriate. Regression means a machine learning model that's trying to predict some kind of continuous outcome. It has a continuous dependent variable. So pretty much everything in scikit-learn has the same form. You first of all create an instance of an object for the machine learning model you want. You then call fit, passing in the independent variables, the things you're going to use to predict, and the dependent variable, the thing that you want to predict. So in our case, the dependent variable is the data frame's sale price column. And so the thing we want to use to predict is everything except that. In pandas, the drop method returns a new data frame with a list of columns removed, right? Well, a list of rows or columns removed. So axis equals 1 means remove columns. So this here is the data frame containing everything except for sale price. Okay? Can I have the box, or can you throw it to Ernest directly? Yes, sure.
So if you want to remove multiple columns, you just pass in a list of strings with the column names?
Let's find out. So to find out, I could hit Shift-Tab, and that will bring up a quick inspection of the parameters. In this case, it doesn't quite tell me what I want. So if I hit Shift-Tab twice, it gives me a bit more information. Yes, and that tells me it's a single label or list-like. List-like means like anything you can index. In Python, there's lots of things. By the way, if I hit 3 times, it will give me a whole little window at the bottom. Okay, so that was Shift-Tab. Another way of doing that, of course, which we learned, would be $df raw dot drop. Okay? Sorry, question mark would be the source code for it. Or a single question mark is the documentation. So I think that trick of like tab complete, shift tab parameters, question mark and double question mark for the docs and the source code. Like, if you know nothing else about using Python libraries, know that, because now you know how to find out everything else. Okay? So, we try to run it, and it doesn't work. Okay, so why didn't it work? So, anytime you get a stack trace like this, so an error, the trick is to go to the bottom, because the bottom tells you what went wrong. Above it, it tells you all of the functions that called other function could cause other functions to get there. Could not convert string to float, conventional. So there was a column name, there was a value, rather, inside my data set, conventional, the word conventional, and it didn't know how to create a model using that string. Now that's true. We have to pass numbers to most machine learning models, and certainly to random forests. So step 1 is to convert everything into numbers. So our data set contains both continuous variables, so numbers where the meaning is numeric, like price, and it contains categorical variables, which could either be numbers where the meaning is not continuous, like zip code, or it could be a string, like large, small, and medium. Okay, so categorical and continuous variables. We want to basically get to a point where we have a data set where we can use all of these variables. So they have to all be numeric, and they have to be usable in some way. So one issue is that we've got something called sale date, which you might remember right at the top, we told it that that's a date, so it's been parsed as a date. And so you can see here it's data type, D type, very important thing. Data type is date time 64-bit. So that's not a number, right? And this is actually where we need to do our first piece of feature engineering, right? Inside a date is a lot of interesting stuff. All right, so since you've got the catch box, can you tell me what are some of the interesting bits of information inside a date?
Well, you can see like a time series pattern, I guess, because the time.
That's true. I didn't express very well. What are some columns that we could pull out of this?
Oh, year, month.
Year, month.
And then the date.
The date as in, like, tell me it needs to be a number. Year, month.
Quarter.
Quarter. You want to pass it to your right and get some more or behind you? Just pass it to your right. Here you go. You got some more columns for us?
Day of the month.
Day of month. Yeah. Keep going to the right.
Day of week.
Day of week. Yeah.
Anything else? The week.
Week of year.
Yeah, week of year.
Yeah. Okay. I'll give you a few more, like that you might want to think about. Would be like, is it a holiday? Is it a weekend? Was it raining that day? Was there a sports event that day? Like, it depends a bit on what you're doing, right? So, like, if you're predicting soda sales in Soma, you would probably want to know, was there a San Francisco Giants ball game on that day, right? So, like, what's in a date is one of the most important pieces of feature engineering you can do. And no machine learning algorithm can tell you whether the Giants were playing that day and that it was important, right? So this is where you need to do feature engineering. So I do as many things automatically as I can for you, right? So here I've got something called add date part. What is that? It's something inside fastai.structured. Okay. And what is it? Well, let's read the source code. Here it is. So you'll find most of my functions are less than half a page of code. Right? So here is something it's going to, so often rather than having docs, I'm going to try to add docs over time, but they're designed that you can understand them by reading the code. So we're passing in a data frame and the name of some field, okay, which in this case was sale date. And so in this case, we can't go df.fieldName because that would actually find a field called field name literally. So df square bracket field name is how we grab a column where that column name is stored in this variable. Okay, so we've now got the field itself, the series. Okay. And so what we're going to do is we're going to go through all of these different strings, right? And this is a piece of Python which actually looks inside an object and finds an attribute with that name. So this is going to go through, and you can Google for Python get attribute. It's a cool little advanced technique. But this is going to go through and it's going to find, for this field, it's going to find its year attribute. Now, Pandas has got this interesting idea, which is if I actually look inside, let's go field equals, this is the kind of experiment I want you to do, right? Play around, sale date. Okay, so I've now got that in a field object, and so I can go field, right? And I can go field dot tab, right? And let's see, is year in there? Oh, it's not. Okay, why not? Well, that's because year is only going to apply to Pandas series that are date time objects. So what Pandas does is it splits out different methods inside attributes that are specific to what they are. So date time objects will have a DT attribute defined, and that is where you'll find all the date time specific stuff. So what I went through was I went through all of these and picked out all of the ones that could ever be interesting for any reason, right? And this is like the opposite of the curse of dimensionality. It's like, if there is any column or any variant of that column that could ever be interesting at all, add that to your data set, add every variation of it you can think of. There's no harm in adding more columns, nearly all the time, right? So in this case, we're going to go ahead and add all of these different attributes. And so for every one, I'm going to create a new field that's going to be called the name of your field with the word date removed, so it'll be sale, and then the name of the attribute. So we're going to get a sale year, sale month, sale week, sale day, etc., etc. Okay? And then at the very end, I'm going to remove the original field, right? Because remember, we can't use sale date directly because it's not a number. Okay? Can we pass that?
So you're saying this only worked because it was a date type? Did you make it a date type or was it already saved as one in the original?
Yeah, it's already a date type. And the reason it was a date type is because when we imported it, we said parse dates equals and told Pandas it's a date type. So as long as it looks date-ish, and we tell it to parse it as a date, it'll turn it into a date type.
Is there a way to do that so it would just look through all the columns and say, like, if it looks like a date, make it a date? Or do you have to know which one?
I think there might be, but for some reason it wasn't ideal. Like maybe it took lots of time or it didn't always work, or for some reason I had to list it here. I would suggest checking out the docs to pandas.readcsv, and maybe on the forum you can tell us what you find, because I can't remember offhand. Good telephoning.
So how about the time zone? Like, how can we get the time zone from the...
Let's do that one on the same forum thread that Svana creates, because I think it's a reasonably advanced question. But generally speaking, the time zone in a properly formatted date will be included in the string, and it should format it. It should pull it out correctly and turn it into a universal time zone. So generally speaking, it should handle it for you.
So I've noticed you, for indexing a column, you interchangeably use the f dot column and the df brackets public column. Is there any consideration between them?
The square brackets one is safer, particularly if you're assigning to a column. If it didn't already exist, you need to use the square brackets format, otherwise you'll get weird errors.
Okay.
So the square brackets format is safer. The dot version saves me like a couple of keystrokes, so I probably use it more than I should. In this particular case, because I wanted to grab something that had field name had something inside it, wasn't the name itself, I have to use square brackets. So square brackets is going to be your safe bet if in doubt.
Got it.
So after I run that, you'll notice that dfraw.columns gives me a list of all of the columns just as strings, and at the end, there they all are. Right? So it's removed sale date and it's added all those. So that's not quite enough. The other problem is that we've got a whole bunch of strings in there, right? So you can just leave that there. Do you want to pass it back? Pass it back. Thanks. Sorry. So here's like low, high, medium. Thank you. Right. So pandas actually has a concept of a category data type, but by default it doesn't turn anything into a category for you. So I've created something called train cats, which creates categorical variables for everything that's a string. Okay, and so what that's going to do is behind the scenes, it's going to create a column that's actually a number, right? It's an integer, and it's going to store a mapping from the integers to the strings. Okay. The reason it's train cats is that you use this for the training set. More advanced usage is that when we get to looking at the test and validation sets, this is a really important idea. In fact, Terence came to me the other day and he said, my model's not working. Why not? And he figured it out for himself. It turned out the reason why was because the mappings he was using from string to number in the training set were different to the mappings he was using from string to number in the test set. So therefore, in the training set, high might have been 3, but in the test set, it might have been 2. So the two were totally different, and so the model was basically non-predictive. Okay, so I have another function called apply categories, where you can pass in your existing training set, and it'll use the same mappings to make sure your test set or validation set uses the same mappings. Okay, so when I go train cats, it's actually not going to make the data frame look different at all. Behind the scenes, it's going to turn them all into numbers. We finish at 12, 11:50. Let's see how we go. I'll try and finish on time. So you'll see now, remember I mentioned there was this .dt attribute that gives you access to everything assuming it's a date time about the date time. There's a .cat attribute that gives you access to things assuming something's a category, right? And so usage band was a string, and so now that I've run train cats, it's turned it into a category. So I can go dfraw.usageband.cat, right? And there's a whole bunch of other things we've got there, okay? So one of the things we've got there is .categories, and you can see here is the list. Now, one of the things you might notice is that this list is in a bit of a weird order: high, low, medium. The truth is, it doesn't matter too much. But what's going to happen when we use the random forest is it's actually going to, this is going to be 0, this is going to be 1, this is going to be 2, and we're going to be creating decision trees. And so we're going to have a decision tree that can split things at a single point. So it would either be high versus low and medium, or medium versus high and low. And that would be kind of weird, right? It actually turns out not to work too badly, but it'll work a little bit better if you have these in sensible orders. Okay, so if you want to reorder a category, then you can just go cat.setCategories and pass in the order you want and tell it it's ordered. And almost every pandas method has an in-place parameter, which rather than returning a new data frame, it's going to change that data frame. Okay, so I'm not going to do that. Like, I didn't check that carefully for categories that should be ordered, but this seems like a pretty obvious one.
Can you reiterate that issue? I didn't understand what the problem was.
Sure. So the usage band column is actually going to be this is actually what our random forest is going to see. These numbers, 1, 0, 2, 1, okay? And they map to the position in this array. And as we're going to learn shortly, a random forest consists of a bunch of trees that's going to make a single split. And the single split is going to be either greater than or less than 1 or greater than or less than 2, right? So we could split it into high versus low and medium, which that semantically makes sense. It's like, is it big? Or we could split it into medium versus high and low, which doesn't make much sense, right? So in practice, the decision tree could then make a second split to say like medium versus high and low, and then within the high and low into high and low. But by putting it in a sensible order, if it wants to split out low, it can do it in one decision rather than two. And we'll be learning more about this shortly. Honestly, it's not a big deal, but I just wanted to mention it's there. And it's also good to know that people, when they talk about like different types of categorical variable, specifically you need to know there's a kind of categorical variable called ordinal. And an ordinal categorical variable is one that has some kind of order, like high, medium, and low, right? And random forests aren't terribly sensitive to that fact, but it's worth knowing it's there and trying it out.
Still ordering wouldn't help our maximum depth parameter.
That's what I'm saying. It helps a little bit, right? It means you can get there with one decision rather than two.
I noticed there's a -1 in that list of categories. Is that like an NA or?
Yeah, exactly. So for free, we get a -1, which refers to missing. And one of the things we're going to do is we're going to actually add one. Can somebody pass it back to Paul? Is we're going to add one to our codes. Maybe in two goes. Let people know it's coming. Yeah, so we're going to add one to all of our codes to make missing 0 later on. But
so for the these categories, you're basically mapping strings to different integers, right?
That's right.
So there's one built-in function in Python is called get dummies. So basically for high, medium, low, there's like 3 columns. So
yeah,
high, 0, 1.
We're going to get to that.
So what is the difference between these?
Yeah, so get dummies, which we'll get to in a moment, is going to create 3 separate columns. 1s and 0s for high, 1s and 0s for medium, 1s and 0s for low, whereas this one creates a single column with an integer, 0, 1, or 2.
Yeah, so what's the difference? Like how should we choose?
We're going to get to that one shortly. Yep. Did you have a question too, Paul, or are you just pointing out? Okay. Okay, so at this point, as long as we always make sure we use .cat.codes, the thing with the numbers in, we're basically done. All of our strings have been turned into numbers. Our dates have been turned into a bunch of numeric columns, and everything else is already a number. Okay. The only other main thing we have to do is notice that we have lots of missing values. So here is dfraw.isNull. That's going to return true or false, depending on whether something is empty. .sum is going to add up how many are empty for each series. And then I'm going to sort them and divide by the size of the data set. So here we have some things which have like quite high percentages of nulls. So missing values, we call them in display all. Isn't that what I called it? Or maybe I didn't run it. There we go. Okay, so we're going to get to that in a moment, but I will point something out, which is reading the CSV took a minute or so. The processing took another 10 seconds or so. From time to time, when I've done a little bit of work I don't want to wait for again, I will tend to save where I'm at. So here I'm going to save it. And I'm going to save it in a format called feather format. This is very, very new, right? But what this is going to do is it's going to save it to disk in exactly the same basic format that it's actually in RAM. This is by far the fastest way to save something and the fastest way to read it back, right? So most of the folks you deal with, unless they're on the cutting edge, won't be familiar with this format. So this would be something you can teach them about. It's becoming the standard, right? It's actually becoming something that's going to be used not just in pandas, but in Java, in Spark, in lots of like things for like communicating across computers, because it's incredibly fast. And it's actually co-designed by the guy that made Panthers, by Wes McKinney. So we can just go dfraw.toFeather and pass in some name. I tend to have a folder called temp for all of my, like, as I'm going along stuff. And so when you go os.makeDirs, you can pass in any path here you like. It won't complain if it's already there, because I've got exists OK equals true. If there are some subdirectories, it'll create them for you. So this is a super handy little function. Okay, so it's not installed. So because I'm using Cressel for the first time, it's complaining about that. So if you get a message that something's not installed, if you're using Anaconda, you can conda install. Cressel actually doesn't use Anaconda, it uses pip. And so we wait for that to go along. Okay, and so now if I run it, and so sometimes you may find you actually have to restart Jupyter. So I won't do that now because we're nearly out of time. So if you restart Jupyter, you'll be able to keep moving along. So from now on, you don't have to rerun all the stuff above. You could just say pd.readFeather, and we've got our data frame back. So the last step we're going to do is to actually replace the strings with their numeric codes. And we're going to pull out the dependent variable, sale price, into a separate variable. And we're going to also handle missing continuous values. And so how are we going to do that? So you'll see here we've got a function called procdf. What is that? Procdf. So it's inside fastai.structured again. And here it is. So quite a lot of the functions have a few additional parameters that you can provide, and we'll talk about them later. But basically, we're providing the data frame to process and the name of the dependent variable, the y field name. Okay, and so all it's going to do is it's going to make a copy of the data frame. It's going to grab the y value. It's going to drop the dependent variable from the original. And then it's going to fix missing. So how do we fix missing? So what we do to fix missing is pretty simple. If it's numeric, then we fix it by basically saying, let's first of all check that it does have some missing. Right? So if it does have some missing values, so in other words, the isNull.sum is non-zero, then we're going to create a new column called, with the same name as the original, plus underscore NA, and it's going to be a Boolean column with a 1 anytime that was missing, and a 0 anytime it wasn't. And we're going to talk about this again next week, but this is, I'll give you the quick version. Having done that, we're then going to replace the NAs, the missing, with the median. Okay, so anywhere that used to be missing will be replaced with the median, and we'll add a new column to tell us which ones were missing. We only do that for numeric. We don't need it for categories because Pandas handles categorical variables automatically by setting them to -1. So what we're going to do is, if it's not numeric and it's a categorical type, we'll talk about the maximum number of categories later, but let's assume this is always true. So if it's not a numeric type, we're going to replace the column with its codes, the integers. Okay, +1, right? So by default, Pandas uses -1 for missing. So now 0 will be missing, and 1, 2, 3, 4 will be all the other categories. So we're going to talk about dummies later on in the course, but basically, optionally, you can say that, if you already know about dummy values, there are columns with a small number of possible values you can turn into dummies instead of numericalizing them, but we're not going to do that for now. Okay, so for now, all we're doing is we're using the categorical codes +1, replacing missing values with the median, adding an additional column telling us which ones were replaced, and removing the dependent variable. So that's what proc df does. It runs very quickly. Okay, so you'll see now sale price is no longer here. Okay, we've now got a whole new variable called y that contains sale price. You'll see we've got a couple of extra blah underscore nas at the end. Okay, and if I look at that, everything is a number. Okay, these booleans are treated as numbers. They're just treated as 0 or 1. They're just displayed as false and true. So you can see here, is it the end of a month? Is it the start of a month? Is it the end of a quarter? It's kind of funny, right? Because we've got things like a model ID, which presumably is some, like, I don't know, it could be a serial number, or it could be like the model identifier that's created by the factory or something. We've got like a data source ID. Like some of these are numbers, but they're not continuous. It turns out actually random forests work fine with those. And we'll talk about why and how and a lot about that in detail. But for now, all you need to know is no problem. Okay, so as long as this is all numbers, which it now is, we can now go ahead and create a random forest. So m.randomForest regressor. Random forests are trivially parallelizable. So what that means is that if you've got more than one CPU, which everybody will basically on their computers at home, and if you've got a T2.medium or bigger at AWS, you've got multiple CPUs. Trivially parallelizable means that it will split up the data across your different CPUs and basically linearly scale, right? So the more CPUs you have, pretty much it will divide the time it takes by that number. Not exactly, but roughly. So n jobs equals -1 tells the random forest regressor to create a separate job, so a separate process basically, for each CPU you have. So that's pretty much what you want all the time. Fit the model using this new data frame we created, using that y value we pulled out, and then get the score. Okay, the score is going to be the R squared. We'll define that next week. Hopefully some of you already know about the R squared. 1 is very good, 0 is very bad. So as you can see, we've immediately got a very high score. Okay, so that looks great, but what we'll talk about next week a lot more is that it's not quite great, because maybe we had data that had points that looked like this, and we fitted a line that looks like this, when actually we wanted one that looks like that. Okay? The only way to know whether we've actually done a good job is by having some other data set that we didn't use to train the model. Now we're going to learn about some ways with random forests we can kind of get away without even having that other data set. But for now, what we're going to do is we're going to split into 12,000 rows, which we're going to put in a separate data set called the validation set, versus the training set's going to contain everything else, right? And our data set is going to be sorted by date, and so that means that the most recent 12,000 rows are going to be our validation set. Again, we'll talk more about this next week. It's a really important idea, but for now, we can just recognize that if we do that and run it, I've created a little thing called print score, and it's going to print out the root mean squared error between the predictions and actuals for the training set, for the validation set, the R squared for the training set, and the validation set. And you'll see that actually the R squared for the training was 0.98, but for the validation was 0.89. Okay? Then the RMSE, and remember this is on the logs, was 0.09 for the training set, 0.25 for the validation set. Now, if you actually go to Kaggle and go to the leaderboard, in fact, let's do it right now. It's got private and public. I'll click on public leaderboard, and we can go down and find out where is 0.25. So there are 475 teams. And generally speaking, if you're in the top half of a Kaggle competition, you're doing pretty well. So 0.25, here we are, 0.25. What was it exactly? 0.25, 0.2507. Yeah, about 110th. So we're about in the top 25%. So the idea, like, this is pretty cool, right? With no thinking at all, using the defaults of everything, we're in the top 25% of a Kaggle competition. So, like, random forests are insanely powerful, and this totally standardized process is insanely good for like any data set. So we're going to wrap up, but what I'm going to ask you to do for Tuesday is like take as many Kaggle competitions as you can, whether they be running now or old ones or data sets that you're interested in for your hobbies or work, and please try it, right? Try this process. And if it doesn't work, you know, tell us on the forum. Here's the data set I'm using, here's where I got it from, here's like the stack trace of where I got an error, or here's like, you know, if you use my print score function or something like it, like, you know, show us what the training versus test set looks like. We'll try and figure it out, right? But what I'm hoping we'll find is that all of you will be pleasantly surprised that with the, you know, hour or two of information you got today, you can already get better models than most of the very serious practicing data scientists that compete in Kaggle competitions. Okay? Great. Good luck, and I'll see you on the forums. Oh, one more thing. Friday, the other class said a lot of them had class during my office hours. So if I made them 1 till 3 instead of 2 till 4 on Fridays, is that okay? Seminar, oh, damn it. Okay, I have to find a whole other time. All right. I will talk to somebody who actually knows what they're doing, unlike me, about finding office hours. Thank you. So from here, the next 2 or 3 lessons, we're going to be really diving deep into random forests. So far, all we've learned is there's a thing called random forests. For some particular data sets, they seem to work really, really well without too much trouble. But we don't really know yet, like, well, how do they actually work? What do we do if they don't work properly? What are their pros and cons? What can we tune, and so forth? So we're going to look at all that. And then after that, we're going to look at how do we interpret the results of random forests to get not just predictions, but to actually deeply understand our data in a model-driven way. So that's where we're going to go from here. So let's just review where we're up to. So we learned that there's this library called FastAI, and the FastAI library is basically, it's a highly opinionated library, which is to say, we've spent a lot of time researching what are the best techniques to get like state-of-the-art results, and then we take those techniques and package them into pieces of code so that you can use the state-of-the-art results yourself. And so where possible, we wrap or provide things on top of existing code. And so in particular, for the kind of structured data analysis we're doing, scikit-learn has a lot of really great code. So most of the stuff that we're showing you from FastAI is stuff to help us get stuff into scikit-learn and then interpret stuff out from scikit-learn. The FastAI library, the way it works in our environment here is that we've got our notebooks are inside FastAI repo /courses and then /ML1 and DL1. And then inside there, there's a symlink to the parent of the parent FastAI. So this is a symlink to a directory containing a bunch of modules. So if you want to use the FastAI library in your own code, there's a number of things you can do. One is to put your notebooks or scripts in the same directory as ML1 or DL1, where there's already this symlink, and just import it just like I do. You could copy this directory, /FastAI, into somewhere else and use it, or you could symlink it, just like I have, from here to wherever you want to use it. Right? So notice, it's mildly confusing. There's a GitHub repo called FastAI, and inside the GitHub repo called FastAI, which looks like this, there is a folder called FastAI. Okay, and so the FastAI folder in the FastAI repo contains the FastAI library. And it's that library, when we go from fastai.imports import star, then that's looking inside the fastai folder for a file called imports.py and importing everything from that. Okay? Yes, Danielle. Nice catch.
And just like as a clarifying question for the symlink, it's just the ln thing you talked about last class. That's just the ln thing that you talked about last class?
Yeah, so a symlink is something you can create by typing ln minus s and then the path to the source, which in this case would be ... fastai. It could be relative or it could be absolute, and then the name of the destination. If you just put the current directory as a destination, it'll use the same name as it comes from. Like a alias on the Mac or a shortcut on Windows. We can hold on to it.
And when you do the import sys,
can I just hang on? Yeah, go again.
Import sys and then append that relative link that also creates the symlink in workbook 2. Was the
I don't think I've created a symlink anywhere in the workbooks. The symlink actually lives inside the GitHub repo.
Okay.
I created some symlinks in the deep learning notebook to some data. Okay. That was different, yeah.
At the top of Tim Lee's workbook from the last class, there was import sys, then append the fastai.
Oh, yeah, don't do that, probably.
Don't do
that. I mean, you can, but I think this is better. Like this way, you can go from fastai imports, and regardless of kind of how you got it there, it's going to work.
Okay.
You know. Great. Okay, so then we had all of our data for Blue Books for Bulldozers competition in data/bulldozers, and here it is, right? So we were able to read that CSV file. The only thing we really had to do was to say which columns were dates, and having done that, we were able to take a look at a few of the examples of the rows of the data. And so we also noted that it's very important to deeply understand the evaluation metric for this project. And so for Kaggle, they tell you what the evaluation metric is. And in this case, it was the root mean squared log error. So that is the sum of the actuals minus the predictions, right? But it's the log of the actuals minus the log of the predictions squared, right? So if we replace actuals with log actuals and replace predictions with log predictions, then it's just the same as root mean squared error. So that's what we did, was we replaced sale price with log of sale price. And so now, if we optimize for root mean squared error, we're actually optimizing for the root mean squared error of the logs. Okay? So then we learnt that we need all of our columns to be numbers. And so the first way we did that was to take the date column and remove it, and instead replace it with a whole bunch of different columns. Such as, is that date the start of a quarter? Is it the end of a year? How many days are elapsed since January the 1st, 1970? What's the year? What's the month? What's the day of week? And so forth. Okay, so they're all numbers. Then we learnt that we can use train_cats to replace all of the strings with categories. Now when you do that, it doesn't look like you've done anything different. They still look like strings, right? But if you actually take a deeper look, you'll see that the data type now is not string but category. And category is a pandas class where you can then go .cat dot and find a whole bunch of different attributes, such as cat.categories to find a list of all of the possible categories. And this says high is going to become 0, low will become 1, medium will become 2. So we can then get codes to actually get the numbers. So then what we need to do to actually use this data set to turn it into numbers is take every categorical column and replace it with cat.codes. And so we did that using procdf. Okay. So how do I get the source code for procdf? Question mark. Okay. All right, so if I scroll down, I go through each column and I numericalize it. Okay, that's actually the one I want. So I'm going to now have to look up numericalize. So tab to complete it. If it's not numeric, then replace the data frames field with that columns.cat.codes plus 1, because otherwise unknown is -1. We want unknown to be 0. Okay? So that's how we turn the strings into numbers. Right? They get replaced with a unique, basically arbitrary index. It's actually based on the alphabetical order of the feature names. The other thing procdf did, remember, was continuous columns that had missing values. The missing got replaced with the median, and we added an additional column called column name _ NA, which is a Boolean column, told you if that particular item was missing or not. So once we did that, we were able to call random forest regressor.fit and get the .score, and it turns out we have an R² of 0.98. Can anybody tell me what an R² is? Melissa, you want to tell me?
You know, it's Marsha.
Okay.
Marsha.
So R² essentially shows how much variance is explained by the model. Mm-hmm. This is the this is the relation of this is SSR, which is like trying to remember the exact formula, but like
I mean roughly, intuitively.
Yeah, intuitively, it's how much the model explains how much it accounts for the variance in the data.
Okay, good. So let's talk about the formula. And so with formulas, the idea is not to learn the formula and remember it, but to learn what the formula does and understand it, right? So here's the formula. It's 1 minus something divided by something else. So what's the something else on the bottom? SS tot. Okay, so what this is saying is we've got some actual data, some yi's, right? We've got some actual data. 3, 2, 4, 1. Okay? And then we've got some average. Okay, so our top bit, this SS tot, is the sum of each of these minus that. So in other words, it's telling us how much does this data vary. But perhaps more interestingly is, remember when we talked about, like, last week, what's the simplest non-stupid model you could come up with? And I think the simplest non-stupid model we came up with was create a column of the mean. Just copy the mean a bunch of times and submit that to Kaggle. If you did that, then your root mean squared error would be this. So this is the root mean squared error of the most naive, non-stupid model, where the model is just predict the mean. On the top, we have SSRes, which is here, which is that we're now going to add a column of predictions. Okay, and so now what we do is, rather than taking the yi minus y mean, we're going to take yi minus fi, right? And so now, instead of saying what's the root mean squared error of our naive model, we're saying what's the root mean squared error of the actual model that we're interested in. And then we take the ratio. So in other words, if we actually were exactly as effective as just predicting the mean, then this would be, top and bottom would be the same. That would be 1. 1 minus 1 would be 0. If we were perfect, so fi minus yi was always 0, then that's 0 divided by something. 1 minus that is 1. Okay, so what is the possible range of values of r squared? Okay, I heard a lot of 0 to 1. Does anybody want to give me an alternative?
Negative 1 to 1.
Negative 1 to 1?
Anything less than 1.
Huh?
Anything less than 1. Or
Anything less than 1. There's the right answer. Let's find out why. Can we have the box? Okay, so why is it any number less than 1?
Because you can make a model basically as crappy as you want, and just like as like big errors as you want, and you're just subtracting from 1 in the formula. So.
Exactly. So interestingly, I was talking to our computer science professor, Terence, this morning, who was talking to a statistics professor who told him that the possible range of values was r squared was 0 to 1. And I said, that is totally not true. If you predict infinity for every column, for every row, then you're going to have infinity for every residual, and so you're going to have 1 minus infinity. Okay, so the possible range of values is less than 1. That's all we know. And this will happen. You will get negative values sometimes in your r squared, and when that happens, it's not a mistake. It's not like a bug. It means your model is worse than predicting the mean. Okay, which suggests it's not great. So that's r squared. It's not necessarily what you're actually trying to optimize, right? But it's the nice thing about it is that it's a number that you can use kind of for every model. And so you can kind of start to try to get a feel of like, what does 0.8 look like? What does 0.9 look like? So like something I find interesting is to like create some different synthetic data sets, just two dimensions, with kind of different amounts of random noise, and like see what they look like on a scatter plot and see what their r squared are, just to kind of get a feel for like, what is an r squared? You know, is an r squared of 0.9 close or not? What about 0.7, close or not? Okay, so I think r squared is a useful number to have a familiarity with, and you don't need to remember the formula if you remember the meaning, which is what's the ratio between how good your model is, root mean squared error, versus how good is the naive mean model, root squared error. Okay, in our case, 0.98, it's saying it's a very good model. However, it might be a very good model because it looks like this, right? And this would be called overfitting. So we may well have created a model which is very good at running through the points that we gave it, but it's not going to be very good at running through points that we didn't give it. So that's why we always want to have a validation set. Creating your validation set is the most important thing that I think you need to do when you're doing a machine learning project, at least in terms of in the actual modeling part. Because what you need to do is come up with a data set where the score of your model on that data set is going to be representative of how well your model is going to do in the real world, like in Kaggle on the leaderboard or off Kaggle, like when you actually use it in production. I very, very, very often hear people in industry say, I don't trust machine learning. I tried modeling once. It looked great. We put it in production. It didn't work. Now, whose fault is that? Right? That means their validation set was not representative. Right? So here's a very simple thing, which generally speaking, Kaggle is pretty good about doing. If your data has a time piece in it, right, as happens in Blue Book for Bulldozers. In Blue Book for Bulldozers, we're talking about the sale price of a piece of industrial equipment on a particular date. So the startup doing this competition wanted to create a model that wouldn't predict last February's prices, but would predict next month's prices. So what they did was they gave us data representing a particular date range in the training set, and then the test set represented a future set of dates that wasn't represented in the training set. Right? So that's pretty good, right? That means that if we're doing well on this model, we've built something which can actually predict the future, or at least it could predict the future then, assuming things haven't changed dramatically. So that's the test set we have. So we need to create a validation set that has the same properties. So the test set had 12,000 rows in. So let's create a validation set that has 12,000 rows, right? And then let's split the data set into the first n minus 12,000 rows for the training set and the last 12,000 rows for the validation set. And so we've now got something which hopefully looks like Kaggle's test set, close enough that when we actually try and use this validation set, we're going to get some reasonably accurate scores. And the reason we want this is because on Kaggle, you can only submit so many times. And if you submit too often, you'll end up overfitting to the leaderboard anyway. And in real life, you actually want to build a model that's going to work in real life. Did you have a question? Can we have the green box? Thank you.
Can you explain the difference between a validation set and a test set?
Absolutely. So what we're going to learn today is how to set, one of the things we'll learn is how to set hyperparameters. Hyperparameters are like tuning parameters that are going to change how your model behaves. Now, if you just have one holdout set, so one set of data that you're not using to train with, and we use that to decide which set of hyperparameters to use, if we try 1,000 different sets of hyperparameters, we may end up overfitting to that holdout set. That is to say, we'll find something which only accidentally worked. So what we actually want to do is we want to have a second holdout set where we can say, okay, I'm finished. Okay, I've done the best I can. And now just once, right at the end, I'm going to see whether it works. And so this is something which almost nobody in industry does correctly. You really actually need to remove that holdout set, and that's called the test set. Remove it from the data, give it to somebody else, and tell them, do not let me look at this data until I promise you I'm finished. Like, it's so hard otherwise not to look at it. And for example, in the world of psychology and sociology, you might have heard about this replication crisis. And this is basically because people in these fields have accidentally, or intentionally maybe, been p-hacking, which means they've been basically trying lots of different variations until they find something that works. And then it turns out when they try to replicate it, in other words, it's like somebody creates a test set. Somebody says, okay, this study which shows, you know, the impact of whether you eat marshmallows on your tenacity later in life, I'm going to rerun it. And like over half the time, they're finding the effect turns out not to exist. So that's why we want to have a test set. Can you give that next door? Yeah.
So for handling categorical data, you converted those to numerics, to numbers, ordered numbers. I've seen a lot of models where we convert categorical data into different columns using one hot encoding.
Yes.
So which approach to use in which model?
Yeah, we're going to tackle that today. Yeah, it's a great question. Okay, So I'm splitting my my data into validation and training sets, and so you can see now that my validation set is 12,000 by 66, whereas my training set is 389,000 by 66. Okay, so we're going to use this set of data to train a model, and this set of data to see how well it's working. So when we then tried that last week, we found out, just a moment, we found out that our model, which had 0.982 R squared on the training set, only had 0.887 on the validation set, which makes us think that we're overfitting quite badly. But it turned out it wasn't too badly, because the root mean squared error on the logs of the prices actually would have put us in the top 25% of the competition anyway. So even although we're overfitting, it wasn't the end of the world. Could you pass the microphone to Marsha, please?
In terms of dividing the set into training and validation, it seems like you simply take the first and train observations of the data set,
yes,
and set them aside. Why don't you randomly pick up the observations?
Because if I did that, I wouldn't be replicating the test set. So Kaggle has a test set that when you actually look at the dates in the test set, they are a set of dates that are more recent than any date in the training set. So if we used a validation set that was a random sample, that is much easier, because we're predicting auctions, like what's the value of this piece of industrial equipment on this day, when we actually already have some observations from that day. So in general, anytime you're building a model that has a time element, you want your test set to be a separate time period, and therefore you really need your validation set to be a separate time period as well. And in this case, the data was already sorted, so that's why this works. Okay?
Okay, thanks.
We've got one more question over there.
Forgot this time series.
Sure.
So let's say we have our test, the training set where we train the data, and then we have the validation set against which we are trying to find the R square. In case our R square turns out to be really bad, we would want to tune our parameters and run it again.
Yes.
So wouldn't that be eventually overfitting on the overall training set?
Yeah, so actually that's the issue. So that would eventually have the possibility of overfitting on the validation set, and then when we try it on the test set or we submit it to Kaggle, it turns out not to be very good. And this happens in Kaggle competitions all the time. Kaggle actually has a fourth data set, which is called the private leaderboard set. And every time you submit to Kaggle, you actually only get feedback on how well it does on something called the public leaderboard set, and you don't know which rows they are. And at the end of the competition, you actually get judged on a different data set entirely, called the private leaderboard set. So the only way to avoid this is to actually be a good machine learning practitioner and know how to set these parameters as effectively as possible, which we're going to be doing partly today and over the next few weeks. Can you get the, actually, why don't you throw it to me?
Is it too early or late to ask, what's the difference between a hyperparameter and a parameter?
Too early.
Okay.
Okay. So let's start tracking things on root mean squared error. So here is root mean squared error in a line of code. And you can see here, like, this is one of these examples where I'm not writing this the way a proper software engineer would write this, right? So a proper software engineer would be a number of things differently. They would have it on a different line. They would use longer variable names. They would have documentation, blah, 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 right? But I really think, like for me, I really think that being able to look at something in one go with your eyes and, like, over time learn to immediately see what's going on has a lot of value. And also to, like, consistently use, like, particular letters to mean particular things or abbreviations, I think works really well in data science. if you're doing it like a take-home interview test or something, you should write your code according to PEP 8 standards, right? So PEP 8 is the style guide for Python code, and you should know it and use it, because a lot of software engineers are super anal about this kind of thing. But for your own work, you know, I think this works well for me, you know. So I just wanted to make you aware, A, that you shouldn't necessarily use this as a role model for dealing with software engineers, but B, that I actually think this is a reasonable approach. Okay, so there's our root mean squared error, and then from time to time we're just going to print out the score, which will give us the RMSE of the predictions on the training versus the actual, the predictions on the valid versus the actual RMSE, the R squared for the training, and the R squared for the valid. And we'll come back to OOB in a moment. So when we ran that, we found that this RMSE was in the top 25%, and it's like, okay, there's a good start. Now, this took 8 seconds of wall time, so 8 actual seconds. If you put %time, it'll tell you how long things took. And luckily, I've got quite a few cores, quite a few CPUs in this computer, because it actually took over a minute of compute time. So it parallelized that across cores. If your data set was bigger or you had less cores, you know, you could well find that this took a few minutes to run or even a few hours. My rule of thumb is that if something takes more than 10 seconds to run, it's too long for me to do like interactive analysis with it, right? I want to be able to like run something, wait a moment, and then continue. So what we do is we try to make sure that things can run in a reasonable time. And then when we're finished at the end of the day, we can then say, okay, this feature engineering, these hyperparameters, whatever, these are all working well, and I'll now rerun it, you know, the big, slow, precise way. So one way to speed things up is to pass in the subset parameter to procdf, and that will randomly sample my data, right? And so here I'm going to randomly sample 30,000 rows. Now, when I do that, I still need to be careful to make sure that my validation set doesn't change and that my training set doesn't overlap with the dates. Otherwise, I'm cheating. So I call split vals again to again do this split by dates. And you'll also see I'm using, rather than putting it into a validation set, I'm putting it into a variable called underscore. This is kind of a standard approach in Python, is to use a variable called underscore if you want to throw something away, because I don't want to change my validation set. Like, no matter what different models I build, I want to be able to compare them all to each other, so I want to keep my validation set the same all the time. Okay? So all I'm doing here is I'm resampling my training set into a the first 20,000 out of a 30,000 subset. So I now can run that, and it runs in 621 milliseconds, so I can like really zip through things. Now, try things out. Okay. So with that, let's use this subset to build a model that is so simple that we can actually take a look at it. And so we're going to build a forest that's made of trees. And so before we look at the forest, we'll look at the trees. In scikit-learn, they don't call them trees, they call them estimators. So we're going to pass in the parameter number of estimators equals 1 to create a forest with just one tree in. And then we're going to make a small tree. So we pass in maximum depth equals 3. And a random forest, as we're going to learn, randomizes a whole bunch of things. We want to turn that off. So to turn that off, you say bootstrap equals false. So if I pass in these parameters, it creates a small deterministic tree. Okay, so if I fit it and say print score, my R squared has gone down from 0.85 to 0.4. So this is not a good model. It's better than the mean model. This is better than 0, right? But it's not a good model. But it's a model that we can draw. Right? So let's learn about what it's built. So a tree consists of a sequence of binary decisions, of binary splits. So it first of all decided to split on coupler system greater than or less than 0.5. That's a Boolean variable, so it's actually true or false. And then within the group where coupler system was true, it decided to split into year made greater than or less than 1987. And then where coupler system was true and year made was less than or equal to 1986, it used FI product class desk is less than or equal to 0.75, and so forth. Right? So right at the top, we have 20,000 samples, 20,000 rows. Right? And the reason for that is because that's what we asked for here when we split our data in the sample. We got a question.
I just want to double check that for your decision tree that you had there, that the coloration was whether it's true or false, not so like it gets darker, it's true for the next one, not the
darker is a higher value. We'll get to that in a moment.
Okay.
So let's look at these numbers here. So in the whole data set, well, our sample that we're using, there are 20,000 rows. The average of the log of price is 10.1. And if we built a model where we just use that average all the time, then the mean squared error would be 0.477. Okay? So this is, in other words, the denominator of an R squared. Right? This is like the most basic model is a tree with 0 splits, right? Which is just predict the average. So the best single binary split we can make turns out to be splitting by where the coupler system is greater than or equal to, sorry, less than or equal to or greater than 0.5. In other words, whether it's true or false. And it turns out if we do that, the mean squared error of coupler system is less than 0.5, so it's false, goes down from 0.477 to 0.11, right? So it's really improved the error a lot. In the other group, it's only improved it a bit. It's gone from 0.47 to 0.41. And so we can see that the coupler system equals false group has a pretty small percentage. It's only got 2,200 of the 20,000, right? Whereas this other group has a much larger percentage, but it hasn't improved it as much. So let's say you wanted to create a tree with just one split. So you're just trying to find, like, what is the very best single binary decision you can make for your data. How might you be able to do that? How could you do it? Do you want to give it to Ford?
Specify the max depth of 1.
But I mean, you're writing. You don't have a random forest, right? How are you gonna like write? What's an algorithm? A simple algorithm which you could use. Sure. So we want to start building a random forest from scratch. So the first step is to create a tree. The first step to create a tree is to create the first binary decision. How are you going to do it? I'm going to give it to Chris. Maybe in 2 steps. Or give it to Chris.
So isn't this simply trying to find the best predictor based on maybe a linear regression?
You could use a linear regression, but could you do something much simpler and more complete? We're trying not to use any statistical assumptions here. I can't see your name, sorry. Prince. Oh, of course you're Prince. I knew that.
Can we just do like, take just one variable, if it is true, give it like the true thing, and if it is false, go on to
so which variable are we going to choose? So at each binary point, we have to choose a variable and something to split on. How are we going to do that? You want to pass it over there? How do I pronounce your name?
Shikhar. So the variable to choose could be like which divides the population into 2 groups which are kind of heterogeneous to each other and homogeneous within themselves, like having the same quality within themselves, and they are very different.
Could you be more specific?
Like in terms of the target variable, maybe.
Yes.
Like let's say we have 2 groups after split, so one has a different price altogether from the second group.
Yes.
But internally they have similar prices.
Okay, that's good. So like to simplify things a little bit, we're saying find a variable that we could split into such that the two groups are as different to each other as possible. And okay, how would you pick which variable and which split point? That's the question. Yeah, what's your first cut? Which variable and which split point? We're making a tree from scratch. We want to create our own tree. Does that make sense? We've got somebody over here. Maisley? I'll pass it to Jason. Maisley, maybe?
Can we test all of the possible split and see which one has a smaller RMSE? And then
That sounds good. Okay, so let's dig into this. So when you say test all of the possible splits, what does that mean? How do we enumerate all the possible splits?
Oh, I didn't think of that, but if you want.
For each variable, you could put one aside, and then put a second aside and compare the two, and if it was better.
Good, okay, so for each variable, for each possible value of that variable, see whether it's better. Now, give it back to Maisley, because I want to dig into the better. When you said see if the RMSE is better, what does that mean, though? Because after a split, you've got two RMSEs. You've got two groups.
So you're just gonna fit with that one variable comparing to the others, not so.
So what I mean here is that before we decided to split on coupler system,
yeah,
we had a mean squared of 0.477, and after we've got two groups, one with a mean squared error of 0.1, another with a mean squared error of 0.4.
So you treat each individual model separately. So for the first split, you're just gonna compare between each variable themselves. And then you move on to the next node with the remaining.
But even the first node, so the model with 0 splits has a single root mean squared error. The model with 1 split, so the very first thing we try, we've now got two groups with 2 mean squared errors. You want to give it to Daniel?
Do you pick the one that gets them as different as they can be?
Well, okay, that would be one idea. Get the 2 mean squared errors as different as possible. But why might that not work? What might be a problem with that?
Sample size.
Go on.
Because you could just literally leave one point out.
Yeah, so we could have year made is less than 1950, and it might have a single sample with a low price, and that's not a great split, is it? Because the other group is actually not going to be very interesting at all. Can you improve it a bit? Can Jason improve it a bit?
Could you take a weighted average?
Yeah, a weighted average. So we could take 0.41 times 17,000 plus 0.1 times 2,000. That's good, right? And that would be the same as actually saying, I've got a model. The model is a single binary decision, and I'm going to say for everybody with year made less than 1986.5, I'm going to fill in 10.2. For everybody else, I'm going to fill in 9.2, and then I'm going to calculate the root mean squared error of this crappy model. And that would give exactly the same, right, as the weighted average that you're suggesting. Okay, good. So we now have a single number that represents how good a split is, which is the weighted average of the mean squared errors of the two groups it creates. Okay, and thanks to, I think it was it Jake, we have a way to find the best split, which is to try every variable and to try every possible value of that variable and see which variable and which value gives us a split with the best score. Does that make sense? Okay, what's your name, sorry? Okay. Easily fixed. Can somebody give Natalie the box? And I will give Natalie.
When you say every possible number for every possible variable, are you saying here we have 0.5 as our criteria to split the tree? So are you saying we're trying out every single number for
every possible value, right? So coupler system only has 2 values, true and false. So there's only one way of splitting, which is trues and falses. Year made is an integer which varies between, like, I don't know, 1960 and 2010. So we can just say, what are all the possible unique values of year made, and try them all. So we're trying all the possible split points. Can you pass that back to Daniel, or pass it to me and I'll pass it to Daniel? So remember, I'm going to speak loudly. Step 1 is breathe in. Okay. Otherwise, it's not possible. Physically not possible.
So I just want to clarify again, for the first split, why did we split on coupler system, true or false, to start with?
Because what we did was we used Jake's technique. We tried every variable. For every variable, we tried every possible split. For each one, we noted down, I think it was Jason's idea, which was the weighted average mean squared error of the 2 groups it created. We found which one had the best mean squared error, and we picked it. And it turned out it was coupler system, true or false. Does that make sense?
I guess my question is more like, so coupler system is like one of the best indicators, I guess?
It's the best.
Okay.
We tried every variable and every
so
possible
each
level.
level after that, it gets less and less.
Everything else it tried wasn't as good.
Okay, and then you do that each time you split?
Right, so now that we've done that, we now take this group here, everybody who's got coupler system equals true, and we do it again. For every possible variable, for every possible level, for people where coupler system equals true, what's the best possible split?
And then, are there circumstances when it's not just like binary, like you split it into like 3 groups for like example year made?
So I'm going to make a claim,
Okay.
and then I'm going to see if you can justify it. I'm going to claim that it's never necessary to do more than one split at a level.
Because you can just split it again.
Because you can just split it again. Exactly. So you can get exactly the same result by splitting twice. Okay, good. So that is the entirety of creating a decision tree. You stop either when you hit some limit that was requested. So we had a limit where we said max depth equals 3. So that's one way to stop, would be you asked to stop at some point, and so we stop. Otherwise, you stop when your leaf nodes, these things at the end are called leaf nodes, when your leaf nodes only have one thing in them. Okay? That's a decision tree. That is how we grow a decision tree. And this decision tree is not very good because it's got a validation R squared of 0.4. So we could try to make it better by removing max depth equals 3, right, and creating a deeper tree. So it's going to go all the way down, it's going to keep splitting these things further until every leaf node only has one thing in it. And if we do that, the training R squared is, of course, 1. Because we can exactly predict every training element because it's in a leaf node all on its own. But the validation R squared is not 1. It's actually better than our really, really shallow tree, but it's not as good as we'd like. Okay, so we want to find some other way of making these trees better. And the way we're going to do it is to create a forest. So what's a forest? To create a forest, we're going to use a statistical technique called bagging. And you can bag any kind of model. In fact, Michael Jordan, who was one of the speakers at the recent Data Institute conference here at University of San Francisco, developed a technique called the bag of little bootstraps, in which he shows how to use bagging for absolutely any kind of model to make it more robust and also to give you confidence intervals. The random forest is simply a way of bagging trees. So what is bagging? Bagging is a really interesting idea, which is, what if we created 5 different models, each of which was only somewhat predictive, but the models weren't at all correlated with each other. They gave predictions that weren't correlated with each other. That would mean that the 5 models would have to have found different insights into the relationships in the data. And so if you took the average of those 5 models, right, then you're effectively bringing in the insights from each of them. And so this idea of averaging models is a technique for ensembling, right, which is really important. Now let's come up with a more specific idea of how to do this ensembling. What if we created a whole lot of these trees? Big, deep, massively overfit trees, right? But each one, let's say we only pick a random 1/10 of the data. So we pick 1 out of every 10 rows at random, build a deep tree, right, which is perfect on that subset and kind of crappy on the rest, right? Let's say we do that 100 times, so different random sample every time. So all of the trees are going to be better than nothing, right? Because they do actually have a real random subset of the data, and so they found some insight, but they're also overfitting terribly. But they're all using different random samples, so they all overfit in different ways on different things. So in other words, they all have errors, but the errors are random. What is the average of a bunch of random errors? 0. So in other words, if we take the average of these trees, each of which have been trained on a different random subset, the errors will average out to 0, and what's left is the true relationship. And that's the random forest. Right? So there's the technique, right? We've got a whole bunch of rows of data. We grab a few at random, right? Put them into a smaller data set and build a tree based on that. Right? And then we put that tree aside and do it again with a different random subset. And do it again with a different random subset. Do that a whole bunch of times. And then for each one, we can then make predictions by running our test data through the tree to get to the leaf node, take the average in that leaf node for all the trees, and average them all together. So to do that, we simply call random forest regressor, and by default, it creates 10 what scikit-learn calls estimators. An estimator is a tree, right? So this is going to create 10 trees. And so we go ahead and train it. I can't remember if I remember to do the split. Okay, so create our 10 trees, and we're just doing this on our little random subset of 20,000. And so let's take a look at one example. Can you pass the box to Devin?
So just to make sure I'm understanding this, so you're saying like we take 10 kind of crappy models, we average 10 crappy models, and we get a good model.
Exactly. Because the crappy models are based on different random subsets, and so their errors are not correlated with each other. If the errors were correlated with each other, this isn't going to work. Okay, so the key insight here is to construct multiple models which are better than nothing, and where the errors are, as much as possible, not correlated with each other.
Is there like a certain number of trees that like we need that in order to be valid? Like,
there's no such thing as like valid or invalid. There's like has a good validation set RMSE or not, you know. And so that's what we're going to look at is how to make that metric higher. And so this is the first of our hyperparameters. And we're going to learn about how to tune hyperparameters, and the first one is going to be the number of trees, and we're about to look at that now. Yes, Maisley.
The subset that you are selecting, are they exclusive? Can you have overlapping of them?
Yeah, so I mentioned, you know, one approach would be pick out like a 10th at random, but actually what scikit-learn does by default is for n rows, it picks out n rows with replacement. Okay, and that's called bootstrapping. And if memory serves me correctly, that gets you on average 63.2% of the rows will be represented, and you know a bunch of them will be represented multiple times. Yeah. Sure. So rather than just picking out like a 10th of the rows at random, instead we're going to pick out of an n row data set, we're going to pick out n rows with replacement. which on average gets about 63.2% of the rows will be represented. Many of those rows will appear multiple times. I think there's a question behind you.
In essence, what this model is doing is, if I understand correct, it's just picking out the data points that look most similar to the one you're looking at.
Yeah, that's a great insight. So what a tree is kind of doing...
Isn't that quite a complicated way of going about doing that, if you see what I mean? There would be other ways of like assessing similarity of features.
There are other ways of assessing similarity, but what's interesting about this way is it's doing it in tree space, right? So we're basically saying, what are, in this case, like for this little tree, what are the 593 samples, closest to this one, and what's their average? Closest in tree space. So other ways of doing that would be like, and we'll learn later on in this course about k nearest neighbors, you could use like Euclidean distance, say, right? But here's the thing. The whole point of machine learning is to identify which variables actually matter the most and how do they relate to each other and to your dependent variable together. Right? So if you've, like, imagine a synthetic data set where you create 5 variables that add together to create your dependent variable, and 95 variables which are entirely random and don't impact your dependent variable. And then if you do like a k nearest neighbors in Euclidean space, you're going to get meaningless nearest neighbors because most of your columns are actually meaningless. Or imagine your actual relationship is that your dependent variable equals x1 times x2. Then you actually need to find this interaction, right? So you don't actually care about how close it is to x1 and how close to x2, but how close to the product. So the entire purpose of modeling in machine learning is to find a model which tells you which variables are important and how do they interact together to drive your dependent variable. And so you'll find in practice the difference between using like tree space or random forest space to find your nearest neighbors versus like Euclidean space is the difference between a model that makes good predictions and a model that makes meaningless predictions. Melissa, do you have?
Might be queued for a break.
I did, but I feel like we've got only 35 minutes, so yeah. Great. So in general, a machine learning model which is effective is one which is accurate. When you look at the training data, it's accurate at predicting, at actually finding the relationships in that training data, and then it generalizes well to new data. And so in bagging, that means that each of your individual estimators, each of your individual trees, you want to be as predictive as possible, but for the predictions of your individual trees to be as uncorrelated as possible. And so the inventor of random forests talks about this at length in his original paper that introduced this in the late 90s, this idea of trying to come up with predictive but poorly correlated trees. The research community in recent years has generally found that the more important thing seems to be creating uncorrelated trees rather than more accurate trees. So more recent advances tend to create trees which are less predictive on their own, but also less correlated with each other. So for example, in scikit-learn, there's another class you can use called extra trees regressor or extra trees classifier with exactly the same API. You can try it tonight. Just replace my random forest regressor with that. That's called an extremely randomized trees model. And what that does is exactly the same as what we just discussed, but rather than trying every split of every variable, it randomly tries a few splits of a few variables, right? So it's much faster to train. It has more randomness, okay? But then with that time, you can build more trees and therefore get better generalization. So in practice, if you've got crappy individual models, you just need more trees to get a good end-up model. Melissa, could you pass that over to Devin?
Could you talk a little bit more about what you mean by like uncorrelated trees?
Yeah. If I build 1,000 trees, each one on just 10 data points, then it's quite likely that the 10 data points for every tree are going to be totally different. And so it's quite likely that those 10 trees are going to, 1,000 trees are going to give totally different answers to each other. So the correlation between the predictions of tree 1 and tree 2 is going to be very small, between tree 1 and tree 3, very small, and so forth. On the other hand, if I create 1,000 trees where each time I use the entire data set with just one element removed, all those trees are going to be nearly identical, i.e. their predictions will be highly correlated. And so in the latter case, it's probably not going to generalize very well. Whereas in the former case, the individual trees are not going to be very predictive. So I need to find some nice in between. So, yes, Danielle.
And is there a case where you want to use one over the other, like any particular times?
Yeah, so again, hyperparameter tuning. So okay. Do you mean in terms of like random forests versus extremely randomized trees? Yeah, so again, a hyperparameter, what tree architecture do we use? So we're going to talk about that now. Can you pass that to Dina?
Yeah, I was just trying to understand how this random forest actually makes sense for continuous variables. I mean, I'm assuming that you build a tree structure and the last final nodes you'd be saying like maybe this small node represents maybe a category A or a category B, but how does it make sense for a continuous target?
So this is actually what we have here, and so the value here is the average. So this is the average log of price for this subgroup, and that's all we do. The prediction is the average of the value of the dependent variable in that leaf node.
Okay, so that means finally, if we have just like 10 leaf nodes, we'll just have 10 values.
Yes.
By predicting.
That's well, if it was only one tree. All right.
Yeah.
So a couple of things to remember. The first is that by default, we're actually going to train the tree all the way down until the leaf nodes are of size 1, which means for a data set with n rows, we're going to have n leaf nodes. And then we're going to have multiple trees, which we average together, right? So in practice, we're going to have lots of different possible values. Is a question behind you?
So for the continuous variable, how do we decide like which value to split at? Because there can be many values in.
We try every possible value of that in the training set.
Won't it be computationally
expensive? And this is where it's very good to remember that your CPU's performance is measured in gigahertz, which is billions of clock cycles per second, and it has multiple cores, and each core has something called SIMD, single instruction multiple data, where it can do up to 8 computations per core at once. And then, if you do it on the GPU, the performance is measured in teraflops, so trillions of floating point operations per second. And so this is where, when it comes to designing algorithms, it's very difficult for us mere humans to realize how stupid algorithms should be given how fast today's computers are. So yeah, it's quite a few operations, but at trillions per second, you hardly notice it. Masha.
I have a question. So essentially, at each mode, we make a decision, like which category to, which variable to use,
and which split point. Yes.
Yeah, but one thing I can't understand. So we have MSE calculated for each node, right?
Yes.
So this is kind of one of the decision criteria. But this MSE, it is calculated for which model? Like which model underlies? Like,
the model is for the initial root node is what if we just predicted the average, right? Which here is 10.098. Just the average. And then the next model is what if we predicted the average of those people with coupler system equals false, and for those people with coupler system equals true. And then the next is what if we predicted the average of coupler systems equals true, year made less than 1986.
Is it always average, or we can use median, or we can even run linear regression?
There's all kinds of things we could do. In practice, the average works really well. There are types of, they're not called random forests, but there are kinds of trees where the leaf nodes are independent linear regressions. They're not terribly widely used, but there are certainly researchers who have worked on them.
Okay, thank you.
And pass it back over there to Ford and then to Jake.
So this tree has a depth of 3.
Yeah.
And then like on one of the next commands, we get rid of the max depth.
Yeah.
Is the tree without the max depth, does that contain the tree with the depth of 3?
Mm-hmm. Yeah.
So is that like by definition? It's
well, except in this case we've added randomness. But if you turn bootstrapping off, then yeah, the deeper tree will, the less deep tree would be how it would start, and then it just keeps splitting.
Okay.
So you have many trees. You're going to have different leaf nodes across trees. Hopefully,
Mm-hmm.
that's what we want.
Mm-hmm.
So how do you average leaf nodes across different trees?
So we just take the first row in the validation set, we run it through the first tree, we find its average, 9.28. Then do it through the next tree, find its average in the second tree, 9.95, and so forth. And we're about to do that, so you'll see it. Okay, so let's try it, right? So after you've built a random forest, each tree is stored in this attribute called estimators underscore. Okay, so one of the things that you guys need to be very, very comfortable with is using list comprehensions. Okay, so I hope you've all been practicing. Okay, so here I'm using a list comprehension to go through each tree in my model. I'm going to call predict on it with my validation set. And so that's going to give me a list of arrays of predictions. So each array will be all of the predictions for that tree. And I have 10 trees. np.stack concatenates them together on a new axis. So after I run this and call .shape, you can see I now have the first axis 10, means I have my 10 different sets of predictions. And for each one, my validation set is a size 12,000. So here are my 12,000 predictions for each of the 10 trees. Right? So let's take the first row of that and print it out. And so here are what we were just saying. Here are 10 predictions, one from each tree. Okay? And so then if we say take the mean of that, here is the mean of those 10 predictions. And then what was the actual? The actual was 9.1, our prediction was 9.07. So you see how like none of our individual trees had very good predictions, but the mean of them was actually pretty good. Right? And so when I talk about experimenting, like Jupyter Notebook is great for experimenting, this is the kind of stuff I mean. Dig inside these objects and like look at them, plot them, take your own averages, cross-check to make sure that they work the way you thought they did. Write your own implementation of R squared, make sure it's the same as the scikit-learn version, plot it. Like here's an interesting plot I did. Let's go through each of the 10 trees, right? And then take the mean of all of the predictions up to the ith tree. Right? So let's start by predicting just based on the first tree, then the first 2 trees, then the first 3 trees, and let's then plot the R squared. So here's the R squared of just the first tree. Here's the R squared of the first 2 trees, 3 trees, 4 trees, blah, 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 up to 10 trees. And so not surprisingly, R squared keeps improving, right? Because the more estimators we have, the more bagging that we're doing, the more it's going to generalize. Right? And you should find that that number there, a bit under 0.86, should match this number here. Okay? Let's rerun that. Yeah, okay, so that's actually slightly above 0.86. Right? So again, these are all like the cross-checks you can do, the things you can visualize to deepen your understanding. Okay, so as we add more trees, our R squared improves. It seems to flatten out after a while. So we might guess that if we increase the number of estimators to 20, right, it's maybe not going to be that much better. So let's see. We've got 0.862 versus 0.860. Yeah, so doubling the number of trees didn't help very much. If I double it again, 867, double it again, 869. So you can see like there's some point at which you're going to, not want to add more trees, not because it's never going to get worse, right? Because every tree is, giving you more semi-random models to bag together, right? But it's going to stop improving things much. Okay, and so this is like the first hyperparameter for you to learn to set is number of estimators, and the method for setting it is as many as you have time to fit and that actually seem to be helping. Okay. Now, in practice, we're going to learn to set a few more hyperparameters. Adding more trees slows it down. But with less trees, you can still get the same insights. So I build most of my models in practice with like 20 to 30 trees. And it's only like then at the end of the project or maybe at the end of the day's work, I'll then try doing like, 1,000 trees and run it overnight. Was there a question? Yes. Can we pass that to Prince?
So each tree might have different estimators, different combination of estimators.
Each tree is an estimator, so this is a synonym. So in scikit-learn, when they say estimator, they mean tree.
So I mean features.
Features.
Each tree might have different
Each tree will have different breakpoints on different columns.
What if at the end we want to look at the important features?
We'll get to that. Yeah. So after we finish with kind of setting hyperparameters, the next stage of the course will be learning about what it tells us about the data. If you need to know it now, for your projects, feel free to look ahead. There's a lesson 2 RF interpretation is where you can see it. Okay, so that's our first hyperparameter. I want to talk next about out-of-bag score. Sometimes your data set will be kind of small, and you won't want to pull out a validation set because doing so means you now don't have enough data to build a good model. What do? There's a cool trick which is pretty much unique to random forests, and it's this. What we could do is recognize that in our first tree, some of our rows didn't get used. So what we could do would be to pass those rows through the first tree and treat it as a validation set. And then for the second tree, we could pass through the rows that weren't used for the second tree through it to create a validation set for that. And so effectively, we would have a different validation set for each tree. And so now, to calculate our prediction, we would average all of the trees where that row was not used for training, right? So for tree number 1, we would have the ones I've marked in blue here, and then maybe for tree number 2, it turned out it was like this one, this one, this one, and this one, and so forth, right? So as long as you've got enough trees, every row is going to appear in the out-of-bag sample for one of them, at least. So you'll be averaging, hopefully a few trees. So if you've got 100 trees, it's very likely that all of the rows are going to appear many times in these out-of-bag samples. So what you can do is you can create an out-of-bag prediction by averaging all of the trees you didn't use to train each individual row, and then you can calculate your root mean squared error, R squared, etc. on that. If you pass OOB score equals true to scikit-learn, it will do that for you, and it will create an attribute called OOB score underscore. And so my little print score function here, if that attribute exists, it adds it to the print. So if you take a look here, OOB score equals true, we've now got one extra number, and it's R squared, that is the R squared for the OOB sample. Its R squared is very similar to the R squared in the validation set, which is what we hoped for. Can we pass it?
Is it the case that the prediction for the OOB score must be mathematically lower than the one for our entire forest?
Certainly it's not true that the prediction is lower. It's possible that the accuracy is lower.
The R squared, squared, I mean.
It's not mathematically necessary that it's true, but it's going to be true on average because your average, for each row appears in less trees in the OOB samples than it does in the full set of trees. So as you see here, it's a little less good. So in general, it's a great insight, Chris. In general, the OOB R-squared will slightly underestimate how generalizable the model is. The more trees you add, the less serious that underestimation is. And for me, in practice, I find it's totally good enough, in practice. Okay, so this OOB score is super handy. And one of the things it's super handy for is you're going to see there's quite a few hyperparameters that we're going to set. And we would like to find some automated way to set them. And one way to do that is to do what's called a grid search. A grid search is where there's a scikit-learn function called grid search, and you pass in the list of all of the parameters, all of the hyperparameters that you want to tune. You pass in for each one a list of all of the values of that hyperparameter you want to try, and it runs your model on every possible combination of all of those hyperparameters and tells you which one is the best. And OOB score is a great choice for getting it to tell you which one is best in terms of OOB score. That's an example of something you can do with OOB which works well. Now, if you think about it, I kind of did something pretty dumb earlier, which is I took a subset of 30,000 rows of the data and I built all my models of that, which means every tree in my random forest is a different subset of that subset of 30,000. Why do that? Why not pick a totally different subset of 30,000 each time? So in other words, let's leave the entire 300,000 records as is, right? And if I want to make things faster, right, pick a different subset of 30,000 each time. So rather than bootstrapping the entire set of rows, let's just randomly sample a subset of the data. And so we can do that. So let's go back and recall proctf without the subset parameter to get all of our data again. And so to remind you, that is, 400,000 in the whole data frame, of which we have 389,000 in our training set. And instead, we're going to go set RF samples 20,000. Remember that was the site of the 30,000, we used 20,000 of them in our training set. If I do this, then now when I run a random forest, it's not going to bootstrap an entire set of 391,000 rows. It's going to just grab a subset of 20,000 rows. Right? And so now if I run this, it will still run just as quickly as if I had originally done a random sample of 20,000, but now every tree can have access to the whole data set, right? So if I do enough estimators, enough trees, eventually it's going to see everything, right? So in this case, with 10 trees, which is the default, I get an R-squared of 0.86, which is actually about the same as my R-squared with the 20,000 subset. And that's because I haven't used many estimators yet, right? But if I increase the number of estimators, it's going to make more of a difference, right? So if I increase the number of estimators to 40, right, it's going to take a little bit longer to run, but it's going to be able to see a larger subset of the data set. And so as you can see, the R-squared's gone up from 0.86 to 0.876. Okay, so this is actually a great approach. And for those of you who are doing the groceries competition, that's got something like 120 million rows, right? There's no way you would want to create a random forest using 128 million rows in every tree. It's going to take forever. So what you could do is use this set RF samples to do 100,000 or a million, or play around with it. So the trick here is that with a random forest using this technique, no data set is too big. I don't care if it's got 100 billion rows, right? You can create a bunch of trees, each one with a different random subset. Can somebody pass the, actually I can pass it.
Sorry.
No worries. We've got some actual pieces of pad, so if you've got a sloppy thing, use one of these pieces of pad.
So my question was, for the OOB scores and these ones, does it take only like for the ones from the sample, or does it take from all the...
That's a great question. So unfortunately, scikit-learn does not support this functionality out of the box, so I had to write this. And it's kind of a horrible hack, right? Because we'd much rather be passing in like a sample size parameter rather than doing this kind of setting up here. So what I actually do is, if you look at the source code, is this is the internal function. I looked at their source code that they call, and I've replaced it with a Lambda function that has the behavior we want. Unfortunately, the current version is not changing how OOB is calculated. So currently OOB scores and set RF samples are not compatible with each other, so you need to turn OOB equals false if you use this approach, which I hope to fix, but at this stage it's not fixed. So if you want to turn it off, you just call reset RF samples, okay, and that returns it back to what it was. Okay, so in practice, when I'm like doing interactive machine learning using random forests in order to like explore my model, explore hyperparameters, the stuff we're going to learn in the future lesson where we actually analyze like feature importance and partial dependence and so forth, I generally use subsets and reasonably small forests. Because all the insights that I'm going to get are exactly the same as the big ones, but I can run it in like, 3 or 4 seconds rather than hours, right? So this is one of the biggest tips I can give you, and very, very few people in industry or academia actually do this. Most people run all of their models on all of the data all of the time using their best possible parameters, which is just pointless, right? If you're trying to find out like which features are important and how are they related to each other and so forth, having that 4th decimal place of accuracy isn't going to change any of your insights at all. Okay, so I would say like do most of your models on, a large enough sample size that your accuracy is, reasonable. When I say reasonable, it's like within a reasonable distance of the best accuracy you can get. And it's taking, a small number of seconds to train so that you can interactively do your analysis. So there's a couple more parameters I wanted to talk about. So I'm going to call reset RF samples to get back to our full data set, because in this case, at least on this computer, it's actually running in less than 10 seconds. So here's our baseline. We're going to do a baseline with 40 estimators. Okay, and so each of those 40 estimators is going to train all the way down until the leaf nodes just have one sample in them. So that's going to take a few seconds to run. Here we go. So that gets us a 0.898 R squared on the validation set, or 0.908 on the OOB. Now in this case, the OOB is better. Why is it better? Well, that's because remember our validation set is not a random sample. Our validation set is a different time period. Okay, so it's actually much harder to predict a different time period than this one, which is just predicting random. Okay, so that's why this is not the way around we expected. So the first parameter we can try fiddling with is min samples leaf. And so min samples leaf says stop training the tree further when your leaf node has 3 or less samples in. So rather than going all the way down until there's 1, we're going to go down until there's 3. So in practice, this means there's going to be like 1 or 2 less levels of decision being made, which means we've got like half the number of actual decision criteria we have to do, so it's going to train more quickly. It means that when we look at an individual tree, rather than just taking 1 point, we're taking the average of at least 3 points. Right? So we'd expect the trees to generalize, each one to generalize a little bit better. Okay? But each tree is probably going to be slightly less powerful on its own. So let's try training that. So possible values of min samples leaf, I find ones which work well are kind of 1, 3, 5, 10, 25. You know, like I find that kind of range seems to work well. But like sometimes if you've got a really big data set and you're not using the small samples, you know, you might need a min samples leaf of hundreds or thousands. So it's, you kind of got to think about like how big are your subsamples going through and try things out. Now in this case, going from the default of 1 to 3 has increased our validation set R squared from 898 to 902. So it's a slight improvement. Okay, and it's going to train a little faster as well. Okay, something else you can try, which is, and so since this worked, I'm going to leave that in. I'm going to add in max features equals 0.5. What does max features do? Well, the idea is that the less correlated your trees are with each other, the better. Now imagine you had one column that was so much better than all of the other columns at being predictive that every single tree you built, regardless of like which subset of rows, always started with that column. So the trees are all going to be pretty similar, right? But you can imagine there might be some interaction of variables where that interaction is more important than that individual column. So if every tree always splits on the first thing, the same thing the first time, you're not going to get much variation in those trees. So what we do is, in addition to just taking a subset of rows, we then, at every single split point, take a different subset of columns. So it's slightly different to the row sampling. For the row sampling, each new tree is based on a random set of rows. For column sampling, every individual binary split we choose from a different subset of columns. So in other words, rather than looking at every possible level of every possible column, we look at every possible level of a random subset of columns. Okay? And each time, each decision point, each binary split, we use a different random subset. How many? Well, you get to pick. 0.5 means randomly choose half of them. The default is to use all of them. There's also a couple of special values you can use here. As you can see in max features, you can also pass in square root to get square root of features, or log 2 to get log 2 of features. So in practice, good values I've found are range from 1, 0.5, log 2, or square root. That's going to give you a nice bit of variation, right? Can somebody pass it to Danielle?
And so just to clarify, does that just like break it up smaller each time it goes through the tree, or is it just taking half of what's left over or like hasn't been touched each time?
There's no such thing as what's left over.
Okay.
Like, after you've split on year made less than or greater than 1984, year made's still there, right? So later on, you might then split on year made less than or greater than 1989. So it's just each time, rather than checking every variable to see where its best split is, you just check half of them. And so the next time you check a different half. The next time you check a different half.
But I mean, like, in terms is as you get like further to like the leaves, you're going to have less options, right?
No, you're not.
Okay.
You never remove the variables.
Okay.
You can use them again and again and again because you've got lots of different split points. So imagine, for example, that the relationship was just entirely linear between year made and price, right? Then in practice, to actually model that, you know, your real relationship is year made versus price, right? But the best we could do would be to kind of first of all split here, right? And then to split here and here, right? And like split and split and split.
But
so
if they were binary, I'm saying, like for
yeah, even if they're binary,
like
most random forest libraries don't do anything special about that. They just kind of go, okay, we'll try this variable. Oh, it turns out there's only one level left, you know. So yeah, that generally they don't do any kind of clever bookkeeping.
Okay.
Okay, so if we add max features equals 0.5, it goes up from 901 to 906. So that's better still. And so as we've been doing this, you also hopefully have noticed that our root mean squared error of log price has been dropping on our validation set as well. And so it's now down to 0.2286. So how good is that, right? So like our totally untuned random forest got us in about the top 25%. Now remember, our validation set isn't identical to the Kaggle test set, right? And this competition, unfortunately, is old enough that you can't even put in a kind of after the time entry to find out how you would have gone. So we can only approximate how we could have gone, but generally speaking, it's going to be a pretty good approximation. So 2286. Here is the competition. Here's the public leaderboard. 2286. There we go. 14th or 15th place. Okay. So, roughly speaking, looks like we would be about in the top 20 of this competition with basically totally brainless random forest with some totally brainless minor hyperparameter tuning. Okay. And so this is kind of why the random forest is such an important, not just first step, but often only step for machine learning. Because it's kind of hard to screw it up. Like, even when we didn't tune the hyperparameters, we still got a good result, right? And then a small amount of hyperparameter tuning got us a much better result. And so any kind of model, and I'm particularly thinking of like linear type models, which have a whole bunch of statistical assumptions and you have to get a whole bunch of things right before they start to work at all, can really throw you off track, right? Because they give you like totally wrong answers about how accurate the predictions can be. Whereas with the random forest, generally speaking, they tend to work on most data sets most of the time with most sets of hyperparameters. So, for example, we did this thing with our categorical variables. In fact, let's take a look at our tree. Single tree. Look at this, right? FI product class desk less than 7.5. What does that mean? So FI product class desk. Here's some examples of that column. All right, so what does it mean to be less than or equal to 7? Well, we'd have to look at .cat.categories to find out. Okay, and so it's 0, 1, 2, 3, 4, 5, 6, 7. So what it's done is it's created a split where all of the backhoe loaders and these three types of hydraulic excavator are in one group and everything else is in the other group. So like, that's like weird, like these aren't even in order. We could have made them in order if we had, bothered to say the categories have this order, but we hadn't, right? So how come this even works, right? Like, because when we turn it into codes, this is actually what the random forest sees. And so imagine, to think about this, imagine like the only thing that mattered was whether it was a hydraulic excavator 0 to 2 metric tons and nothing else mattered. Imagine that, right? So it has to pick out this single level. Well, it can do that because first of all, it could say, okay, let's pick out everything less than 7 versus greater than 7 to create, this as one group and this as another group, right? And then within this group, it could then pick out everything less than 6 versus greater than 6, which is going to pick out this one item, right? So with 2 split points, we can pull out a single category. So this is why it works, right? Is because the tree is like infinitely flexible. Even with a categorical variable, if there's particular categories which have different levels of price, it can like gradually zoom in on those groups by using multiple splits. Right? Now, you can help it by telling it the order of your categorical variable, but even if you don't, it's okay. It's just going to take a few more decisions to get there. Right? And so you can see here, it's actually using this product class desk quite a few times. Right? And as you go deeper down the tree, you'll see it used more and more, right? So whereas in a linear model, or almost any kind of other model, certainly any non-tree model, pretty much, encoding a categorical variable like this won't work at all, because there's no linear relationship between totally arbitrary identifiers and anything, right? So these are the kinds of things that make random forests very easy to use and very resilient. And so by using that, we've gotten ourselves a model which is clearly, world class at this point already. It's like, probably well in the top 20 of this Kaggle competition. And then in our next lesson, we're going to learn about how to analyze that model to learn more about the data to make it even better. Great. So this week, try and really experiment. Right? Have a look inside, try and draw the trees, try and plot the different errors, try maybe using different data sets to see how they work. Really experiment to try and get a sense, and maybe try to replicate things like write your own R squared, write your own versions of some of these functions. See how much you can really learn about your data set and about the random forest. So today we're going to look at something I think maybe even more important than building a predictive model that's good at predicting, which is to learn how to interpret that model to find out what it says about your data, to actually understand your data better by using machine learning. And this is kind of contrary to the common refrain that things like random forests are black boxes that hide meaning from us. And you'll see today that the truth is quite the opposite. The truth is that random forests allow us to understand our data deeper and more quickly than traditional approaches. The other thing we're going to learn today is how to look at larger data sets than those which you can import with just the defaults. And specifically, we're going to look at a data set with over 100 million rows, which is the current Kaggle competition for groceries forecasting. Did anybody have any questions outside of those two areas, since we're covering that today, or comments that they wanted to talk about?
Yeah, I apologize. It's kind of basic, just to make sure I'm understanding the concept.
Make sure they can hear you.
Oh, sorry. Can you just talk a little bit about in general, I understand the details more now of a random forest, but when do you know this is an applicable model to use? In general, be oh, I should try a random forest here, because that's the part that I'm still if I'm told to, I can. But
So the short answer is I can't really think of anything offhand that it's definitely not going to be at least somewhat useful for. So it's always worth trying. I think really the question is, in what situations should I try other things as well? And the short answer to that question is, for unstructured data, what I call unstructured data, so where all the different data points represent the same kind of thing, like a waveform in a sound or speech, or the words in a piece of text, or the pixels in an image, you almost certainly are going to want to try deep learning. And then outside of those two, there's a particular type of model we're going to look at today called a collaborative filtering model, where, which it so happens that the groceries competition is of that kind, where neither of those approaches are quite what you want without some tweaks to them. So that would be the other main one.
Sorry, you're saying neither. Are you saying deep learning and random
Neither
forests?
deep learning or random forests is exactly what you want. You need to kind of do some tweaks. You'll see. If anybody thinks of other places where maybe neither of those techniques is the right thing to use, mention it on the forums, even if you're not sure, so we can talk about it, because I think this is one of the more interesting questions. And to some extent, it is a case of practice and experience, but I do think there are, two main classes to know about. So last week we, at the point where we had kind of done some of the key steps, like the CSV reading in particular, which took, a minute or two, at the end of that we saved it to a feather format file. And just to remind you, that's because this is basically almost the same format that it lives in RAM, so it's like ridiculously fast to read and write stuff from feather format. So what we're going to do today is we're going to look at lesson 2, RF interpretation, and the first thing we're going to do is read that feather format file. Now, one thing to mention is a couple of you pointed out during the week a really interesting little bug or little issue, which is in the procdf function. The procdf function, remember, finds the numeric columns which have missing values and creates an additional Boolean column, as well as replacing the missing with medians. Also turns the categorical objects, into the integer codes. The main things it does. And a couple of you pointed out some key points about the missing value handling. The first one is that your test set may have missing values in some columns that weren't in your training set, or vice versa. And if that happens, you're going to get an error when you try to do the random forest, because it's going to say, if that is missing field appeared in your training set but not in your test set, and it ended up in the model, it's going to say you can't use that data set with this model because you're missing one of the columns it requires. That's problem number 1. Problem number 2 is that the median of the missing value, the median of the numeric values in the test set may be different to the training set, and so it may actually process it into something which has different semantics. So I thought that was a really interesting point. So what I did was I changed procdf so it returns a third thing, NAs. And the NAs thing it returns, it doesn't matter in detail what it is, but I'll tell you just so you know, that's a dictionary where the keys are the names of the columns that have missing values, and the values of the dictionary are the medians. And so then optionally, you can pass NAs as an additional argument to procdf, and it'll make sure that it adds those specific columns and it uses those specific medians. Okay, so it's giving you the ability to say, process this test set in exactly the same way as we process this training set. Can you pass that, please?
Hi, is this a updated feature? So you just updated it?
Yeah, so I just did that
so we have to do
yesterday or the day before.
So just the git pull. And
yeah, in fact, that's a good point. Before you start doing work any day, I would start doing a git pull. And if something's not working today that was working yesterday, check the forum where there'll be an explanation of why. This library in particular is moving fast, but pretty much all the libraries that we use, including PyTorch in particular, move fast. And so one of the things to do if you're watching this through the MOOC is to make sure that you go to course.fast.ai and check the links there, because there'll be links saying, oh, these are the differences from the course. And so they're kind of kept up to date so that you're never going to, because I can't edit what I'm saying. I can only edit that. Yeah. But yeah, do a git pull before you start each day. So I haven't actually updated all of the notebooks to add the extra return value. I will over the next couple of days, but if you're using them, you'll just need to put an extra comma NAs here. Otherwise, you'll get an error that it's returned 3 things and you only have room for 2 things. Okay. What I want to do, I think what I want to do before I talk about interpretation is to show you what the exact same process looks like when you're working with a really large data set. So And you'll see it's kind of almost the same thing, but there's going to be a few cases where we can't use the defaults because the defaults kind of like just run a little bit too slowly, right? So specifically, I'm going to look at the Kaggle groceries competition. Specifically, what's it called? Here it is. Comparación Favorita, grocery sales forecasting. So this competition, well, who is entering this competition? Okay, a lot of you. Who would like to have a go at explaining what this competition involves, what the data is and what you're trying to predict?
Okay, trying to predict the items on the shelf depending on lots of factors like oil prices.
When you say predicting the items on the shelf, what do you mean? What are you actually predicting?
How much they need to have in stock to maximize their, I guess.
It's not quite what we're predicting, but we'll try and fix that in a moment. So go on.
Yeah. And then there's a bunch of different data sets that you can use to do that. There's oil prices, there's stores, there's locations, and then each of those can be used to try to predict it.
Okay. Does anybody want to have a go at expanding on that? Let's go right with that.
All right. So we have a bunch of information on different products. So we have so for
Just
every.
Lift it up a little bit higher. Okay. Yeah.
All right. So for every store, for every item, for every day, we have a lot of related information available, like the location where the store was located, the class of the product, and the units sold. And then based on this, we are supposed to forecast in a much shorter time frame compared to the training data. For every item number, how much we think it's going to sell. So only the units and nothing else.
Okay, good. So somebody can help get that back here. So so your ability to explain the problem you're working on is really, really important. Okay, so if you don't currently feel confident of your ability to do that, practice, right, with someone who is not in this competition. Tell them all about it. So in this case, or in any case, really, the key things to understand a machine learning problem would be to say, what are the independent variables and what is the dependent variable? So the dependent variable is the thing that you're trying to predict. The thing you're trying to predict is how many units of each kind of product were sold in each store on each day during a 2-week period. So that's the thing that you're trying to predict. And the information you have to predict it is how many units of each product at each store on each day were sold in the last few years, and for each store, some metadata about it, like where is it located and what class of store is it. For each type of product, you have some metadata about it, such as what category of product is it, and so forth. For each date, we have some metadata about it, such as what was the oil price on that date. So this is what we would call a relational data set. So a relational data set is one where we have a number of different pieces of information that we can join together. Specifically, this kind of relational data set is what we would refer to as a star schema. A star schema is a kind of data warehousing schema where we basically say there's some central transactions table. And in this case, the central transactions table, if we go to the data section here, is train.csv, and it contains the number of units that were sold by date, by store ID, by item ID. Okay? So that's the central transactions table, very small, very simple. And then from that, we can join various bits of metadata. And it's called a star schema because you can kind of imagine the transactions table in the middle and then all these different metadata tables joined onto it, giving you more information about the date, the item ID, and the store ID. Okay? Sometimes you'll also see a snowflake schema, which means there might then be additional information joined onto maybe the the items table that tells you about different item categories, and join to the store table telling you about the state that the store's in, and so forth. So you can have like a kind of a whole snowflake. Right? So that's the basic information about this problem. Okay, the independent variables, the dependent variable, and you probably also want something about like things like the time frame. Okay. Now, we start in exactly the same way as we did before, loading in exactly the same stuff, setting the path. But when we go read CSV, if you say limit memory equals false, right, then you're basically saying use as much memory as you like to figure out what kinds of data is here. It's going to run out of memory, pretty much regardless of how much memory you have. So what we do in order to limit the amount of space that it takes up when we read it in is we create a dictionary for each column name to the data type of that column. Right? And so for you to create this, it's basically up to you to, run less or head or whatever on the data set to see what the types are and to figure that out and pass them in. So then you can just pass in dtype equals with that dictionary. And so check this out, right? We can read in the whole CSV file in 1 minute and 48 seconds. And there are 125.5 million rows. So like, when people say like Python's slow, no, Python's not slow. Python can be slow if you don't use it right. But we can actually parse 125 million CSV records in less than 2 minutes.
Put my language hat on for just a moment. Actually, if it's fast, almost certainly it's going to C.
Right.
Yeah, so Python is a wrapper around a bunch of C code usually.
Yeah, exactly.
So if Python itself isn't actually very fast.
Yeah. So that was Terence Parr, who writes things for writing programming languages for a living. So, and he is right. Python itself is not fast, but almost everything we want to do in Python in data science has been written for us in C, or actually more often in Python, which is a Python-like language which compiles to C. And so most of the stuff we run in Python is actually running not just C code, but actually in Pandas, a lot of it's written in like assembly language. It's heavily optimized. Behind the scenes, a lot of that is going back to actually calling Fortran-based libraries for linear algebra. So there's layers upon layer of speed that actually allow us to spend less than 2 minutes reading in that much data. Yeah, if we wrote our own CSV reader in pure Python, it would take, it takes thousands of times, at least thousands of times longer than the optimized versions. So for us, what we care about is the speed we can get in practice. And so this is pretty cool. As well as telling it what the different data types were, we also have to tell it, as before, which things do you want to parse as dates. Nice catch.
I've noticed that in this dictionary you specify int 64, int 33, and int 8. I was wondering in practice, is it like faster if you all specify them to int or slower, or like any performance consideration?
So the key performance consideration here was to use the smallest number of bits that I could to fully represent the column. So if I had used int 8 for item number, there are more than 255 item numbers. But more specifically, the maximum item number is bigger than 255. So on the other hand, if I had used int 64 for store number, it's using more bits than necessary. Given that the whole purpose here was to avoid running out of RAM, we don't want to be using up 8 times more memory than necessary. So the key thing was really about memory. And in fact, when you're working with large data sets, very often you'll find the slow piece is the actually reading and writing to RAM, not the actual CPU operations. So very often that's the key performance consideration. Also, however, as a rule of thumb, smaller data types often will run faster, particularly if you can use SIMD, so that's single instruction, multiple data, vectorized code. It can pack more numbers into a single vector to run at once.
Thank you.
Okay. That was all heavily simplified and not exactly right, but right enough, I think, for this purpose.
Once you do this, the shuffle thing beforehand is not needed anymore? Like maybe do a random subselection?
Yeah, so although here I've read in the whole thing, when I start, I never start by reading in the whole thing. So if you search the forum for SHUF, S-H-U-F, you'll find some tips about how to use this Unix command to get a random sample of data at the command prompt. And then you can just read that. And the nice thing is that way, like that's a good way, for example, to find out what data types to use, is to read in a random sample and let pandas figure it out for you. Oh, thank you. I think I'm still fine for this one. Yeah, and in general, I do as much work as possible on a sample until I feel confident that I understand the sample before I move on. So, yeah. Having said that, what we're about to learn is some techniques for running models on this full data set that are actually going to work on arbitrarily large data sets. And also, I specifically wanted to talk about how to read in large data sets. One thing to mention, on promotion objects are like saying create a general purpose Python data type which is slow and memory heavy. And the reason for that is that this is a Boolean which also has missing values. And so we need to deal with this before we can turn it into a Boolean. So you can see after that, I then go ahead and I say fill in the missing values with false. Now you wouldn't just do this without doing some checking ahead of time, but some exploratory data analysis shows that it seems that this is probably an appropriate thing to do. It seems that missing does mean false. Objects generally read in as strings, so replace the strings true and false with actual Booleans, and then finally convert it to an actual Boolean type. So at this point, when I save this, this file now of 123 million records takes up something under 2.5 gigabytes of memory. So like you can do, like run, look at pretty large data sets even on pretty small computers, which is interesting. So at that point, now that it's in a nice fast format, look how fast it is. I can save it to feather format in under 5 seconds. Okay, so that's nice. And then because pandas is generally pretty fast, you can do stuff like summarize every column of all 125 million records in 20 seconds. Okay, so the first thing I looked at here actually is the dates, right? Generally speaking, dates are just going to be really important in a lot of the stuff you do, particularly because any model that you put in practice, you're going to be putting it in at some date that is later than the date that you trained it, by definition, right? And so if anything in the world changes, you need to know how your predictive accuracy changes as well. And so what you'll see on Kaggle, and what you should always do in your own projects, is make sure that your dates don't overlap. So in this case, the dates that we have in the training set go from 2013 to mid-August 2017. Okay, there's our first and last. And then in our test set, they go from 1 day later, right, August the 16th, until the end of the month. So this is a key thing that, like, you can't really do any useful machine learning until you understand this basic piece here, which is you've got 4 years of data, and you're trying to predict the next 2 weeks. Okay, so like that's just a fundamental thing that you're going to need to understand before you can really do a good job of this. And so as soon as I see that, what does that say to you? If you wanted to now use a smaller data set, should you use a random sample, or is there something better you could do?
Probably from the bottom, more recent.
Yeah, get the most recent, right? And if you ever have trouble answering questions like this, just try to make it as physical as possible. So it's like, okay, I'm going to go to a shop next week and I've got a $5 bet with my brother as to whether I can guess how many cans of Coke are going to be on the shelf. All right, well, probably the best way to do that would be to go to the shop same day of the previous week and see how many cans of Coke are on the shelf and guess it's going to be the same. You wouldn't go and look at how many were there 4 years ago.
But couldn't 4 years ago, that same time frame of the year, be important? I mean, like, for example, how much Coke they have on the shelf at Christmas time is going to be way more than...
So, exactly. So, it's not that there's no useful information from 4 years ago, and so we don't want to entirely throw it away, but as a first step, like what is the simplest possible thing? It's kind of like submitting the means. I wouldn't submit the mean of 2012 sales. I would want to probably submit the mean of last month's sales, for example. So yeah, we're just trying to think about like how might we want to kind of create some initial easy models and later on, like we might want to weight it. So for example, we might want to weight more recent dates more highly. They're probably more relevant. But we should do a whole bunch of exploratory data analysis to check that. So here's what the bottom of that data set looks like. Okay, and you can see literally it's got a date, a store number, an item number, and unit sales, and tells you whether or not that particular item was on sale at that particular store on that particular date. And then there's some arbitrary ID, right? So that's it. So now that we have read that in, we can do stuff like, this is interesting, again we have to take the log of the sales, and it's the same reason as we looked at last week, right? Because we're trying to predict something that kind of varies according to ratios. They told us in this competition that the root mean squared log error is the thing they care about, so we take the log. They mentioned also, if you check the competition details, which you always should read carefully the definition of any project you do, they say that there are some negative sales that represent returns, and they tell us that we should consider them to be zero for the purpose of this competition. So I clip the sales so that they fall between 0 and no particular maximum. Okay, so clip just means cut it off at that point, truncate it. And then take the log of that plus 1. Why do I do plus 1? Because again, if you check the details of the chemical competition, that's what they tell you they're going to use, is they're not actually just taking the root mean squared log error, but the root mean squared log plus 1 error. Okay. Because log of 0 doesn't make sense. We can add the date part as usual, and again, it's taking a couple of minutes, right? So I would run through all this on a sample first, so everything takes 10 seconds to make sure it works, just to check everything looks reasonable before I go back, because I don't want to wait 2 minutes for something I don't know it's going to work. But as you can see, all these lines of code are identical to what we saw for the bulldozers competition. In this case, all I'm reading in is a training set. I didn't need to run train cats because all of my data types are already numeric. Okay. If they weren't, I would need to call train cats, and then I would need to call apply cats to apply the same categorical codes that I now have in the training set to the validation set. I call procdf as before to check for missing values and so forth. So all of those lines of code are identical. These lines of code, again, are identical because root mean squared error is still what we care about. And then I've got two changes. The first is set RF samples, which we learnt about last week. So we've got 120-something million records. We probably don't want to create a tree from 120 million something records, right? I don't even know how long that's going to take. I haven't had the time and patience to wait and see. So, you could start with 10,000 or 100,000, maybe it runs in a few seconds, make sure it works, and you can kind of figure out how much you can run. And so I found getting it to 1 million, it runs in under a minute, right? And so the point here is there's no relationship between the size of the data set and how long it takes to build the random forest. The relationship is between the number of estimators multiplied by the sample size. Okay? Yes.
Just curious what n jobs is, because in the past it's always been -1, and you made it 8 here.
Yeah, so the number of jobs is the number of cores that it's going to use. And I was running this on a computer that has about 60 cores, and I just found if you try to use all of them, it spent so much time spinning up jobs, so it was a bit slower. So if you've got like lots and lots of cores on your computer, sometimes you want less than -1 means use every single core.
Oh.
Yeah. There's one more change I made, which is that I converted the data frame into an array of floats, and then I fitted on that. Why did I do that? Because internally, inside the random forest code, they do that anyway, right? And so given that I wanted to run a few different random forests with a few different hyperparameters, by doing it once myself, I saved that minute 37 seconds, right? So if you run a line of code and it takes like quite a long time, so the first time I ran this random forest regressor, it kind of took 2 or 3 minutes, and I thought, I don't really want to wait 2 or 3 minutes. You can always add in front of the line of code %run. And what %run does is it runs something called a profiler. And what a profiler does is it'll tell you which lines of code behind the scenes took the most time, right? And in this case, I noticed that there was a line of code inside scikit-learn that was this line of code, and it was taking all the time, nearly all the time. And so I thought, oh, I'll do that first, and then I'll pass in the result, and I won't have to do it again, okay? So this thing of looking to see which things is taking up the time is called profiling, and in software engineering, it's one of the most important tools you have. Data scientists really underappreciate this tool, but you'll find like amongst conversations on GitHub issues or on Twitter or whatever amongst the top data scientists, they're sharing and talking about profiles all the time. And that's how easy it is to get a profile. So for fun, you know, try running prun from time to time on stuff that's taking 10, 20 seconds and see if you can learn to interpret and use profiler outputs. You know, even though in this case I didn't write this scikit-learn class, I was still able to use the profile to figure out how to make it run over twice as fast, right? By avoiding recalculating this each time. So in this case, I built my regressor. I decided to use 20 estimators. Something else that I noticed in the profiler is that I can't use OOB score when I use set RF samples. Because if I do, it's going to use the other 124 million rows to calculate the OOB score, which is like, again, it's still going to take forever. So I may as well have a proper validation set anyway. Besides which, I want a validation set that's the most recent dates rather than as random. So if you use set RF samples on a large data set, don't put the OOB score parameter in because it takes forever. So that got me a 0.76 validation root mean squared log error. And then I tried like fiddling around with different min samples. So if I decreased the min sample sleeve from 100 to 10, it took a little bit more time to run, as you would expect. And the error went down from 76 to 71. So that looked pretty good. So I kept decreasing it down to 3. And that brought this error down to 0.70. When I decreased it down to 1, it didn't really help. So I kind of had like a reasonable random forest here. When I say reasonable, though, it's not reasonable in the sense that it does not give a good result on the leaderboard. And so this is a very interesting question about why is that? And the reason is really coming back to Savannah's question earlier, like where might random forests not work as well? Let's go back and look at the data. Okay, here's the entire data set that well, not the whole data set. Here's all the columns that we used. So the columns that we have to predict with are the date, the store number, the item number, and whether it was on promotion or not. And then, of course, we used add date part, so there's also going to be day of week, day of month, day of year, is quarter, start, etc., etc. So if you think about it, most of the insight, around like how much of something do you expect to sell tomorrow is likely to be very wrapped up in the details about like where is that store, what kind of things do they tend to sell at that store, for that item, what category of item is it? If it's like fresh bread, they might not sell much of it on Sundays because on Sundays, fresh bread doesn't get made. Whereas if it's gasoline, maybe they're going to sell a lot of gasoline because on Sundays people go and fill up their car for the week ahead, right? Now, a random forest has no ability to do anything other than create a bunch of binary splits on things like day of week, store number, item number. It doesn't know which one represents gasoline. It doesn't know which stores are in the center of the city versus which ones are out in the sticks. It doesn't know any of these things. So its ability to really understand what's going on is somewhat limited. So we're probably going to need to use the entire 4 years of data to even get some useful insights. But then as soon as we start using the whole 4 years of data, a lot of the data we're using is really old. So interestingly, there's a Kaggle kernel that points out that what you could do is just take the last 2 weeks and take the average sales by date, by store number, by item number, and just submit that. And if you just submit that, you come about 30th. All right? So for those of you in the groceries, Terence has a comment or a question.
I think this may have tripped me up, actually. I think you said date, store, item. I think it's actually store, item, sales, and then you mean across date.
Oh, yeah, you're right. It's store, item, and on promotion.
Promotion, yes.
Yeah. If you do it by date as well, you end up. So each row represents basically like a cross tabulation of all of the sales on that date in that store for that item. So if you put date in there as well, there's only going to be 1 or 2 items being averaged in each of those cells, which is too much variation. Basically, it's too sparse. It doesn't give you a terrible result, but it's not 30th. So your job, if you're looking at this competition, and we'll talk about this in the next class, is how do you start with that model and make it a little bit better, right? Because if you can, then by the time we meet up next, hopefully you'll be above the top 30. Because, Kaggle being Kaggle, lots of people have now taken this kernel and submitted it, and they all have about the same score. And the scores are ordered not just by score, but by date submitted. So if you now submit this kernel, you're not going to be 30th because you're way down the list of when it was submitted. Right? But if you can do a tiny bit better, you're going to be better than all of those people. So try and think of how can you make this a tiny bit better. Yes,
could you try to capture seasonality and trend effects by creating new columns, like these are the average sales in the month of August, these are the average sales for this year?
Yeah, I think that's a great idea. So the thing for you to think about is how to do that, right? And so see if you can make it work, because there are details to get right, which, and I know Terence has been working on this for the last week and he's gone almost crazy. Right? The details crazier. The details are difficult. They're not difficult like intellectually difficult. They're kind of difficult in the way that makes you want to headbutt your desk at 2 a.m. And this is something to mention in general, is the coding you do for machine learning is it's incredibly frustrating and incredibly difficult. Not difficult technically, but difficult if you get a detail wrong, much of the time it's not going to give you an exception. It'll just silently be slightly less good than it otherwise would have been, right? And if you're on Kaggle, at least you know, okay, well, I'm not doing as well as other people on Kaggle, right? But if you're not on Kaggle, you just don't know. You don't know if your company's model is half as good as it could be because you made a little mistake, right? So That's why, one of the reasons why practicing on Kaggle now is great, right? Because you're going to get practice in finding all of the ways in which you can infuriatingly screw things up, right? And you'll be amazed. Like for me, there's an extraordinary array of them. But as you get to know what they are, you'll start to know how to check for them as you go, right? And so the only way, like you should assume every button you press, you're going to press the wrong button. Right? And that's fine as long as you have a way to find out. Okay, so we'll talk about that more during the course, but unfortunately there isn't like a set of specific things I can tell you to always do. You just always have to think like, okay, what do I know about the results of this thing I'm about to do? I'll give you a really simple example. If you've actually created that basic entry where you take the mean by date, by store number, by on promotion, right, and you've like submitted it and you've got a reasonable score, and then you think you've got something that's a little bit better, and you do predictions for that, how about you now create a scatter plot showing the predictions of your average model on one axis versus the predictions of your new model on the other axis? You should see that they just about form a line, right? And if they don't, then that's a very strong suggestion that you've screwed something up, right? So like that would be an example. Okay, can you pass that one to the end of that row? Possibly 2 steps. 1 step's enough.
Yeah, so for a problem like this, unlike the car insurance problem on Kaggle where columns are unnamed, we know we know what the columns represent and what they are. How often do you pull in data from other sources to supplement that? I mean, you could maybe like weather data, or for example, or how often is that used?
Very often, right? And so the whole point of this star schema is that you've got your central table and then you've got these other tables coming off it that provide metadata about it. So for example, weather is metadata about a date, right? Now, on Kaggle specifically, most competitions have the rule that you can use external data as long as you post on the forum that you're using it and that it's publicly available. But you have to check on a competition by competition basis, they will tell you. Outside of Kaggle, you should always be looking for like, what external data could I possibly leverage here? All right. Yes, sir. Because otherwise they can't hear on the recording.
Okay. So are we still talking about how to tweak this data set?
If you wish.
Well, I'm not familiar with the countries here, so maybe...
This is Ecuador.
Ecuador. So maybe I would...
It's Ecuador's largest grocery chain.
Ecuador's largest grocery chain. Maybe I would start looking for Ecuador's holidays and shopping holidays, maybe when they have a 3-day weekend or a week off.
And actually that information is provided in this case. And so in general, one way of tackling this kind of problem is to create lots and lots of new columns containing things like average number of sales on holidays, average percent change in sale between January and February, and so on and so forth. And so if you have a look at, there's been a previous competition on Kaggle called Rossmann store sales that was almost identical. It was in Germany, in this case, for a major grocery chain, how many items are sold by day, by item type, by store. And in this case, the person who won, quite unusually actually, was something of a domain expert in this space. They're actually a specialist in doing logistics predictions. And this is basically what they did was, he's a professional sales forecast consultant. He created just lots and lots and lots of columns based on his experience of what kinds of things tend to be useful for making predictions. So that's an approach that can work. The third place team did almost no feature engineering, however, and also they had one big oversight, which I think they would have won if they hadn't had it. So you don't necessarily have to use this approach. So we'll be learning a lot more about how to win this competition, and ones like it as we go. They did interview the third place team. So if you Google for Kaggle, Rossmann, you'll see it. The short answer is they use deep learning. So one of the things, and these are a couple of charts that, so Terence is actually my teammate on this competition. So Terence drew a couple of these charts for us, and I wanted to talk about this, which is if you don't have a good validation set, it's hard, if not impossible, to create a good model. So in other words, like if you're trying to predict next month's sales and you build a bunch, you try to build a model and you have no way of really knowing whether the models you built are good at predicting sales a month ahead of time, then you have no way of knowing when you put your model in production whether it's actually going to be any good, right? So you need a validation set that you know is reliable at telling you whether or not your model is likely to work well when you put it into production or use it on the test set. So in this case, what Terence has plotted here is, and so normally you should not use your test set for anything other than using it right at the end of the competition or right at the end of the project to find out how you've gone. But there's one thing I'm going to let you use the test set for in addition, and that is to calibrate your validation set. So what Terence did here was he built 4 different models, right? Some which he thought would be better than others, and he submitted each of the 4 models to Kaggle to find out its score. And so the x-axis is the score that Kaggle told us on the leaderboard, okay? And then on the y-axis, he plotted the score on a particular validation set he was trying out to see whether this validation set looked like it was going to be any good. Right. So if your validation set is good, then the relationship between the leaderboard score, i.e. the test set score, and your validation set score should lie in a straight line. Ideally, it'll actually lie on the y equals x line. Right? But honestly, that doesn't matter too much. As long as, relatively speaking, it tells you which models are better than which other models, then you know which model is the best, right? And you know how it's going to perform on the test set because you know the linear relationship between the two things. Okay. So in this case, Terence has managed to come up with a validation set which is looking like it's going to predict our Kaggle leaderboard score pretty well. And that's really cool, right? Because now he can go away and try 100 different types of models, feature engineering, weighting, tweaks, hyperparameters, whatever else, see how they go in the validation set, and not have to submit to Kaggle, right? So we're going to get a lot more iterations, a lot more feedback. Right? This is not just true of Kaggle, but every machine learning project you do. Right? And so if you find, so here's a different one he tried, right, where it wasn't as good, right? It's like, oh, these ones that were quite close to each other, it's showing us the opposite direction. That's a really bad sign. So it's like, okay, this validation set idea didn't seem like a good idea. This validation set idea didn't look like a good idea. And so in general, if your validation set's not showing a nice straight line, you need to think carefully. Like, okay, how is the test set constructed? How is my validation set different? There's some way you're constructing it which is different. You're going to have to draw lots of charts and so forth.
So one question is, and I'm going to try to guess how you did it. So how do you actually try to construct this validation set as close to the... So what I would try to do is to try to sample points from the training set that are very closer as possible to some of the points in the test set.
Close in what sense?
I don't know. I will have to find the features.
Well, in this case, for this groceries.
For this groceries, the last points.
Yeah, close by date. Yeah. So basically, all the different things Terence was trying were different variations of
something
close
like
by
that.
date. So the most recent.
Mm-hmm.
Yeah, what I noticed was, so first I looked at the date range of the test set, and then I looked at the kernel that described how
so
he or she...
Here's the date range of the test set. So the last 2 weeks of August 26, 2017.
That's right. And then the person who submitted the kernel that said how to get the 0.58 leaderboard position or whatever score.
The average by group. Yeah.
I looked at the date range of that. And That was
like 9 or 10 days. Right?
Well, it was actually 14 days,
14.
and the test set is 16 days.
Okay.
But the interesting thing is the test set begins on the day after payday and ends on the payday.
Ah.
And so these are things I also paid attention to.
And I think that's one of the bits of metadata that they told us, So these are the kinds of things you just got to try. Like I said, plot lots of pictures, and even if you didn't know it was payday, you would want to I would time series chart of sales, and you would hopefully see that every 2 weeks there would be a spike or whatever, and you'd be like, oh, I want to make sure that I have the same number of spikes in my validation set that I had in my test set, for example. Okay, let's take a 5-minute break, and let's come back at 2:32. Okay, so this is my favorite bit, interpreting machine learning models. And by the way, if you're looking for my notebook about the groceries competition, you won't find it in GitHub because I'm not allowed to share code for running competitions with you unless you're on the same team as me. That's the rule. After the competition is finished, it'll be on GitHub, however, so if you're doing this through the video, you should be able to find it. So let's start by reading in our feather file. So our feather file is exactly the same as our CSV file. This is for our Blue Book for Bulldozers competition. So we're trying to predict the sale price of heavy industrial equipment at auction. And so reading the feather format file means that we've already read in the CSV and processed it into categories. And so the next thing we do is to run procdf in order to turn the categories into integers, deal with the missing values, and pull out the dependent variable. Okay, this is exactly the same thing as we used last time to create a validation set, where the validation set represents the last couple of weeks, the last 12,000 records by date. And I discovered, thanks to one of your excellent questions on the forum last week, I had a bug here, which is that procdf was shuffling the order, sorry, not procdf. And last week we saw a particular version of procdf where we passed in a subset. And when I passed in the subset, it was randomly shuffling. And so then when I said split vals, it wasn't getting the last rows by date, but it was getting a random set of rows. So I've now fixed that. So if you rerun the lesson 1 RF code, you'll see slightly different results. Specifically, you'll see in that section that my validation set results look less good. But that's only for this tiny little bit where I had subset equals set. Yes, Chenshi.
I'm a little bit confused about the notation here. So NAS is both a input variable and it's also the output variable of this function. And
yeah.
Why is that?
The procdf returns a dictionary telling you which things were missing, which columns were missing, and for each of those columns what the median was. So when you call it on like the larger data set, the non-subset, you want to take that return value, right? And you don't pass in an NADIC to that point. You just want to get back the result. Later on, when you pass it into a subset, you want to have the same missing columns and the same medians, and so you pass it in. And if like this different subset, like if it was a whole different data set, turned out it had some different missing columns, it would update that dictionary with additional key values as well. So it kind of, you don't have to pass it in. If you don't pass it in, then it just gives you the information about what was missing and the medians. If you do pass it in, it uses that information for any missing columns that are there, and if there are some new missing columns, it'll update that dictionary with that additional information.
So it's like keeping all data sets, column information.
Yeah, it's going to keep track of all any missing columns that you came across in anything you passed across. Yeah.
Thank you.
Okay, so we split it into the training and test set just like we did last week. And so to remind you, once we've done PropDF, this is what it looks like. This is the log of sale price. Okay. So the first thing to think about is we already know how to get the predictions, right? Which is we take the average value in each leaf node in each tree after running a particular row through each tree, right? That's how we get the prediction. But normally we don't just want a prediction, we also want to know how confident we are of that prediction. And so we would be less confident of a prediction if we haven't seen many examples of rows like this one. And if we haven't seen many examples of rows like this one, then we wouldn't expect any of the trees to kind of have a path through which is really designed to help us predict that row. And so conceptually, you would expect then that as you pass this unusual row through different trees, it's kind of going to end up in very different places. So in other words, rather than just taking the mean of the predictions of the trees and saying that's our prediction, what if we took the standard deviation of the predictions of the trees? So the standard deviation of the predictions of the trees, if that's high, that means each tree is giving us a very different estimate of this row's prediction. So if this was a really common kind of row, right, then the trees will have learnt to make good predictions for it because it's seen lots of opportunities to split based on those kinds of rows, right? So the standard deviation of the predictions across the trees gives us some kind of at least relative understanding of how confident we are of this prediction. So that is not something which exists in scikit-learn or in any library I know of, so we have to create it. But we already have almost the exact code we need, because remember last lesson we actually manually calculated the averages across different sets of trees, so we can do exactly the same thing to calculate the standard deviations. So when I'm doing random forest interpretation, I pretty much never use the full data set. I always call set RF samples, because we don't need a massively accurate random forest. We just need one which indicates the nature of the relationships involved, right? And so I just make sure this number is high enough that if I call the same interpretation commands multiple times, I don't get different results back each time. That's like the rule of thumb about how big does it need to be, right? But in practice, 50,000 is a high number, and most of the time, it would be surprising if that wasn't enough, right? And it runs in seconds. So I generally start with 50,000. So with my 50,000 samples per tree set, I create 40 estimators. I know from last time that min samples leaf equals 3, max features equals 0.5 isn't bad. And again, we're not trying to create the world's most predictive tree anyway. So that all sounds fine. We get an R squared on the validation set of 0.89. Again, we don't particularly care, but as long as it's good enough, which it certainly is. And so here's where we can do that exact same list comprehension as last time. Remember, go through each estimator, that's each tree, call .predict on it with our validation set, make that a list comprehension, and pass that to np.stack, which concatenates everything in that list across a new axis. Okay. So now our rows are the results of each tree, and our columns are the result of each row in the original data set. And then we remember we can calculate the mean, right? So here's the prediction for our data set row number 1. And here's our standard deviation. Okay, so here's how to do it for just one observation, right, at the end here. We've calculated for all of them, just printing it for one here. Now, this this can take quite a while, and specifically, it's not taking advantage of the fact that my computer has lots of cores in it. List comprehensions, this is like, the list comprehension itself is Python code, right? It's my Python code. And Python code, unless you're doing special stuff, runs in serial, which means it runs on a single CPU. It doesn't take advantage of your multi-CPU hardware. And so if I wanted to run this, on more trees and more data, this 1 second is going to go up. And you see here the wall time, the amount of actual time it took, is roughly equal to the CPU time, whereas if it was running on lots of cores, the CPU time would be higher than the wall time. So it turns out that scikit-learn provides a handy, actually not scikit-learn, FastAI provides a handy function called parallel trees, which calls some stuff inside scikit-learn. And parallel trees takes two things. It takes a random forest model that I trained, here it is, M, and some function to call. And it calls that function on every tree in parallel. So in other words, rather than calling t.predict xvalid, let's create a function that calls t.predict xvalid. Let's use parallel trees to call it on our model for every tree. Okay, and it will return a list of the result of applying that function to every tree. And so then we can np.stack that. So hopefully you can see that that code and that code are basically the same thing, right? But this one is doing it in parallel. And so you can see here now our wall time has gone down to 500 milliseconds, and it's now giving us exactly the same answer. Okay, so a little bit faster. Time permitting, we'll talk about more general ways of writing code that runs in parallel, because it turns out to be super useful for data science. But here's one that we can use that's very specific to random forests. Okay, so what we can now do is we can always call this to get our predictions for each tree, and then we can call standard deviation to then get them for every row. And so let's try using that. So what I could do is let's create a copy of our data, and let's add an additional column to it, which is the standard deviation of the predictions across the first axis. Okay? And let's also add in the mean, so they're the predictions themselves. So you might remember from last lesson that one of the predictors we have is called enclosure, and we'll see later on that this is an important predictor. And so let's start by just doing a histogram. So one of the nice things in Pandas is it's got built-in plotting capabilities. It's well worth Googling for Pandas plotting to see how to do it. Yes, Terence?
Jeremy, can you remind me what enclosure is?
So we don't know what it means. And it doesn't matter, like that's the whole purpose of this process, is that we're going to figure out, we're going to learn about what things are, or at least what things are important, and we'll later on figure out what they are and how they're important. So we're going to start out knowing nothing about this data set, right? So there's something, so I'm just going to look at something called enclosure that has something called eRops and something called ORops, and I don't even know what this is yet. All I know is that the only three that really appear in any great quantity are ORops, eRops, WAC, and eRops. And this is like really common as a data scientist. You often find yourself looking at data that you're not that familiar with, and you've got to figure out at least like which bits to study more carefully and which bits seem to matter and so forth. So in this case, I at least know that these three groups I really don't care about because they basically don't exist. So given that, we're going to ignore those three. So we're going to focus on this one here, this one here, and this one here. And so here you can see what I've done is I've taken my data frame and I've grouped by enclosure, and I am taking the average of these three fields. So here you can see here's the average sale price, the average prediction, and the standard deviation of prediction for each of my three groups. So I can already start to learn a bit here. As you would expect, the prediction and the sale price are close to each other on average, so that's a good sign. And then the standard deviation varies a little bit. It's a little hard to see in a table, so what we could do is we could try to start like printing these things out. So here we've got the sale price for each level of enclosure, and here we've got the prediction for each level of enclosure, and for the error bars I'm using the standard deviation of prediction. Right, so here you can see the actual, and here's the prediction, and here's my confidence interval. Okay? Or at least it's the average of the standard deviation of the random forests. So this tells us, it'll tell us if there's some groups or some rows that we're not very confident of at all. So we could do something similar for product size, right? So here's different product sizes. We can do exactly the same thing of looking at our predictions and our standard deviations. Okay, we could sort by, and what we could say is like, well, what's the ratio of the standard deviation of the predictions to the predictions themselves, right? So you would kind of expect on average that when you're predicting something that's a bigger number, that your standard deviation would be higher, right? So you can like sort by that ratio. And what that tells us is that the product size large and product size compact, our predictions are less accurate, you know, as relatively speaking, as a ratio of the total price. And so then if we go back and have a look, well, there you go. That's why. From the histogram, those are the smallest groups. Okay, so as you would expect, in small groups, we're doing a less good job, right? So this confidence interval you can really use for two main purposes. One is that you can group it up like this and look at the average confidence interval by group to find out, are there some groups that you just don't seem to have confidence about those groups? But perhaps more importantly, you can look at them for specific rows. And so when you put it in production, you might always want to see the confidence interval. So if you're doing, say, your credit scoring, so deciding whether to give somebody a loan, you probably want to see not only what's their level of risk, but how confident are we? And if they want to borrow lots of money and we're not at all confident about our ability to predict whether they'll pay it back, we might want to give them a smaller loan. Okay, so those are the two ways in which you would use this. Okay, let me go to the next one, which is the most important. The most important is feature importance. And the only reason I didn't do this first is because I think the intuitive understanding of how to calculate confidence interval is the easiest one to understand intuitively. In fact, it's almost identical to something we've already calculated, right? But in terms of which one do I look at first in practice, I always look at this in practice. So when I'm working on, whether it be a Kaggle competition or a real-world project, I build a random forest as fast as I can, try and get it to the point that it's like, you know, significantly better than random, but doesn't have to be much better than that. And then the next thing I do is to plot the feature importance. And the feature importance tells us, in this random forest, which columns mattered, right? So we had like dozens and dozens of columns originally in this data set, and here I'm just picking out the top 10. So you can just call RF feature importance. Again, this is part of the FastAI library. It's leveraging stuff that's in scikit-learn. Pass in the model, pass in the data frame, because we need to know the names of the columns, right? And it'll tell you, it'll order, give you back a pandas data frame showing you in order of importance how important was each column. And here I'm just going to pick out the top 10. So we can then plot that, right? So fi, because it's a data frame, we can use data frame plotting commands. So here I've plotted all of the feature importances, right? And so you can see here, like, and I haven't been able to write all of the names of the columns at the bottom, which that's not the important thing. The important thing is to see that some columns are really, really important, and most columns don't really matter at all. And like in nearly every data set you use in real life, this is what your feature importance is going to look like. It's going to say there's like a handful of columns that you care about. And this is why I always start here, right? Because at this point, in terms of like looking into learning about this domain of heavy industrial equipment options, I only going to care about learning about the columns which matter, right? So are we going to bother learning about enclosure? Depends whether enclosure is important. And there it is. It's in the top 10. So we are going to have to learn about enclosure. Okay? So then we could also plot this as a bar plot. Right? So you can hear I've just created a tiny little function here that's going to just plot my bars, and I'm just going to do it for the top 30. And so you can see the same basic shape here, and I can see there's my enclosure. Okay, so we're going to learn about how this is calculated in just a moment. But before we worry about how it's calculated, much more important is to know what to do with it. So the most important thing to do with it is to now sit down with your client or your data dictionary or whatever your source of information is and say to them, okay, tell me about year made. What does that mean? Where does it come from? Plot lots of things like histograms of year made and scatter plots of year made against price and learn everything you can, because year made and coupler system, they're the things that matter, right? And what will often happen in real world projects is that you'll sit with the client and you'll say, oh, it turns out the coupler system is the second most important thing. And then they might say, that makes no sense. Now, that doesn't mean that there's a problem with your model. It means there's a problem with their understanding of the data that they gave you, right? So let me give you an example. I entered a Kaggle competition where the goal was to predict which applications for grants at a university would be successful. And I used this exact approach, and I discovered a number of columns which were almost entirely predictive of the dependent variable. And specifically, when I then looked to see in what way they were predictive, it turned out that whether they were missing or not was basically the only thing that mattered in this data set. And so later on, so I ended up winning that competition, and I think a lot of it was thanks to this insight, right? And so later on, I heard what had happened, and it turns out that at that university, there's an administrative burden to filling out the database. And so for a lot of the grant applications, they don't fill in the database for the folks whose applications weren't accepted, right? So in other words, these missing values in the data set were saying, okay, this grant wasn't accepted, because if it was accepted, then the admin folks are going to go in and type in that information. So this is what we call data leakage. And data leakage means there's information in the data set that I was modeling with, which the university wouldn't have had in real life at the point in time they were making a decision, right? So when they're actually deciding, which grant applications should I prioritize, they don't actually know which ones the admin staff are later on going to add information to because it turns out that they got accepted. You see what I mean? Right? So one of the key things you'll find here is data leakage problems, and that's a serious problem that you need to deal with. The other thing that will happen is you'll often find it's signs of collinearity. And I think that's what's happened here with coupler system. I think coupler system tells you whether or not a particular kind of heavy industrial equipment has a particular feature on it. But if it's not that kind of industrial equipment at all, it will be empty, it will be missing. And so coupler system is really telling you whether or not it's a certain class of heavy industrial equipment. Now, this is not leakage. This is actual information you actually have at the right time. It's just that, interpreting it, you have to be careful, okay? So I would go through at least the top 10 or kind of look for where the natural breakpoints are and really study these things carefully. To make life easier for myself, what I tend to do is I try to throw some data away and see if that matters. So in this case, I had a random forest, which, let's go and see how accurate it was, 0.889. What I did was I said here, okay, well, let's go through our feature importance data frame and filter out those where the importance is greater than 0.005. right? So 0.025, so 0.005 is about here, right? It's kind of like where they really flatten off, right? So let's just keep those. And so that gives us a list of 25 column names. And so then I say, okay, let's now create a new data frame view, which just contains those 25 columns. Call split vals on it again, split it into test and training set, and create a new random forest. And let's see what happens. And you can see here the R squared basically didn't change. 891 versus 889. So it's actually increased a tiny bit, right? I mean, generally speaking, removing redundant columns, it shouldn't make it worse. If it makes it worse, they weren't redundant after all. It might make it a little better, because if you think about how we built these trees, when it's deciding what to split on, it's got less things to have to worry about trying. It's less often going to accidentally find a crappy column. So it's got a slightly better opportunity to create a slightly better tree with slightly less data, but it's not going to change it by much. But it's going to make it a bit faster, and it's going to let us focus on what matters. So if I rerun feature importance now, I've now got 25. Now the key thing that's happened is that when you remove redundant columns, is that you're also removing sources of collinearity. Right? In other words, two columns that might be related to each other. Now, collinearity doesn't make your random forest less predictive, but if you have two columns that are related to each other, this column's a little bit related to this column, and this column's a strong driver of the dependent variable, then what's going to happen is that the importance is going to end up kind of split between the two collinear columns. It's going to say well, both of those columns matter, so it's going to split it between the two. So by removing some of those columns with very little impact, it makes your feature importance plot clearer. And so you can see here, actually, year made was pretty close to coupler system before, but there must have been a bunch of things that were collinear with year made, which makes perfect sense, right? Like old industrial equipment wouldn't have had a bunch of kind of technical features that new ones would, for example. So it's actually saying oh, okay, year made really, really matters, right? So I trust this feature importance better. The predictive accuracy of the model is a tiny bit better, but this feature importance has a lot less collinearity to confuse us. So let's talk about how this works. And it's actually really simple. And not only is it really simple, it's a technique you can use not just for random forests, but for basically any kind of machine learning model. And interestingly, almost no one knows that. Many people will tell you, oh, this particular kind of model, there's no way of interpreting it. And the most important interpretation of a model is knowing which things are important. And that's almost certainly not going to be true, because this technique I'm going to teach you actually works for any kind of model. So here's what we're going to do. We're going to take our data set, the bulldozers, right? And we've got this column which we're trying to predict, right? Which is price. And then we've got all of our independent variables. Okay, so here's an independent variable here, year made, right? Plus a whole bunch of other variables. And remember, after we did a bit of trimming, we had 25 independent variables. Okay. How do we figure out how important year made is? Well, we've got our whole random forest, right? And we can find out our predictive accuracy. So we're going to put all of these rows through our random forest. And we're going to spit out some predictions. Right, and we're going to compare them to the actual price to get, in this case, for example, our root mean squared error and our R squared. And we're going to call that, that's our starting point, right? So now, let's do exactly the same thing, but let's take the year made column and randomly shuffle it. So randomly permute just that column. So now, year made has exactly the same distribution as before, same mean, standard deviation, but it's going to have no relationship to the dependent variable at all, because we totally randomly reordered it. So before, we might have found our R squared was 0.89, right? And then after we shuffle year made, we check again, and now it's like 0.8. Like, oh, our score got much worse when we destroyed that variable. And it's like, okay, let's try again. Let's put year made back to how it was. And this time, let's take enclosure and shuffle that. Right? And we find this time with enclosure, it's 0.84. And we can say, oh, okay, so the amount of decrease in our score for year made was 0.09, and the amount of decrease in our score for enclosure was 0.05. Right? And this is going to give us our feature importances for each one of our columns. Yes.
Wouldn't just excluding, let's say, each column and running a random forest and checking the decay in the performance?
Yeah, so you could remove the column and train a whole new random forest, but that's going to be really slow. Whereas this way, we can keep our random forest and just test the predictive accuracy of it again. Right, so this is nice and fast by comparison. In this case, we just have to rerun every row forward through the forest for each shuffled column.
I see. We're just basically doing predictions after
Exactly.
shuffling. Okay.
Yeah, great question.
So if you want to do like multi-collinearity, would you do 2 of them and then random shuffle and then 3 of them random shuffle? Like that
Yeah, so I mean, I don't think you mean multicollinearity. I think you mean looking for interaction effects. Yeah, so if you want to say which pairs of variables are most important, you could do exactly the same thing, each pair in turn. In practice, there are better ways to do that because that's obviously computationally pretty expensive. And so we'll try and find time to do that if we can. Okay. So we now have a model which is a little bit more accurate and we've learned a lot more about it. So we're out of time, and so what I would suggest you try doing now before the next class for this bulldozers data set is like go through the top, I don't know, 5 or 10 predictors and try and learn what you can about how to draw plots in pandas, and try to come back with like some insights about like what's the relationship between year made and the dependent variable, what's the histogram of year made, try and find, some possible, like, now that you know year made is really important, is there some noise in that column which we could fix? Are there some weird encodings in that column that we could fix? This idea I had that maybe coupled system is there entirely because it's collinear with something else. Do you want to like try and figure out whether that's true? If so, how would you do it? FI product class desk, that rings alarm bells for me. It sounds like it might be a high cardinality categorical variable. It might be something with lots and lots of levels because it sounds like it's like a model name. So like go and have a look at that model name. Does it have some ordering to it? Could you make it an ordinal variable to make it better? Does it have some kind of hierarchical structure in the string that we could split it on like hyphen to create more subcolumns? Have a think about this, and so try and make it so that, by Tuesday when you come back, you've got some new, ideally you've got a better accuracy than what I just showed because you found some new insights, or at least that you can tell the class about some things you've learnt about how heavy industrial equipment options work in practice. Okay? Great. See you on Tuesday. All right, welcome back. Something to mention, somebody asked on the forums, really good question, was like, how do I deal with version control and notebooks? The question was something like, every time I change the notebook, Jeremy goes and changes it on Git, and then I do a Git pull, and I end up with a conflict, and blah, blah, blah. And that happens a lot with notebooks, because notebooks behind the scenes are JSON files, which like every time you run even a cell without changing it. It updates that little number saying like what numbered cell this is, and so now suddenly there's a change. And so trying to merge notebook changes is a nightmare. So my suggestion, like a simple way to do it is when you're looking at some notebook, like lesson 2, RF interpretation, you want to start playing around with this. First thing I would do would be to go File, make a copy, and then in the copy say File Rename, and give it a name that starts with TMP, and that will hide it from Git, right? And so now you've got your own version of that notebook that you can play with, okay? And so if you now do a Git pull and see that the original changed, it won't conflict with yours, and you can now see there are 2 different versions. There are different ways of kind of dealing with this Jupyter Notebook Git problem, like everybody has it. One is there are some hooks you can use that like remove all of the cell outputs before you commit to Git. But in this case, I actually want the outputs to be in the repo so you can read it on GitHub and see it. So it's a minor issue, but it's something which catches everybody. Yes, Terrence.
Before we move on to interpretation of the random forest model, I wonder if we could summarize the relationship between the hyperparameters on the random forest and its effect on, overfitting and dealing with collinearity and yada, yada, yada.
Yeah, that sounds like a question born from experience. Absolutely. So I'm going to go back to lesson 1 RF. If you're ever unsure about where I am, you can always see my top here, courses ML1, lesson 1 RF. In terms of the hyperparameters that are interesting, and I'm ignoring like pre-processing, but just the actual hyperparameters. The first one of interest, I would say, is the set RF samples command, which determines how many rows are in each sample, so in each tree, created from how many rows.
Is that tree or nodes?
In each tree. Right. So before we start a new tree, we either bootstrap a sample, so sampling with replacement from the whole thing, or we pull out a subsample of a smaller number of rows, and then we build a tree from there. So step 1 is we've got our whole big data set, and we grab a few rows at random from it, and we turn them into a smaller data set, and then from that we build a tree, right? So that's the size of that is set RF samples. So when we change that size, let's say this originally had like 1 million rows, and we said set RF samples 20,000, right? And then we're going to grow a tree from there. Assuming that the tree remains kind of balanced as we grow it, can somebody tell me how many layers deep would this tree be? And assuming we're growing it until every leaf is of size 1. Yes?
Log base 2.
Log base 2 of 20,000. Right. Okay. So the depth of the tree doesn't actually vary that much depending on the number of samples, right? Because it's related to the log of the size. Can somebody tell me at the very bottom, so once we go all the way down to the bottom, how many leaf nodes would there be? Speak up. What? 20,000, right? Because every single leaf node has a single thing in it. So we've got obviously a linear relationship between the number of leaf nodes and the size of the sample. So when you decrease the sample size, it means that there are less kind of final decisions that can be made, right? So therefore the tree is going to be less rich in terms of what it can predict because it's just making less different individual decisions. And it also is making less binary choices to get to those decisions. So therefore, setting RF samples lower is going to mean that you overfit less, but it also means that you're going to have a less accurate individual tree model, right? And so remember, the way Bryman, the inventor of random forest, described this is that you're trying to do two things when you build a model, with bagging. One is that each individual tree, or as sklearn would say, each individual estimator is as accurate as possible, right, on the training set. So it's like each model is a strong predictive model. But then across the estimators, the correlation between them is as low as possible, so that when you average them out together, you end up with something that generalizes. So by decreasing the set RF samples number, we are actually decreasing the power of the estimator and increasing the correlation. And so is that going to result in a better or a worse validation set result for you? It depends, right? This is the kind of compromise which you have to figure out when you do machine learning models. Can you pass that back there?
If I put the OOB value equal to 2, so it is basically dividing every third. It ensures that every 37% of the data won't be there in each tree, right?
The OOB, say again?
OOB, if I put OOB equal to true in random forest, so isn't that make sure that out of my entire data, 37% of data won't be there in every tree?
So all OOB equals true does is it says whatever your subsample is, it might be a bootstrap sample or it might be a subsample, take all of the other rows, right, and put them into for each tree, and put them into a different data set and calculate the error on those. So it doesn't actually impact training at all. It just gives you an additional metric, which is the OOB error. So if you don't have a validation set, then this allows you to get kind of a quasi-validation set for free.
If I don't set RF sample, what will be the default?
If you what, sorry?
If I don't set RF sample.
Set out of sample?
If I don't set
RF sample?
Yeah.
So the default is actually if you say reset RF samples, and that causes it to bootstrap. So it'll sample a new data set as big as the original one, but with replacement. Okay, so obviously the second benefit of set RF samples is that you can run more quickly, and particularly if you're running on a really large data set, like 100 million rows, it won't be possible to run it on the full data set. So you would either have to pick a subsample yourself before you start, or use set RF samples. The second key parameter that we learnt about was min samples leaf. Okay, so if I changed min samples leaf, before we assumed that min samples leaf was equal to 1. All right, if I set it equal to 2, then what would be my new depth? How deep would it be? Yes, log base 2, 20,000 minus 1. Okay, so each time we double the min samples leaf, we're removing one layer from the tree. Fang, I'll come back to you again since you're doing so well. How many leaf nodes would there be in that case? Fang? How many leaf nodes would there be in that case? 10,000. Okay, so we're going to be, again, dividing the number of leaf nodes by that number. So the result of increasing min samples leaf is that now each of our leaf nodes has more than one thing in, so we're going to get a more stable average that we're calculating in each tree. Okay. We've got a little bit less depth. Okay, we've got less decisions to make, and we've got a smaller number of leaf nodes. So again, we would expect the result of that would be that each estimator would be less predictive, but the estimators would be also less correlated. So again, this might help us to avoid overfitting. Could you pass the microphone over here, please?
Hi, Jeremy. I'm not sure if, in that case, every node will have exactly two
No,
observations.
it won't necessarily have exactly two, and I thank you for mentioning that. So it might try to do a split. And so one reason, well, what would be an example, Chen-Shi, that you wouldn't split even if you had 100 nodes? What might be a reason for that? Sorry, 100 items in a leaf node.
They're identical.
They're all the same. They're all the same in terms of
Well, one's
the independent or the dependent?
The dependent.
In terms of the dependent, right? I mean, I guess either, but much more likely would be the dependent. So if you get to a leaf node where every single one of them has the same auction price, or in classification, like every single one of them is a dog, then there is no split that you can do that's going to improve your information, right? And remember, information is the term we use in a kind of a general sense in random forest to describe the amount of difference, about additional information we create from a split is like how much are we improving the model. So you'll often see this word information gain, which means like how much better did the model get by adding an additional split point. And it could be based on RMSE, or it could be based on cross entropy, or it could be based on how different are the standard deviations or whatever. So that's just a general term. Okay, so that's the second thing that we can do, which again, it's going to speed up our training because it's like one less set of decisions to make. Remember, even though there's one less set of decisions, those decisions like have as much data again as the previous set. So like each layer of the tree can take like twice as long as the previous layer. So it could definitely speed up training, and it could definitely make it generalize better. So then the third one that we had was max features. Who wants to tell me what max features does? Do you want to pass that back over there? Okay, Vinay.
So max features determines how many features you're going to use in each tree. In this case, it's a fraction, half. So you're going to use half the features for each tree.
Nearly right, or kind of right. Can you be more specific, or can somebody else be more specific? It's not exactly for each tree, Chen-Shi.
Is it for each tree randomly sample half of the features?
So not quite. It's not for each tree. So the set, do you want to pass it to Kerem? So the set RF samples picks a subset of samples, a subset of rows for each tree. But min samples leaf, but max features doesn't quite do that. It does something different.
At each split, we will be
at each split. It will
pick randomly half.
Yeah, right.
Columns.
So it kind of sounds like a small difference, but it's actually quite a different way of thinking about it, which is we do our set RF samples. So we pull out our subsample or our bootstrap sample, and that's kept for the whole tree. And we have all of the columns in there, right? And then with max features equals 0.5, at each point, at each split, we pick a different half of the features. And then here we'll pick a different half of the features. And here we'll pick a different half of the features. And so the reason we do that is because we want the trees to be as rich as possible, right? So particularly like if you were only doing a small number of trees, like you had only 10 trees, and you picked the same column set all the way through the tree, you're not really getting much variety in what kind of things it can find. Okay, so this way, at least in theory, seems to be something which is going to give us a better set of trees. It's picking a different random subset of features at every decision point.
The overall effect.
So the overall effect of max features, again, it's the same. It's going to mean that each individual tree is probably going to be less accurate, but the trees are going to be more varied. And in particular here, this can be critical because, like, imagine that you've got one feature that's just super predictive. It's so predictive that, like, every random subsample you look at always starts out by splitting on that same feature. Then the trees are going to be very similar in the sense like they all have the same initial split, right? But there may be some other interesting initial splits because they create different interactions of variables. So by like half the time, that feature won't even be available at the top of the tree. So at least half the trees are going to have a different initial split. So it definitely can give us more variation, and therefore, again, it can help us to create more generalized trees that have less correlation with each other, even though the individual trees probably won't be as predictive. In practice, we actually looked at, have a little picture of this, that as you add more trees, right, if you have max features equals none, that's going to use all the features every time, right? Then with like very, very few trees, that can still give you a pretty good error. But as you create more trees, it's not going to help as much because they're all pretty similar because they're all trying every single variable. Whereas if you say max features equals square root or max features equals log 2, then as we add more estimators, we see improvements. Okay, so there's an interesting interaction between those two. And this is from the sklearn docs, this cool little chart. Okay. So then things which don't impact our training at all, njobs simply says how many CPU, how many cores do we run on. Okay, so it'll make it faster up to a point. Generally speaking, making this more than like 8 or so may have diminishing returns. -1 says use all of your cores. So there's I don't know why the default is to only use one core. That seems weird to me. You'll definitely get more performance by using more cores because all of you have computers with more than one core nowadays. And then OOB score equals true simply allows us to see the OOB score. If you don't say that, it doesn't calculate it. And particularly if you had set RF samples pretty small compared to a big data set, OOB is going to take forever to calculate. Hopefully at some point we'll be able to fix the library so that doesn't happen. There's no reason it need be that way, but right now that's how the library works. Okay. So there are key basic parameters that we can change. There are more that you can see in the docs or shift tab to have a look at them. But the ones you've seen are the ones that I've found useful to play with. So feel free to play with others as well. And generally speaking, max features of, as I said, max features of like either none means all of them, about 0.5 or square root or log, kind of those trees seem to work pretty well. And then for min samples leaf, I would generally try kind of 1, 3, 5, 10, 25, 100. And like as you start doing that, if you notice by the time you get to 10, it's already getting worse, then there's no point going further. If you get to 100, it's still going better, then you can keep trying, right? But they're the kind of general amounts that most things seem to sit in. All right. So random forest interpretation is something which you could use to create some really cool Kaggle kernels. Now, obviously, one issue is the FastAI library is not available in Kaggle kernels, but if you look inside fastai.structured, right, and remember you can just use double question mark to look at the source code for something, or you can go into the editor to have a look at it. You'll see that most of the methods we're using are a small number of lines of code in this library and have no dependencies on anything. So you could just copy that little, if you need to use one of those functions, just copy it into your kernel. And if you do, just say, this is from the FastAI library. You can link to it on GitHub because it's available on GitHub as open source, but you don't need to import the whole thing, right? So this is a cool trick, is that because you're the first people to learn how to use these tools, you can start to show things that other people haven't seen, right? So, for example, this confidence based on tree variance is something which doesn't exist anywhere else. Feature importance definitely does, and that's already in quite a lot of Kaggle kernels. If you're looking at a competition or a data set where nobody's done feature importance, being the first person to do that is always going to win lots of votes because it's like the most important thing. Is like which features are important. So last time let's just make sure we've got our tree and our data. So we need to change this to add one extra thing. All right, so that's going to load in our data. Split. There's our data. Okay. So as I mentioned, when we do model interpretation, I tend to set RF samples to some subset, something small enough that I can run a model in under 10 seconds or so, because there's just no point running a super accurate model. 50,000 is more than enough to see. You'll basically see each time you run an interpretation, you'll get the same results back. And so as long as that's true, then you're already using enough data. Okay. So feature importance, we learnt it works by randomly shuffling a column, each column one at a time, and then seeing how accurate the model, the pre-trained model, the model we've already built is, when you pass it in all the data as before, but with one column shuffled. So some of the questions I got after class kind of reminded me that it's very easy to underappreciate how powerful and kind of magic this approach is. And so to explain, I'll mention a couple of the questions that I heard. So one question was like, why don't we, or what if we just took one column at a time and created a tree on just each one column at a time? So we've got our data set, it's got a bunch of columns, so why don't we just like grab that column and just build a tree from that, right? And then like we'll see which column's tree is the most predictive. Can anybody tell me why that may give misleading results about feature importance? Karen.
I also asked this question.
Okay.
So we will be going to lose the interactions between the features.
Yeah.
If we just shuffle them, it will be at randomness, and we will able to both capture the interactions and the importance of the feature at the same
Great.
time.
Yeah. And so this issue of interactions is not a minor detail. It's like, it's massively important. So like think about this bulldozers data set where, for example, where there's one field called year made and there's one field called sale date. And like, if we think about it, it's pretty obvious that what matters is the combination of these two, which in other words is like, how old is the piece of equipment when it got sold? So if we only included one of these, we're going to massively underestimate how important that feature is. Now, here's a really important point though. It's pretty much always possible to create a simple like logistic regression, which is as good as pretty much any random forest, if you know ahead of time exactly what variables you need, exactly how they interact, exactly how they need to be transformed, and so forth, right? So in this case, for example, we could have created a new field which was equal to year made, sale date or sale year minus year made, and we could have fed that to a model and got that interaction for us. But the point is, we never know that. Like you never, like you might have a guess about, I think some of these things are interacted in this way, and I think this thing we need to take the log and so forth. But, the truth is that the way the world works, the causal structures, they've got many, many things interacting in many, many subtle ways, right? And so that's why using trees, whether it be gradient boosting machines or random forests, works so well. So, can you pass that to Terence, please?
One thing that bit me years ago was also, I tried that, doing one variable at a time, thinking, oh, well, I'll figure out which one's most correlated with the dependent variable. But what it doesn't pull apart is that what if all variables are basically a copy of the same variable? Then they're all going to seem equally important, but in fact, it's really just one factor.
Yeah, and that's also true here. So if we had like a column appeared twice, right? Then shuffling that column isn't going to make the model much worse, right? There'll be, if you think about like how it was built, some of the times, particularly if we had like max features is 0.5, then some of the times we're going to get version A of the column, some of the times we're going to get version B of the column. So like half the time, shuffling version A of the column is going to make a tree a bit worse. Half the time it's going to make, column B will make it a bit worse. And so it'll show that both of those features are somewhat important, and it'll kind of like share the importance between the two features. And so this is why I write collinearity, but collinearity literally means that they're linearly related. So this isn't quite right. But this is why having two variables that are closely related to each other, or more variables that are closely related to each other, means that you will often underestimate their importance using this random forest technique. Yes, Terence.
And so once we've shuffled and we get a new model, what exactly are the units of these importances? Is this a change in the R squared?
Yeah, I mean, it depends on the library we're using. So the units are kind of like, I never think about them. I just kind of know that like in this particular library, 0.005 is often kind of a cutoff I would tend to use, but all I actually care about is this picture, right, which is the feature importance ordered for each variable, and then kind of zooming in, turning it into a bar plot, and I'm kind of like, okay, here they're all pretty flat, and I can see, okay, that's about 0.005, and so I remove them at that point and just see like the model, hopefully the validation score didn't get worse. And if it did get worse, I'll just decrease this a little bit until it doesn't get worse. So yeah, the units of measure of this don't matter too much. And we'll learn later about a second way of doing variable importance, by the way. Can you pass that over there?
Is one of the goals here to remove variables that I guess your score will not get worse if you remove them, so you might as well get rid of them?
Yeah, so that's what we're going to do next. So, having looked at our feature importance plot, we said, okay, it looks like the ones like less than 0.005, are kind of this long tail of boringness. So I said, let's try removing them, right? So let's just try grabbing the columns where it's greater than 0.005. And I said, let's create a new data frame called df keep, which is df train with just those kept columns. Created a new training and validation set with just those columns. Created a new random forest. And I looked to see how the validation set score and the validation set RMSE changed. And I found they got a tiny bit better. So if they're about the same or a tiny bit better, then my thinking is, well, this is just as good a model, but it's now simpler. And so now when I redo the feature importance, there's less collinearity, right? And so in this case, I saw that year made went from being like quite a bit better than the next best thing, which was coupler system, to way better than the next best thing, right? And coupler system went from being like quite a bit more important than the next two to equally important to the next two. So it did seem to definitely change these feature importances and hopefully give me some more insight there.
So how does that help our model in general? Like, what does it mean that year made is now way ahead of the others? Like, what does
so we're going to dig into that kind of now. But basically, it tells us that, for example, if we're looking for like how are we dealing with missing values, is there noise in the data, if it's a high cardinality categorical variable, they're all different steps we would take. So, for example, if it was a high cardinality categorical variable that was originally a string, right? Like, for example, I think like maybe FI product class description. I remember one of the ones we looked at the other day had like, first of all, was the type of vehicle and then a hyphen and then like the size of the vehicle. We might look at that and be like, okay, well, that was an important column. Let's try like splitting it into two on hyphen and then take that bit, which is like the size of it, and try and, parse it and convert it into an integer. We can try and do some feature engineering. And basically, until you know which ones are important, you don't know where to focus that feature engineering time. You can talk to your client, and say, or if you're doing this inside your workplace, you go and talk to the folks that are responsible for creating this data. So if you were actually working at a bulldozer auction company, you might now go to the actual auctioneers and say, I'm really surprised that coupler system seems to be driving people's pricing decisions so much. Why do you think that might be? And they can say to you, oh, it's actually because only these classes of vehicles have coupler systems, or only this manufacturer has coupler systems. And so frankly, this is actually not telling you about coupler systems, but about something else. And oh, hey, that reminds me, that's something else. We actually have measured that. It's in this different CSV file. I'll go get it for you. So it kind of helps you focus your attention.
So I had a fun little problem this weekend. As you know, I introduced a couple of crazy computations into my random forest, and all of a sudden they're like, oh my God, these are the most important variables ever, squashing all of the others. But then I got a terrible score. And then is that because, now that I think I have my scores computed correctly, what I noticed is that the importance went through the roof, but the validation set was still bad or got worse. Is that because somehow that computation allowed the training to, almost like an identifier, map exactly what the answer was going to be for training, but of course that doesn't generalize to the validation set? Is that what I observed?
Okay, so there's two reasons why your validation score might not be very good. Let's go up here. Okay, so we get these 5 numbers, right? The RMSE of the training, validation, R squared of the training, validation, and the R squared of the OOB. Okay, so there's 2 reasons, and really in the end what we care about, like for this Kaggle competition, is the RMSE of the validation set, assuming we've created a good validation set. So in Terence's case, he's saying this number, this thing I care about, got worse when I did some feature engineering. Why is that? Okay, there's 2 possible reasons. Reason 1 is that you're overfitting. If you're overfitting, then your OOB will also get worse. If you're doing a huge data set with a small set RF sample so you can't use an OOB, then instead create a second validation set, which is a random sample, okay, and do that, right? So in other words, if your OOB or your random sample validation set has got much worse, then you must be overfitting. I think in your case, Terence, it's unlikely that's the problem, because random forests don't overfit that badly. Like, it's very hard to get them to overfit that badly unless you use some really weird parameters, like only one estimator, for example. Like, once you've got 10 trees in there, there should be enough variation that you can definitely overfit, but not so much that you're going to destroy your validation score by adding a variable. So I think you'll find that's probably not the case, but it's easy to check. And if it's not the case, then you'll see that your OOB score or your random sample validation score hasn't got worse. Okay, so the second reason your validation score can get worse, if your OOB score hasn't got worse, you're not overfitting, but your validation score has got worse, that means you're doing something that is true in the training set, but not true in the validation set. So this can only happen when your validation set is not a random sample. So for example, in this bulldozers competition or in the grocery shopping competition, we've intentionally made a validation set that's for a different date range. It's for the most recent 2 weeks, right? And so if something different happened in the last 2 weeks to the previous weeks, then you could totally break your validation set. So for example, if there was some kind of unique identifier, which is like different in the two date periods, then you could learn to identify things using that identifier in the training set, but then like the last 2 weeks may have a totally different set of IDs with a different set of behavior, could get a lot worse. Yeah. What you're describing is not common though, and so I'm a bit skeptical it might be a bug, but hopefully there's enough things you can now use to figure out if it is a bug. We'll be interested to hear what you learn. Okay, so that's feature importance, and so I'd like to compare that to how feature importance is normally done in industry and in academic communities outside of machine learning, like in psychology and economics and so forth. And generally speaking, people in those kind of environments tend to use some kind of linear regression, logistic regression, general linear models. So they start with their data set and they basically say, well, that was weird. Oh, okay. So they start with their data set and they say, I'm going to assume that I know the kind of parametric relationship between my independent variables and my dependent variable. So I'm going to assume that it's a linear relationship, say, or it's a linear relationship with a link function like a sigmoid to create logistic regression, say. And so assuming that I already know that, I can now write this as an equation. So if I've got like x1, x2, so forth, right? I can say, all right, my y values are equal to ax1 plus bx2 equals y, and therefore I can find out the feature importance easily enough by just looking at these coefficients and saying like which one's the highest, particularly if you've normalized the data first, right? So there's this kind of trope out there, it's very common, which is that like this is somehow more accurate or more pure or in some way better way of doing feature importance. But that couldn't be further from the truth, right? If you think about it, if you were missing an interaction, right? Or if you were missing a transformation you needed, or if you've any way been anything less than 100% perfect in all of your pre-processing so that your model is the absolute correct truth of this situation, right? Unless you've got all of that correct, then your coefficients are wrong, right? Your coefficients are telling you in your totally wrong model, this is how important those things are, right? Which is basically meaningless. So where I'll say the random forest feature importance, it's telling you in this extremely high parameter, highly flexible functional form with few if any statistical assumptions, this is your feature importance, right? So I would be very cautious, you know, and again, I can't stress this enough. When you leave MSAN, when you leave this program, you are much more often going to see people talk about logistic regression coefficients than you're going to see them talk about random forest variable importance. And every time you see that happen, you should be very, very, very skeptical of what you're seeing. Anytime you read a paper in economics or in psychology, or the marketing department tells you they did this regression or whatever, every single time those coefficients are going to be massively biased by any issues in the model. Furthermore, if they've done so much pre-processing that actually the model's pretty accurate, then now you're looking at coefficients that are going to be of like a coefficient of some principal component from a PCA, or a coefficient of some distance from some cluster or something, at which point they're very, very hard to interpret anyway. They're not actual variables, right? So they're kind of the two options I've seen when people try to use classic statistical techniques to do a kind of a variable importance equivalent. I think things are starting to change slowly. You know, there are some fields that are starting to realize that this is totally the wrong way to do things, but it's been, you know, nearly 20 years since random forests appeared. So it takes a long time. You know, people say that the only way that knowledge really advances is when the previous generation dies. And that's kind of true, right? Like particularly academics, you know, they make a career of being good at a particular sub thing, and you know, often it's not until the next generation comes along that people notice that, oh, that's actually no longer a good way to do things. And I think that's what's happened here. Okay. So we've got now a model which isn't really any better as a predictive accuracy-wise, but it's kind of, we're getting a good sense that there seems to be like 4 main important things. When it was made, the coupler system, its size, and its product classification. Okay, so that's cool. There is something else that we can do, however, which is we can do something called one-hot encoding. So this is where we're talking about categorical variables. So remember, a categorical variable, let's say we had like a string, high, and remember the order we got was kind of back weird. It was high, low, medium. So it was in alphabetical order by default. Right? Was our original category for like usage band or something? And so we mapped it to 0, 1, 2, right? And so by the time it gets into our data frame, it's now a number. So the random forest doesn't know that it was originally a category. It's just a number, right? So when the random forest is built, it basically says, oh, is it greater than 1 or not? Or is it greater than 0 or not? You know, basically the 2 possible decisions it could have made. For something with like 5 or 6 spans, you know, it could be that just one of the levels of a category is actually interesting, right? So like if it was like very high, very low, or unknown, right? Then we've now got like 6 levels, and maybe the only thing that mattered was whether it was like unknown. Maybe like not knowing its size somehow impacts the price. And so if we wanted to be able to recognize that, and particularly if like it just so happened that the way that the numbers were coded was that unknown ended up in the middle, right? Then what it's going to do is it's going to say, okay, there is a difference between these 2 groups, you know, less than or equal to 2 versus greater than 2. And then when it gets into this leaf here, it's going to say, oh, there's a difference between these 2, between less than 4 and greater than or equal to 4. And so it's going to take 2 splits to get to the point where we can see that it's actually unknown that matters. So this is a little inefficient, and we're kind of like wasting tree computation. And like wasting tree computation matters because every time we do a split, we're halving the amount of data, at least, that we have to do more analysis. So it's going to make our tree less rich, less effective if we're not giving the data in a way that's kind of convenient for it to do the work it needs to do. So what we could do instead is create 6 columns. We could create a column called is very high, is very low, is high, is unknown, is low, is medium. And each one would be 1s and 0s, right? It's either 1 or 0. So we had 6 columns. Just one moment. So having added 6 additional columns to our data set, the random forest now has the ability to pick one of these and say like, oh, let's have a look at is unknown. There's one possible split I can do, which is 1 versus 0. Let's see if that's any good, right? So it actually now has the ability in a single step to pull out a single category level. And so this kind of coding is called one-hot encoding. And for many types of machine learning model, this is like necessary. Something like this is necessary. Like if you're doing logistic regression, you can't possibly put in a categorical variable that goes 0 through 5 because there's obviously no linear relationship between that and anything, right? So one-hot encoding, a lot of people incorrectly assume that all machine learning requires one-hot encoding. But in this case, I'm going to show you how we could use it optionally and see whether it might improve things sometimes. Yeah.
Hi, Jeremy. So if we have 6 categories, like in this case, would there be any problems with adding a column for each of the categories? So, because in linear regression, we said we had to do it, like if there's 6 categories, we should only do it for 5 of them.
Yeah, so you certainly can say, oh, let's not worry about adding is medium because we can infer it from the other 5. I would say include it anyway, because like rather than otherwise the random forest would have to say is very high no, is very low no, is high no, is unknown low, is low no, okay, and finally I'm there, right? So it's like 5 decisions to get to that point. So the reason in linear models that you need to not include one is because linear models hate collinearity. But we don't care about that here. So we can do one-hot encoding easily enough, and the way we do it is we pass one extra parameter to procdf, which is what's the max number of categories, right? So if we say it's 7, then anything with less than 7 levels is going to be turned into a one-hot encoded bunch of columns, right? So in this case, this has got 6 levels, so this would be one-hot encoded, whereas like zip code has more than 6 levels, and so that would be left as a number. And so generally speaking, you obviously probably wouldn't want to one-hot encode zip code, right? Because that's just going to create masses of data, memory problems, computation problems, and so forth, right? So this is like another parameter that you can play around with. So if I do that, try it out, run the random forest as per usual, you can see what happens to the R squared of the validation set and to the RMSE of the validation set. And in this case, I found it got a little bit worse. This isn't always the case, and it's going to depend on your data set. You know, do you have a data set where single categories tend to be quite important, or not? And in this particular case, it didn't make it more predictive. However, what it did do is that we now have different features, right? So procdf puts the name of the variable and then an underscore and then the level name. And so interestingly, it turns out that whereas before it said that enclosure was somewhat important, when we do it as one-hot encoded, it actually says enclosure eRops with a C is the most important thing. So for at least the purpose of like interpreting your model, you should always try one-hot encoding, quite a few of your variables. And so I often find somewhere around 6 or 7 is pretty good. You can try like making that number as high as you can so that it doesn't take forever to compute, and the feature importance doesn't include like really tiny levels that aren't interesting. So that's kind of up to you to play around with. But in this case, like this is actually, I found this very interesting. It clearly tells me I need to find out what enclosure eRops with AC is. Why is it important? Because like it means nothing to me, right? But it's the most important thing, so I should go figure that out. Savannah had a question. Can you plus that?
So can you explain how changing the max number of categories works? Because for me, it just seems like there's 5 categories, there's 5 categories.
Oh, yeah, sorry. So it's just like, all it's doing is saying like, okay, here's a column called zip code. Here's a column called usage band. And here's a column sex, right? I don't know, whatever, right? And so like zip code has whatever, 5,000 levels. The number of levels in a category, we call its cardinality. Okay. So it has a cardinality of 5,000. Usage band maybe has a cardinality of 6. Sex has maybe a cardinality of 2. So when procdf goes through and says, okay, this is a categorical variable, should I one-hot encode it? It checks the cardinality against max n cats and says, oh, 5,000 is bigger than 7, so I don't one-hot encode it. And then it goes to usage band. 6 is less than 7, I do one-hot encode it. Goes to sex, 2 is less than 7, I do one-hot encode it. So it just says for each variable, how do I decide whether to one-hot encode it or not?
In procdf, we are keeping both label encodes and one-hot encodes, right?
No, once we decide to one-hot encode, it does not keep the original variable.
Wouldn't the fact that maybe the best split will be an interval, and we would need a label encode?
Well, you don't need a label encode. If the best is an interval, it can approximate that with multiple one-hot encoding levels.
So in terms of efficiency, it will be.
Yeah. So, like, it's the truth is that each column is going to have some, different, should it be label encoded or not, which you could make on a case-by-case basis. I find in practice, it's just not that sensitive to this, and so I find like just using a single number for the whole data set gives me what I need. But, if you were building a model that really had to be as awesome as possible and you had lots and lots of time to do it, you can go through don't use procdf. You can go through manually and decide which things to use dummies or not. You'll see in the code, if you look at the code for procdf, right? Like, I never want you to feel like the code that happens to be in the FastAI library is the code that you're limited to, right? So where is that done? You can see that the max ncat gets passed to numericalize, and numericalize simply checks, okay, is it a numeric type, and is the number of categories either not been passed to us at all, or we've got more unique values than there are categories, and if so, we're going to use the categorical codes. So for any column where where it's skipped over that, right, so it's remained as a category, then at the very end we just go pandas.getDummies, we pass in the whole data frame. And so pandas.getDummies, you pass in the whole data frame, it checks for anything that's still a categorical variable, and it turns it into a dummy variable, which is another way of saying a one-hot encoding. So, with that kind of approach, you can easily override it and do your own dummy verification, variabilization. Did you have a question?
So some data has a quite obvious order, like if you have like a rating system like good, bad, poor, whatever, things like that. There's an order to that, and showing that order by doing the dummy variable thing probably will work in your benefit. So is there a way to just force it to leave alone one variable, just like convert it beforehand yourself?
Not in the library. And to remind you, like, unless we explicitly do something about it, we're not going to get that order. So when we import the data, so this is in lesson 1 RF, we showed how by default the categories are ordered alphabetically, and we have the ability to order them properly. So yeah, if you've actually made an effort to turn your ordinal variables into proper ordinals, using procdf can destroy that if you have max ncats. So the simple way to avoid that is if we know that we always want to use the codes for usage band rather than the, like never one-hot encode it, you could just go ahead and replace it, right? You could just say, okay, let's just go df.usageband equals df.usageband.cat.codes, and it's now an integer. And so it'll never get changed. All right. So we kind of have already seen how variables which are basically measuring the same thing can kind of confuse our variable importance. And they can also make our random forest slightly less good because it requires like more computation to do the same thing. There's more columns to check. So I've got to do some more work to try and remove redundant features. And the way I do that is to do something called a dendrogram. And it's a kind of hierarchical clustering. So cluster analysis is something where you're trying to look at objects. They can be either rows in a data set or columns, and find which ones are similar to each other. So often you'll see people particularly talking about cluster analysis. They normally refer to rows of data, and they'll say like, oh, let's plot it, right? And like, oh, there's a cluster, and there's a cluster, right? A common type of cluster analysis, time permitting, we may get around to talking about this in some detail, is called k-means, which is basically where you assume that you don't have any labels at all, and you take basically a couple of data points at random, and you gradually find the ones that are near to it and move them closer and closer to centroids, and you kind of repeat it again and again. And it's an iterative approach that you basically tell it how many clusters you want, and it'll tell you where it thinks the clusters are. A really, I don't know why, but a really underused technique, 20, 30 years ago, it was much more popular than it is today, is hierarchical clustering. Hierarchical. Also known as agglomerative clustering. And in hierarchical or agglomerative clustering, we basically look at every pair of objects and say, okay, which two objects are the closest, right? So in this case, we might go, okay, those two objects are the closest. And so we kind of like delete them and replace it with the midpoint of the two. And then, okay, here are the next two closest. We delete them and replace them with the midpoint of the two. And you keep doing that again and again, right? Since we're kind of removing points and replacing them with their averages, you're gradually reducing the number of points by pairwise combining. And the cool thing is you can plot that like so, right? So if rather than looking at points, you look at variables, we can say, okay, which two variables are the most similar? And it says, okay, sale year and sale elapsed are very similar. So the kind of horizontal axis here is how similar are the 2 points that are being compared, right? So if they're closer to the right, it means they're very similar. So sale year and sale elapsed have been combined, and they were very similar.
What are you measuring? What is this similarity?
Again, it's like, who cares? You know, it'll be like a correlation coefficient or something like that. You know, in this particular case, what I actually did, so you get to tell it. So in this case, I actually used Spearman's R. So you guys familiar with correlation coefficients already? Correlation. So correlation is almost exactly the same as the R squared, right? But it's between two variables rather than a variable and its prediction. The problem with a normal correlation is that if the, I'll create a new workbook here. If you have data that looks like this, then you can do a correlation and you'll get a good result, right? But if you've got data which looks like this, right, and you try and do a correlation, it assumes linearity. That's not very good, right? So there's a thing called a rank correlation, a really simple idea. It's replace every point by its rank, right? So instead of like, so we basically say, okay, this is the smallest, so we'll call that 1, 2, there's the next one, 3, here's the next one, 4, 5, right? So you just replace every number by its rank, right? And then you do the same for the y-axis. So we'll call that 1, 2, 3, and so forth, right? And so then you do like a new plot where you don't plot the data, but you plot the rank of the data. And if you think about it, the rank of this data set is going to look an exact line, because every time something was greater on the x-axis, it was also greater on the y-axis. So if we do a correlation on the rank, that's called a rank correlation. Okay? So because I want to find the columns that are similar in a way that the random forest would find them similar, random forests don't care about linearity, they just care about ordering, so a rank correlation is the right way to think about that. So Spearman's R is the name of the most common rank correlation, but you can literally replace the data with its rank and chuck it at the regular correlation, and you'll get basically the same answer. The only difference is in how ties are handled. It's a pretty minor issue.
Like if you had like a full parabola in that rank correlation, you will not rely
Right.
on,
It has to be monotonic.
Okay.
Yeah. Okay. So once I've got a correlation matrix, there's basically a couple of standard steps you do to turn that into a dendrogram, which I have to look up on Stack Overflow each time I do it. You basically turn it into a distance matrix, and then you create something that tells you, which things are connected to which other things hierarchically. So this kind of, these two and this step here are like just 3 standard steps that you always have to do to create a dendrogram. And so then you can plot it. All right, so sale year and sale elapsed seem to be measuring basically the same thing, at least in terms of rank, which is not surprising, because sale elapsed is the number of days since the first day in my data set. So obviously these two are nearly entirely correlated with some ties. Grouse attracts and hydraulics flow and coupler system all seem to be measuring the same thing. And this is interesting because remember, coupler system, it said, was super important. Right? And so this rather supports our hypothesis that it's nothing to do with whether it's a coupler system, but whether it's whatever kind of vehicle it is that has these kind of features. Product group and product group's desk seem to be measuring the same thing. FI base model and FI model desk seem to be measuring the same thing. And so once we get past that, everything else, like suddenly the things are further away. So I'm probably going to not worry about those. So we're going to look into these 1, 2, 3, 4 groups that are very similar. Could you pass that over there?
Is it implied in that graph that the similarity between stick length and enclosure is higher than with stick length and anything that's higher?
Yeah, pretty much. I mean, it's a little hard to interpret, but given that stick length and enclosure don't join up until way over here, it would strongly suggest that they're a long way away from each other. Otherwise, you would expect them to have joined up earlier. I mean, it's possible to construct like a synthetic data set where you kind of end up joining things that were close to each other through different paths. So you've got to be a bit careful, but I think it's fair to probably assume that stick length or enclosure are probably very different.
So they are very different, but would they be more similar than, for example, stick length and sale day of year?
Sale day of
which
year.
Is at the very top.
No, there's nothing to suggest that here, because like the key point is to notice where they sit in this tree, right? And they sit in totally different halves of the tree.
Okay, thank you.
But really, to actually know that, the best way would be to actually look at the Spearman R correlation matrix, right? If you just want to know how similar is this thing to this thing, the Spearman R correlation matrix tells you that. Can you pass that over there?
So to this we are passing the data frame, right?
Say again?
We are passing the data frame, or are we passing the model to it?
This is just a data frame. So we're passing in df keep. So that's the data frame containing the, whatever it was, 30 or so features that our random forest thought was interesting. So there's no random forest being used here. The measure, the distance measure is being done entirely on rank correlation. So what I then do is I take these groups, right? And I create a little function that I call get out of band score, right? Which is, it does a random forest for some data frame. I make sure that I've taken that data frame and split it into a training and validation set. And then I call fit and return the OOB score, right? So basically what I'm going to do is I'm going to try removing each one of these 1, 2, 3, 4, 5, 6, 7, 8, 9 or so variables one at a time and see which ones I can remove and it doesn't make the OOB score get worse. And And each time I run this, I get slightly different results. So actually, it looks like last time I had 7 things, not 8 things. So you can see I just do a loop through each of the things that I'm thinking, like maybe I could get rid of this because it's redundant. And I print out the column name and the OOB score of a model that is trained after dropping that one column. Okay, so the OOB score on my whole data frame is 0.89. And then after dropping each one of these things, basically none of them get much worse. Sale elapsed is getting quite a bit worse than sale year. But like it looks like pretty much everything else I can drop with like only like a 3rd decimal place problem. So obviously though, you've got to remember the dendrogram, like let's take FI model desk and FI base model, right? They're very similar to each other, right? So what this says isn't that I can get rid of both of them, right? I can get rid of one of them because they're basically measuring the same thing, okay? So then I try it. I say, okay, let's try getting rid of one from each group, sale year, FI base model, and Grouser tracks, okay? And like, let's now have a look. It's like, okay, I've gone from 0.890 to 0.888. It's like, again, so close as to be meaningless. So that sounds good. Simpler is better. So I'm now going to drop those columns from my data frame. And then I can try running the full model again. And I can see, so reset RF samples means I'm using my whole data frame, my whole bootstrap sample, use 40 estimators, and I've got 0.907. Okay, so I've now got a model which is smaller and simpler, and I'm getting a good score for. So at this point, I've now got rid of as many columns as I feel I comfortably can, ones that either didn't have a good feature importance or were highly related to other variables, and the model didn't get worse significantly when I removed them. So now I'm at the point where I want to try and really understand my data better by taking advantage of the model. And we're going to use something called partial dependence. And again, this is something that you could use in a Kaggle kernel, and lots of people are going to appreciate this because almost nobody knows about partial dependence. And it's a very, very powerful technique. What we're going to do is we're going to find out, for the features that are important, how do they relate to the dependent variable, right? So let's have a look, right? So let's, again, since we're doing interpretation, we'll set RF samples to 50,000 to run things quickly. We'll take our data frame, we'll get our feature importance, and notice that we're using max and cat because I'm actually pretty interested in terms of for interpretation and seeing the individual levels. And so here's the top 10. And so let's try and learn more about those top 10. So year made is the second most important. So one obvious thing we could do would be to plot year made against sale elapsed. Because as we've talked about already, it just seems to make sense. They're both important, but it seems very likely that they kind of combine together to find how old was the product when it was sold. So we could try plotting year made against sale elapsed to see how they relate to each other. And when we do, we get this very ugly graph. And it shows us that year made actually has a whole bunch that are 1,000, right? So clearly, this is where I would tend to go back to the client or whatever and say, okay, I'm guessing that these bulldozers weren't actually made in the year 1000. And they would presumably say to me, oh yes, they're ones where we don't know when it was made. Maybe before 1986, we didn't track that. Or maybe things that are sold in Illinois don't have that data provided, or whatever. They'll tell us some reason. So in order to understand this plot better, I'm just going to remove them from this interpretation section of the analysis. So I'm just going to say, okay, let's just grab things where year made is greater than 1930. Okay. So let's now look at the relationship between year made and sale price. And there's a really great package called ggplot ggplot originally was an R package. GG stands for the grammar of graphics. And the grammar of graphics is like this very powerful way of thinking about how to produce charts in a very flexible way. I'm not going to be talking about it much in this class. There's lots of information available online, but I definitely recommend it as a great package to use. ggplot, which you can pip install, it's part of the FastAI environment already. ggplot in Python has basically the same parameters and API as the R version. The R version is much better documented, so you should read its documentation to learn how to use it. But basically you say, okay, I want to create a plot of this data frame. Now, when you create plots, most of the data sets you're using are going to be too big to plot. As in, like, if you do a scatter plot, it'll create so many dots that it's just a big mess. It'll take forever. And remember, when you're plotting things, you're looking at it, right? So there's no point plotting something with 100 million samples when if you only used 100,000 samples, it's going to be pixel identical, right? So that's why I call get sample first. So get sample just grabs a random sample. Okay, so I'm just going to grab 500 points for now. Okay, so I'm going to grab 500 points from my data frame. I got a plot. Year made against sale price. AES stands for aesthetic. This is the basic way that you set up your columns in ggplot. Okay, so this says to plot these columns from this data frame, and then there's this weird thing in ggplot where plus means basically add chart elements. Okay, so I'm going to add a smoother. So most of very, very often you'll find that a scatter plot is very hard to see what's going on because there's too much randomness, whereas a smoother basically creates a little linear regression for every little subset of the graph. And so it kind of joins it up and allows you to see a nice smooth curve. Okay, so this is like the main way that I tend to look at univariate relationships. And by adding standard error equals true, it also shows me the confidence interval of this smoother, right? So low S stands for locally weighted regression, which is this idea of doing lots of little linear regressions. So we can see here the relationship between year made and sale price is kind of all over the place, right? Which is like not really what I would expect. I would have expected that more recent stuff that's sold more recently would probably be like more expensive because of inflation and because they're like more current models and so forth. And the problem is that when you look at a univariate relationship like this, there's a whole lot of collinearity going on, a whole lot of interactions that are being lost. So for example, why did the price drop here? Is it actually because like things made between 1991 and 1997 are less valuable? Or is it actually because most of them were also sold during that time and actually there was like maybe a recession then? Or maybe it was like the product sold during that time, a lot more people were buying types of vehicle that were less expensive. Like there's all kinds of reasons for that. And so again, as data scientists, one of the things you're going to keep seeing is that at the companies that you join, people will come to you with these kind of univariate charts where they'll say like, oh my God, our sales in Chicago have disappeared. They've got really bad. Or people aren't clicking on this ad anymore. And they'll show you a chart that looks like this. And they'll be like, what happened? And most of the time, you'll find the answer to the question, what happened, is that there's something else going on, right? So actually, in Chicago last week, actually, we were doing a new promotion, and that's why our revenue went down. It's not because people aren't buying stuff in Chicago anymore. It's because the prices were lower, for instance. So what we really want to be able to do is say, well, what's the relationship between sale price and year made, all other things being equal? So all other things being equal basically means if we sold something in 1990 versus 1980 and it was exactly the same thing to exactly the same person in exactly the same auction, so on and so forth, what would have been the difference in price? And so to do that, we do something called a partial dependence plot. And this is a partial dependence plot. There's a really nice library which nobody's heard of called PDP, which does these partial dependence plots. And what happens is this. We've got our sample of 500 data points, right? And we're going to do something really interesting. We're going to take each one of those 100 randomly chosen auctions, and we're going to make a little data set out of it, right? So like here's our come on, one more. Here's our data set of like 500 auctions. And here's our columns, one of which is the thing that we're interested in, which is year made. So here's year made. Okay, and what we're going to do is we're now going to try and create a chart where we're going to try and say, all other things being equal, in 1960, how much did bulldozers cost? How much did things cost in auctions? And so the way we're going to do that is we're going to replace the year made column with 1960. We're going to copy in the value 1960 again and again and again all the way down, right? So now every row, the year made is 1960. And all of the other data is going to be exactly the same. And we're going to take our random forest, and we're going to pass all this through our random forest to predict the sale price. So that will tell us, for everything that was auctioned, how much do we think it would have been sold for if that thing was made in 1960? And that's what we're going to plot here. All right, that's the price we're going to plot here. And then we're going to do the same thing for 1961. All right, we're going to replace all these and do 1961. Yeah.
So, well, to be clear, we've already fit the random forest.
Yes.
And then we're just passing a new year and seeing what it determines the price should be?
Yeah, so this is a lot like the way we did feature importance. But rather than randomly shuffling the column, we're going to replace the column with a constant value. Right? So randomly shuffling the column tells us how accurate it is when you don't use that column anymore. Replacing the whole column with a constant tells us, or estimates for us, how much we would have sold that product for in that auction, on that day, in that place, if that product had been made in 1961. Right? So we basically then take the average of all of the sale prices that we calculate from that random forest. And so we do it in 1961, and we get this value, right? So what the partial dependence plot here shows us is each of these light blue lines actually is showing us all 500 lines. So it says for row number 1 in our data set, if we sold it in 1960, we're going to index that to 0, right? So we'll call that 0, right? If we sold it in 1970, that particular auction would have been here. If we sold it in 1980, it would have been here. If we sold it in 1990, it would have been here. So we actually plot all 500 predictions of how much every one of those 500 auctions would have gone for if we replace its year made with each of these different values. And then this dark line here is the average, right? So this tells us how much would we have sold on average all of those auctions for if all of those products were actually made in 1985, 1990, 1993, 1994, and so forth. And so you can see what's happened here is, at least in the period where we have a reasonable amount of data, which is since 1990, this is basically a totally straight line, which is what you would expect, right? Because if it was sold on the same date, and it was the same kind of tractor, and it was sold to the same person in the same auction house, then you would expect more recent vehicles to be more expensive because of inflation and because they're newer, right? They're not as secondhand. And you would expect that relationship to be roughly linear. And that's exactly what we're finding. Okay. So by removing all of these externalities, it often allows us to see the truth much more clearly. There's a question at the back. Can you pass that back there? You're done. Okay. So this partial dependence plot concept is something which is using a random forest to get us a more clear interpretation of what's going on in our data. And so the steps were to, first of all, look at the feature importance to tell us, like, which things do we think we care about, and then to use the partial dependence plot to tell us what's going on average, right? There's another cool thing we can do with PDP is we can use clusters. And what clusters does is it uses cluster analysis to look at all of these, each one of the 500 rows, and say, do some of those 500 rows kind of move in the same way? And like we can kind of see, it seems like there's a whole lot of rows that kind of go down and then up, and there seems to be a bunch of rows that kind of go up and then go flat. Like it does seem like there are some kind of different types of behaviors being hidden. And so here is the result of doing that cluster analysis, right? Is we still get the same average, but it says here are kind of the 5 most common shapes that we see. And this is where you could then go in and say, all right, it looks like some kinds of vehicle, actually after 1990, their prices are pretty flat. And before that, they were pretty linear. Some kinds of vehicle are kind of exactly the opposite. And so like different kinds of vehicle have these different shapes, right? And so this is something you could dig into. I think there was one at the back. Oh, you could. Okay.
So what are we going to do with this information?
Well, the purpose of interpretation is to learn about a data set. And so why do you want to learn about a data set? It's because you want to do something with it, right? So in this case, it's not so much something if you're trying to win a Kaggle competition. I mean, it can be a little bit, like some of these insights might make you realize, oh, I could transform this variable or create this interaction or whatever. Obviously, feature importance is super important for Kaggle competitions. But this one's much more for like real life, you know? So this is when you're talking to somebody and you say to them like, okay, those plots you've been showing me, which actually say that like there was this kind of dip in prices, you know, based on like things made between 1990 and 1997. There wasn't really, you know, actually they were increasing. There was actually something else going on at that time. You know, it's basically the thing that allows you to say like, for whatever this outcome I'm trying to drive in my business is, this is how something's driving it, right? So if it's like, I'm looking at, you know, kind of advertising technology, what's driving clicks, then I'm actually digging in to say, okay, this is actually how clicks are being driven. This is actually the variable that's driving it. This is how it's related. So therefore we should change our behavior in this way. That's really the goal of any model. I guess there's 2 possible goals. One goal of a model is just to get the predictions. Like if you're doing hedge fund trading, you probably just want to know what the price of that equity is going to be. If you're doing insurance, you probably just want to know how much claims that guy's going to have. But probably most of the time, you're actually trying to change something about how you do business, how you do marketing, how you do logistics. So the thing you actually care about is how the things are related to each other.
All right, I'm sorry, can you explain again, when you scroll up and you were looking at the sale price year May, looking at the entire model, and you saw that dip, just the graph right above, and you said something about that dip didn't signify what we thought it did. Can you explain why you got that?
So this is like a classic, boring univariate plot, right? So this is basically just taking all of the dots, all of the options, plotting year made against sale price, and we're going to just fitting a rough average through them. And so it's true that products made between 1992 and 1997, on average in our data set, are being sold for less. So like very often in business, you'll hear somebody look at something like this and they'll be like, oh, we should stop auctioning equipment that is made in that year, in those years, because like we're getting less money for example. But if the truth actually is that during those years, it's just that people were making more small industrial equipment, where you would expect it to be sold for less, and actually our profit on it is just as high, for instance. Or during those years, it's not things made during those years now would have would be cheaper. It's that during those years, when we were selling things in those years, they were cheaper because like there was a recession going on. So if you're trying to like actually take some action based on this, you probably don't just care about the fact that things made in those years are cheaper on average, but how does that impact today? You know, so this approach where we actually say, let's try and remove all of these externalities. So if something is sold on the same day to the same person of the same kind of vehicle, then actually how does year made impact price? And so this basically says, for example, if I am deciding what to buy at an auction, then this is kind of saying to me, okay, like getting a more recent vehicle on average really does, on average, give you more money, which is not what the kind of the naive univariate plot said. Can you pass it to Tyler?
For like this bulldozer, bulldozers made in 2010 probably are not close to the type of bulldozers that were made in 1960.
Right.
And if you're taking something that would be so very different, like a 2010 bulldozer, and then trying to just drop it to say, oh, if it was made in 1960, that may cause poor prediction at a point because it's so far outside of any training.
Absolutely. So, you know, I think that's a good point. It's, you know, it's a limitation of a random forest is if you've got a kind of data point that's like of a kind, you know, which is kind of like in a part of the space that it's not seen before. Like maybe people didn't put air conditioning really in bulldozers in 1960, and you're saying how much would this bulldozer with air conditioning have gone for in 1960? You don't really have any information to know that. So, you know, this is still the best technique I know of, but it's not perfect. And, you know, you kind of hope that the trees are still going to find some useful truth, even though it hasn't seen that combination of features before. But yeah, it's something to be aware of. So you can also do the same thing in a PDP interaction plot. And a PDP interaction plot, which is really what I'm trying to get to here, is like how does sale elapsed and year made together impact price. And so if I do a PDP interaction plot, it shows me sale elapsed versus price, it shows me year made versus price, and it shows me the combination versus price. Remember, this is always log of price. That's why these prices look weird, right? And so you can see that the combination of sale elapsed and year made is, as you would expect, later dates, so more elapsed time, is giving me, oh, sorry, it's the other way around, isn't it? So the highest prices are those where there's the least elapsed and the most recent year made. So you can see here, there's the univariate relationship between sale elapsed and price. And here is the univariate relationship between year made and price. And then here is the combination of the two. It's enough to see like clearly that these two things are driving price together. You can also see these are not like simple diagonal lines, so it's kind of some interesting interaction going on. And so based on looking at these plots, it's enough to make me think, oh, we should maybe put in some kind of interaction term and see what happens. So let's come back to that in a moment, but let's just look at a couple more. Remember in this case, I did one hot encoding way back at the top here. I said max n cat equals 7. So I've got like n closure erops with AC. So if you've got one hot encoded variables, you can pass an array of them to plot PDP, and it'll treat them as a category, right? And so in this case, I'm going to create a PDP plot of these three categories. I'm going to call it enclosure. And I can see here that enclosure erops with AC on average are more expensive than enclosure erops. and enclosure OROPs. It actually looks like enclosure OROPs and enclosure EROPs are pretty similar, whereas EROPs with AC is higher. So this is, at this point, I'd probably be inclined to hop into Google and like type EROPs and OROPs and find out what the hell these things are. And here we go. So it turns out that EROPs is enclosed rollover protective structure. And so it turns out that if your bulldozer is fully enclosed, then optionally you can also get air conditioning. So it turns out that actually this thing is telling us whether it's got air conditioning. If it's an open structure, then obviously you don't have air conditioning at all. So that's what these three levels are. And so we've now learnt, all other things being equal, the same bulldozer sold at the same time, built at the same time, sold to the same person is going to be quite a bit more expensive if it has air conditioning than if it doesn't. Okay, so again, we're kind of getting this nice interpretation ability. And, now that I've spent some time with this data set, I've certainly noticed that this, knowing this is the most important thing, you do notice that there's a lot more air-conditioned bulldozers nowadays than there used to be, and so there's definitely an interaction between kind of date and that. So based on that earlier interaction analysis, I've tried, first of all, setting everything before 1950 to 1950, because it seems to be some kind of missing value. I've then set age to be equal to sale year minus year made. And so then I try running a random forest on that. And indeed, age is now the single biggest thing. Sale elapsed is way back down here. Year made is back down here. So we've kind of used this to find an interaction. But remember, of course, a random forest can create an interaction through having multiple split points. So we shouldn't assume that this is actually going to be a better result. And in practice, I actually found when I looked at my score and my RMSE, adding age was actually a little worse. We'll see about that later, probably in the next lesson. Okay. So one last thing is tree interpreter. This is also in the category of things that most people don't know exist, but it's super important. Almost pointless for like Kaggle competitions, but super important for real life. And here's the idea. Let's say you're an insurance company and somebody rings up and you give them a quote and they say, oh, that's $500 more than last year. Why? Okay, so in general, you've made a prediction from some model and somebody asks why. And so this is where we use this method called tree interpreter. And what tree interpreter does is it allows us to take a particular row. So in this case, we're going to pick row number 0, right? So here is row 0, right? Presumably this is like year made. I don't know what all the codes stand for, but like here's all of the columns in row 0. What I can do with a tree interpreter is I can go ti.predict, pass in my random forest, pass in my row, so this would be like this particular customer's insurance information, or this, in this case, this particular auction, right? And it'll give me back 3 things. The first is the prediction from the random forest. The second is the bias. The bias is basically the average sale price across the whole original data set, right? So like remember in our random forest, we started with single trees. Oh, we haven't got a draw in there anymore. But remember, we started with a single tree in our random forest. And we split it once, and then we split that once, and then we split that once, right? And we said like, oh, what's the average value for the whole data set? Then what's the average value for those where the first split was true? And then what's the average value where the next split was also true, until eventually you get down to the leaf nodes where you've got the average value you predict, right? So you can kind of think of it this way. If this, for a single tree, if this is our final leaf node, right, maybe we're predicting like 9.1, right? And then maybe the average log sale price for the whole lot is like 10.2, right? That's the average for all the options. And so you could kind of like work your way down here. So in fact, let's go and create this. Let's actually go and run this so we can see it. Okay, so let's go back and redraw this single tree. You'll find like in Jupyter Notebooks, often a lot of the things we create, like videos, progress bars and stuff, they don't know how to like save themselves to the file. So you'll see just like a little string here. And so you actually have to rerun it to create the string. So this was the single tree that we created. So the whole data set had an average log sale price of 10.2. The data set for those with coupler system equals true had an average of 10.3. The data set for coupler system equals true, enclosure less than 2 was 9.9. And then eventually we get all the way up here. And also model ID less than 4573, it's 10.2. So you could kind of like say, okay, why did this particular row, let's say we had a row that ended up over in this leaf node, why did we predict 10.2? Well, it's because we started with 10.19, and then because the coupler system was less than 0.5, so it was actually false, we added about 0.2 to that, so we went from 10.1 to 10.3, right? Sorry, 10.2 to 10.3. So we added a little bit because this one is true, and then to go from 10.3 to 9.9, so because enclosure is less than 2, we subtracted about 0.4, and then because model ID was less than 4500, we added about 0.7, right? So you could see like with a single tree, you could like break down like why is it that we predicted 10.2, right? And it's like at each one of these decision points, we're adding or subtracting a little bit from the value. So what we could then do is we could do that for all the trees. And then we could take the average. So every time we see enclosure, did we increase or decrease the value and how much by? Every time we see model ID, did we increase or decrease the value and how much by? And so we could take the average of all of those. And that's what ends up in this thing called contributions. So here is all of our predictors, and here is the value of each. And so this is telling us, and I've sorted them here, that the fact that this thing was made in 1999 was the thing that most negatively impacted our prediction. And the fact that the age of the vehicle was 11 years was what most positively impacted.
I don't think you actually. I think you actually need to sort after you zip them together.
They seem to be sorted, negative 0.5.
Well, no, the
0.1.
values are sorted, but then they're just reassigned to the columns in the original order. Which is why an 11-year-old tractor is what's most positively impacting price.
Thank you. That makes perfect sense. Yes, we need to do an index sort. Okay. Thank you. We'll make sure we fix that by next week. So we need to sort columns by the index contributions. So then there's this thing called bias, and so the bias is just the average before we start doing any splits, right? So if you basically start with the average log of value, and then we went down each tree, and each time we saw year made, we had some impact, coupler system, some impact, product size, some impact, and so forth, right? Never mind. Okay, so I think what we might do is we might come back to, because we're kind of out of time, we might come back to tree interpreter next time. But the basic idea, this was the last of our key interpretation points, and the basic idea is that we want some ability to not only tell us about the model as a whole and how it works on average, but to look at how the model makes predictions for an individual row. And that's what we're doing here. Okay, great.